Welcome to Luminous Starlight Audiobooks. This is 50 Animals That Shaped Civilization, the complete audiobook. Chapter 1. The Mosquito. The deadliest soldier in history. The accidental weapon. No general has ever won as many wars as the mosquito. Not Napoleon. Not Genghis Khan. Not Alexander the Great. While history books credit human commanders with the outcomes of civilization's pivotal conflicts, the evidence points elsewhere. An estimated 52 billion people, nearly half of all humans who have ever lived, were killed by diseases carried by a creature the size and weight of a grapeseed. The mosquito didn't just witness history. She wrote it. And here is the detail that reframes everything. Mosquito-borne diseases did not exist in the Americas before 1492. The indigenous civilizations of the New World, the Aztec, the Maya, the Inca, were not destroyed primarily by Spanish steel. They were destroyed by Spanish mosquitoes. Hernán Cortés arrived with 600 men. The malaria and yellow fever that followed him arrived with billions. In 1697, the Kingdom of Scotland attempted to establish a trading colony on the Caribbean shore of Panama. New Caledonia was meant to position Scotland to dominate Atlantic and Pacific trade simultaneously, a bold geopolitical gamble funded by a large share of the nation's liquid capital, and staffed by 2,500 volunteers who believed they were building an empire. Within 2 years, some 70% of them were dead of fever. Their immune systems had no defenses against yellow fever or malaria. The mosquito did what no army could. Scotland, bankrupted by the disaster, accepted union with England in 1707 partly to resolve the debts the collapsed colony had created. The United Kingdom, one of the most consequential political entities in modern history, exists, in part, because of a mosquito. This is the kind of causality that never appears in school textbooks, and probably should. Washington's secret weapon. In the summer of 1781, the American Revolution was not going well for George Washington. His army was exhausted, undersupplied, and outmaneuvered in the Southern theater. What turned the war was not a brilliant tactical stroke. Washington's greatest asset in the final campaign was the malarial Anopheles mosquito, which systematically destroyed the fighting capacity of British forces under General Charles Cornwallis. British soldiers, newly arrived from England, had no immunity. American troops, many of them Southerners who had grown up in malarious lowlands, had partial resistance built from years of exposure. Cornwallis surrendered at Yorktown in October 1781 not because he was outgeneraled, but because a significant portion of his army was too sick to stand, let alone fight. The gin and tonic, still ordered in bars around the world today, is a direct descendant of this dynamic. British soldiers stationed in India and Africa were required to take quinine, the antimalarial compound derived from cinchona bark, as a daily prophylactic. To make the intensely bitter compound palatable, they mixed it with gin, sugar, and lime. The cocktail that became synonymous with colonial leisure was, at its origin, medicine. The mosquito invented it. The mosquito has killed more humans than any other cause of death in our species' history, and she is not finished yet. Timothy Weingard, The Mosquito, 2019. The equalizer that wasn't. The mosquito did not distribute its damage equally. This is its darkest legacy. Partial acquired immunity to mosquito-borne diseases, developed over generations of exposure, was more common among West Africans than among Europeans. Colonial plantation owners, observing that African laborists survived tropical fevers that killed European indentured servants, drew a catastrophic conclusion, that Africans were biologically suited to brutal labor in hot climates. The mosquito's biology became a rationale for the transatlantic slave trade. The distortion ran even deeper. Widespread malaria prolonged the American Civil War by degrading the combat effectiveness of both armies, particularly in Southern campaigns. Some historians argue that without malaria extending the conflict, a faster Union victory might not have produced the political conditions that led to the Emancipation Proclamation in 1863. The mosquito shaped not just the war's duration, but its moral turning point. What the mosquito is doing right now. The mosquito has not lost. Current estimates place mosquito-related deaths at over 2 million per year, a figure that has barely moved despite a century of insecticides, bed nets, and vaccine research. Deaths caused by other humans, by comparison, average around 475,000 annually. We are, by a considerable margin, more dangerous to each other than almost anything else alive except for her. As global temperatures rise, the mosquito's viable range expands northward and to higher altitudes, reaching populations that have been free of malaria and dengue for generations. Those populations have no immunity. History offers a consistent lesson about what happens next. The mosquito has always been most lethal when it meets people who believe they are finally safe. There is a bitter irony in the modern response to this threat. The same global connectivity that spreads disease-carrying mosquitoes across continents also carries the scientific tools to fight them: gene-drive technology that could theoretically collapse entire mosquito populations, mRNA vaccines adapted from COVID research, satellite mapping of breeding grounds. Whether these tools arrive in time, and whether they reach the populations most at risk, is a question that is less about science than about political will and economic priority. The mosquito has always exploited the gaps between what humans know and what they choose to do. That gap remains wide. Chapter 2. The Beaver. The animal that drew the map of North America. The hat that conquered a continent. The map of North America was not drawn by generals or kings. It was drawn by a hat. For 2 centuries, the single most coveted object in European fashion was a broad-brimmed felt hat made from beaver fur, dense, water-resistant, and capable of holding its shape through decades of wear. Statesmen wore them. Clergy wore them. Military officers wore them as markers of rank. And because European beavers had been hunted to near extinction by 1600, the entire colonial project in the northern half of a continent was organized, almost from the beginning, around finding more of them. The French founded Quebec in 1608 not because Samuel de Champlain was seized by a vision of civilization on the St. Lawrence River, but because the beaver populations upstream were vast and largely untouched. The Dutch settled Manhattan in 1626, famously purchased for 60 guilders worth of trade goods, because the Hudson River Valley was one of the richest beaver habitats on the continent. The English chartered the Hudson's Bay Company in 1670 after 2 explorers returned to London with reports that beavers were everywhere in the lands to the west. King Charles II granted the charter within months. The animal that built Canada, and shaped the early United States, was not the eagle. It was a rodent with a flat tail and a talent for waterproofing. To understand why a hat reorganized a hemisphere, it helps to understand what beaver felt actually was. The beaver's underfur consists of microscopic barbed fibers that, when heated and pressed, lock together into a material of extraordinary durability. Wool felt deteriorates in rain, beaver felt repels it. Wool felt loses its shape, beaver felt holds it for decades. In an era before synthetic materials, before reliable waterproofing, before mass-produced clothing of any kind, a beaver felt hat was a genuinely superior technology, and fashion, as it always does, followed function until function became status. By the 1580s, beaver wool had become the primary material of French hatmakers, spreading quickly to England after Huguenot refugees carried their craft across the Channel. Demand rose faster than European supply could meet it. Russia, the previous main source, had hunted its own beaver populations into near collapse. North America, with an estimated 60 million beavers before European contact, was the solution. What began as incidental trading between Basque fishermen and indigenous peoples on the Newfoundland coast became within a generation the economic engine of an entire colonial era. Wars fought for a rodent. The beaver wars of the 1640s and 1650s were not, as their name might suggest, a minor colonial skirmish. They were a catastrophic series of conflicts initiated by the Iroquois Confederacy to establish a monopoly over the fur trade between the Great Lakes and the European settlements on the Atlantic coast. The Iroquois, having exhausted the beaver populations in their own territory by the 1630s, systematically destroyed their neighbors, the Huron, the Erie, the neutral nation, and displaced tens of thousands of people across the Great Lakes region. Entire nations ceased to exist as political entities. The demographic map of northeastern North America was permanently redrawn. The cause was not religion, not territorial ambition in the conventional sense, not ancient grievance. It was beaver pelts. European powers were simultaneously fighting their own version of the same war. France and England's colonial rivalry in North America, the conflict that eventually produced the 7 Years' War, the fall of New France in 1763, and the geopolitical conditions that made the American Revolution possible, was substantially a competition for beaver territory. The borders that emerged from these conflicts were not drawn according to geography or population, they were drawn according to where the animals were. Trappers called beaver pelts furry banknotes. In the early 1800s, for pelts could buy a pistol. The currency of a continent ran on a rodent. Eric J. Dolin, Fur, Fortune, and Empire, 2010. The End of an Era, and What It Left Behind. The beaver's reign ended not through conservation but through fashion. In the 1840s, silk hats became the new marker of European status, displacing beaver felt almost overnight. Demand collapsed. The Hudson's Bay Company, which had built a commercial empire on the animal's back, pivoted to other goods. But the damage to beaver populations across the continent was severe in many regions. Animals that had numbered in the tens of millions had been reduced to near extinction. Their disappearance was not only ecological. Beaver dams regulate water flow, create wetlands, raise water tables, and support the fish populations that entire indigenous economies depended on. When the beavers went, the ecosystems went with them. Today, beaver populations in North America have partially recovered, and conservation biology has given the animal a new kind of fame. Ecologists now describe beavers as a keystone species, creatures whose dams and ponds create habitat for hundreds of other species, slow erosion, filter water, and reduce the severity of drought. Ranchers in the American West have begun deliberately reintroducing beavers to degraded streams and watching the landscape recover within seasons. The same animal that drove 2 centuries of colonial warfare is now being deployed as a tool of ecological restoration. Its value, it turns out, was never really in the hat. Chapter 3. The Cod. How a Fish Rewrote the Atlantic World. The fish that built an empire. Before the Pilgrims, before Columbus in practical terms, before any permanent English settlement in North America, there was the cod. European fishermen, Basques, Portuguese, Bristol merchants were crossing the Atlantic annually by the 1480s, perhaps earlier, drawn not by gold or land but by the staggering abundance of a single fish off the coast of what is now Newfoundland. The Grand Banks, the shallow underwater plateau southeast of Newfoundland, produced cod in numbers that defied belief. John Cabot's crew in 1497 reportedly lowered baskets into the sea and pulled them up full of fish. The only capital required was salt, wood for ships, and the willingness to survive the North Atlantic crossing. Salt cod, dried, preserved, cheap to ship, became the protein engine of the Atlantic economy. It fed the enslaved populations of Caribbean sugar plantations, the urban poor of Catholic Europe during hundreds of meatless fast days, and the armies of half a dozen empires. Where the fish went, civilization followed. The price of salt. The technology that made cod valuable was not a fishing technique but a preservation method. Salt cod, heavily brined, then air-dried until it becomes hard as wood, could survive months at sea and years in storage without refrigeration. This gave it a reach that fresh fish could never match. Catholic Europe's religious calendar, with its 100-odd meatless fast days per year, created structural demand for preserved fish across an entire continent. The Church had inadvertently designed a protein supply chain, and the cod of the North Atlantic was its central link. The Basques, with access to salt mines in the Bay of Biscay, were early masters of this trade. They guarded their fishing grounds as state secrets, which is why we have almost no documentation of their transatlantic voyages before Cabot. The fish were too profitable to advertise. The triangular trade that defined the early Atlantic economy ran on cod. New England fishermen caught cod. They sold the lowest grades, the broken, the undersized, the brine-soaked remnants, to the Caribbean plantation economies as feed for enslaved workers. The profits bought molasses. The molasses became rum. The rum bought more labor. The triangle had many sides, but one of them was always fish. The varieties of cod commerce reveal the brutal hierarchies of the Atlantic world. The finest salt cod, large, uniform pieces from prime fish, went to Mediterranean Catholic markets where consumers had money and standards. The broken pieces, the undersized fish, the oversalted remnants went to Caribbean plantation operators as the cheapest protein available for enslaved workers. The same fish, caught on the same banks, in the same haul, produced entirely different products depending on the social position of the intended consumer. The cod trade was not simply an economy. It was a system of stratification made of fish. The sacred cod was not decor. It was a frank acknowledgement that New England's political independence had been purchased with fish. Mark Kurlansky, Cod, A Biography of the Fish That Changed the World, 1997. The fish that funded revolutions. The economics of the cod trade were revolutionary in a precise, literal sense. New England merchants who dominated the North Atlantic fishery in the 18th century accumulated capital independent of British financial institutions. They did not need London banks. They had fish. When Britain passed the Navigation Acts and later closed New England ports to the fishing trade, it was not merely an economic insult, it was an existential threat. The cod fishery was the financial foundation of colonial New England. Cutting it off was cutting off the oxygen supply. The Massachusetts House of Representatives hung a carved wooden cod above its chamber in 1784. The sacred cod, as it is still called, was not whimsy. It was a frank acknowledgement that the political independence of Massachusetts had been purchased, in meaningful part, with fish. The collapse that changed everything. For 500 years, the Grand Banks seemed inexhaustible. In 1992, the Canadian government closed the North Atlantic cod fishery entirely. The stock had not declined, it had collapsed. 5 centuries of extraction had reduced one of the planet's most abundant fish populations to near functional extinction in the span of a single generation of industrial trawling. The closure put 35,000 people out of work overnight, the largest single-event layoff in Canadian history. Entire coastal communities in Newfoundland lost their economic reason for existing. Some have not recovered. The cod collapse was not merely an environmental event. It was a demonstration that the Atlantic civilization built on this fish had been systematically spending down a capital stock it assumed was infinite. The sacred cod in the Massachusetts State House now hangs as something closer to an epitaph. The civilization the cod built is still here. The cod largely is not. The economic and ecological logic of the collapse followed the same pattern seen in every major wild fishery that has failed. The catches stayed high until they didn't, because the last generation of fishing effort was concentrated on the last generation of fish. The warning signs were there in declining average fish sizes and longer voyage times, but the industry's capital structure, boats, processing plants, port facilities, made it nearly impossible to reduce effort voluntarily before the stock failed completely. Chapter 4. The Silkworm. The worm that connected the world. The monopoly. For 3,000 years, China possessed what was arguably the most valuable industrial secret in human history. The silk produced by the larvae of Bombyx mori, a domesticated moth that can no longer survive in the wild, was the closest thing the ancient world had to a luxury material that could not be substituted or replicated. It was lighter than wool, stronger than cotton, lustrous in ways that no other fiber could match. Roman emperors paid for it with gold by weight. Persian kings wore it to signal supremacy. The trade routes that carried it halfway around the world became so central to commerce and culture that we still call them the Silk Road, as if the road itself were made of the material it transported. The Chinese understood that the secret of silk production, the cultivation of mulberry trees, the harvest of cocoons, the unreeling of the single continuous filament that each cocoon contains, was worth more than the silk itself. Exporting the knowledge was a capital offense. For centuries, this prohibition held. Then, in 552 CE, two Byzantine monks arrived at the court of Emperor Justinian I with a gift hidden inside their hollow walking canes, the eggs of the silkworm. The smuggled eggs changed everything. Byzantine silk production began within a generation. Within a century, Persia, Syria, and eventually Italy had their own sericulture industries. China's monopoly, the stranglehold on the most valuable material in the ancient world, was broken by two monks and a pair of canes. The Silk Road did not disappear. Trade in finished silk continued for centuries. But its terms had shifted irrevocably. The worm itself. The silkworm is one of the most thoroughly domesticated animals on Earth, so thoroughly that it has lost nearly all capacity for independent survival. Wild populations of Bombyx mori no longer exist. The moth cannot fly effectively. The larvae cannot find food on their own. The entire species exists only in relationship with human cultivation, an arrangement that has persisted for at least 5,000 years. What the silkworm produces, in exchange for this dependence, is extraordinary. Each cocoon consists of a single continuous filament of protein fiber up to 1,500 meters long, produced by the larva as it spins its protective case. When heated in water, the sericin binding the filament dissolves, and the thread can be unreeled, twisted with others, and woven into fabric of remarkable properties. The filament is stronger per weight than steel. It absorbs moisture without feeling wet. It insulates in cold and releases heat in warmth. Silk's luster comes from the prism-like triangular structure of each fiber, which refracts light at multiple angles simultaneously. In 552 CE, two monks arrived at the Byzantine court with the eggs of the silkworm hidden in their hollow walking canes. The 3,000-year monopoly on the most valuable material in the ancient world ended with a pair of canes. Xinru Liu, The Silk Road in World History, 2010. The road it built. The Silk Road was not a road. It was a network of shifting overland and maritime routes connecting China with Central Asia, the Middle East, and the Mediterranean, a network that carried not only silk but spices, paper, gunpowder, Buddhism, Islam, the Black Death, and the agricultural crops that transformed the diets of every civilization it touched. The cities that grew up along these routes, Samarkand, Kasha, Dunhuang, were among the most cosmopolitan places on Earth before the age of modern globalization. Merchants from a dozen linguistic traditions met and traded in their markets. Artistic styles blended across thousands of miles. The religions of the world spread along these same paths, carried by merchants who needed common frameworks of trust in unfamiliar territories. None of this infrastructure existed to move silk specifically. It existed to move anything of value across difficult terrain. But it was silk, small, light, extraordinarily valuable, and impossible to produce outside a narrow band of climate and expertise that made the economics work. The worm that could not leave its mulberry tree nonetheless connected the ancient world. What the silkworm is now. Global silk production today is dominated by China and India, as it has been for most of recorded history. The industry employs an estimated 1 million people in India alone. But silk's share of the global textile market is less than 0.2%, a fraction of what it once was, displaced by synthetic fibers that replicate many of its properties at a fraction of the cost. What has not been replicated is the chemistry. Silk fibroin, the protein that makes up the filament, has become one of the most researched biomaterials in medicine. Its biocompatibility with human tissue, its strength, and its gradual biodegradability make it ideal for sutures, scaffolding for tissue regeneration, and drug delivery systems. The worm that built the ancient world's most powerful trade network is now being asked to help rebuild damaged human hearts. Its utility, it turns out, was never fully understood. Chapter 5. The Pigeon. The soldier who could not be shot down. Cher Amy. On October 3, 1918, in the Argonne forest in northeastern France, an American battalion of nearly 600 men found itself surrounded by German forces and being shelled accidentally by its own artillery. The battalion's commander, Major Charles Whittlesey, had no working radio. He sent 2 pigeons carrying messages to headquarters. Both were shot down by German snipers who understood exactly what the birds carried. He had 1 pigeon left, a small blue-checked cock named Cher Amy. Cher Amy was released into German fire. He was hit almost immediately, shot through the breast, blinded in one eye, and his right leg nearly severed, hanging by a tendon with the message capsule still attached. He kept flying. He covered the 25 miles to divisional headquarters in under 30 minutes. The message reached the artillery commander. The guns stopped. 194 men who would have died did not. Cher Amy was awarded the Croix de Guerre with Palm by France. American surgeons carved him a small wooden leg. He died the following year and was preserved. You can still see him in the Smithsonian. The story of Cher Amy is unusual in its drama but not in its structure. Carrier pigeons served in every major conflict from the Franco-Prussian War through the Second World War. They were used by both sides, in every theater, because they solved a problem that no other technology of the era could: reliable one-way communication across contested territory. Radio signals could be jammed or intercepted. Runners could be shot. A pigeon flying at 60 miles per hour at 300 feet altitude was nearly impossible to stop. Armies knew this, which is why snipers were assigned specifically to kill enemy birds. How the bird works. The homing pigeon's navigational ability is among the most studied and least fully explained phenomena in biology. A pigeon removed from its loft, transported in darkness to an unfamiliar location hundreds of miles away, and released will return home with accuracy that continues to astonish researchers. The bird appears to use a combination of the Earth's magnetic field, the position of the sun, low-frequency sounds, and most recently documented olfactory maps built from the specific chemical signature of air currents at its home loft. What makes the carrier pigeon militarily valuable is that this navigation is one-directional. The bird flies home. You cannot send a message to an unknown location. You can only send it to the place where the bird was raised. Armies overcame this limitation by deploying mobile lofts, trucks or vans containing the pigeon's home birds that could be positioned wherever communication was needed. The message would be written, attached to the bird's leg, and the bird released from the front. It would fly to the mobile loft, wherever that happened to be. Cher Amy was shot through the breast, blinded in one eye, his leg hanging by a tendon. He kept flying. He covered 25 miles in under 30 minutes. 194 men who would have died did not. Racing Pigeon Digest, Account of the Lost Battalion, 1918. Reuters and the Pigeon Post. The military use of carrier pigeons is well documented. Less remembered is their role in creating the modern financial press. Paul Julius Reuter, before he founded the news agency that still bears his name, ran a network of 45 carrier pigeons between Brussels and Aachen in 1850, bridging a gap in the telegraph line between Paris and Berlin that took 6 hours by train. His pigeons made the crossing in 2. The financial information he carried, stock prices, political intelligence, arrived in London hours before any competitor. The Reuters news agency that grew from this operation became one of the most influential information businesses in the world, and it began with pigeons. The telegraph eventually replaced the pigeon post for commercial purposes, as it replaced it for most other applications. But the lesson persisted: reliable, fast, point-to-point communication is worth enormous amounts of money to the people who need it. The pigeon taught us this, and every communications technology since has been trying to do what the pigeon did, just faster. The modern pigeon. Today's urban pigeon is the feral descendant of the rock dove, the same species as the carefully bred carrier pigeon, now living in the ecological niche originally occupied by cliff-dwelling birds, finding in human architecture an adequate substitute for rock faces. They are widely regarded as pests. The same animal that received military honors, carried stock prices that moved markets, and saved the lives of soldiers in 2 world wars now competes with pigeons for crumbs in city squares. The irony is sharp but not unusual. Animals that served human civilization at critical moments are often discarded when the moment passes. The pigeon's navigational abilities are no longer economically or militarily necessary. What remains is the bird itself, carrying no message anyone needs, navigating back to roosts no one wants it to find. It is still, by any objective measure, extraordinary. We have simply stopped needing it to be. Chapter 6. The Flea. The tiny courier that ended the Middle Ages. What the flea carried. The Black Death arrived in Europe in 1347 on 12 Genoese trading ships docking at Messina, Sicily. Sailors on the ships were already dead or dying, covered in black swellings that oozed blood and pus. The Sicilian authorities ordered the ships out of harbor immediately. It was too late. Within 5 years, between a third and half of Europe's population was dead, somewhere between 25 and 50 million people, in a span of time so short that the dead could not be buried, the living could not be tended, and the social order that had governed medieval Europe for centuries fractured beyond repair. For most of that time, historians blamed the rats. Specifically, they blamed the black rat, which carried Yersinia pestis in its bloodstream, and which spread the bacterium to humans through its bite. This is partially correct, but the rat was never the vector. The flea was. The rat flea, Xenopsilla chiopis, fed on infected rats and then, when those rats died, sought new hosts. Human beings were convenient. A single flea bite was sufficient to introduce enough bacteria to trigger infection. The rats were carriers. The fleas were the delivery mechanism. The plague was a flea problem wearing a rat mask. The world it unmade. Before the Black Death, the dominant labor system in Western Europe was feudalism, peasants bound to land they did not own, performing labor for lords in exchange for protection and the right to farm small plots. The system was stable precisely because labor was plentiful and land was scarce. Peasants had no leverage. After the Black Death, labor was extraordinarily scarce. Lords competing for the surviving peasants were forced to offer wages, reduced obligations, freedom of movement, and improved conditions. Peasants who survived discovered, for the first time in generations, that their labor had market value. The feudal system did not collapse overnight. It took another century of plague recurrences, peasant revolts, and social renegotiation, but the Black Death was the event that made it structurally unstable. The Church, which had presented itself as the intermediary between God and humanity, found its authority shattered by its inability to explain or prevent the catastrophe. A God who allowed a third of his creation to die in suppurating agony within months offered limited comfort to survivors. Alternative spiritual movements, mystical sects, and eventually the conditions for the Protestant Reformation all trace a line back to the credibility crisis the plague created. The flea, in a real sense, made the modern world by destroying the medieval one. The Black Death did not kill feudalism. It made feudalism structurally impossible. When labor became scarce, peasants discovered they had leverage for the first time in 300 years. John Kelly, The Great Mortality, 2005. The Flea in Science. The flea is not only a historical villain. It is a biological marvel. The flea's jump, proportionally among the most powerful in the animal kingdom, was for decades attributed entirely to muscle power. High-speed photography eventually revealed the truth. The flea's jump is powered by a compressed pad of resilin, a rubber-like protein stored in the thorax, that is released like a miniature catapult. The mechanism produces an acceleration of roughly 100 g, compared to the approximately 5 g experienced by astronauts during rocket launches. The flea feels none of it, because its exoskeleton is designed specifically to withstand these forces. Engineers studying efficient mechanical systems have spent decades trying to understand and replicate the flea's spring mechanism. Resilin-inspired materials are now being developed for use in robotics, prosthetics, and shock absorption systems. The creature that destroyed medieval Europe may yet prove useful for building the infrastructure of the modern one. Why the flea still matters. Plague is not a historical curiosity. Yersinia pestis is still present in rodent populations across Central Asia, the American West, and parts of Africa. Small outbreaks occur regularly, a handful of cases per year in the United States, more in Madagascar, which experienced a significant outbreak as recently as 2017. The bacterium has not gone anywhere. The conditions that allowed it to become the Black Death, dense, malnourished, immunologically naive populations living in close proximity to rats, without access to antibiotics or public sanitation, have largely been eliminated in wealthy countries. In places where those conditions persist, the flea is still a potential catastrophe waiting for the right moment. The flea does not know any of this. It does not know that it ended the Middle Ages, enabled the labor market, or contributed to the conditions that produced the Renaissance. It knows only that it is hungry, and that warm bodies are available. That has always been enough. The flea's current global distribution is itself a product of human mobility. Rat fleas arrived in new continents on the same ships as rats. Cat fleas and dog fleas spread with pet ownership. Human fleas, Pulex irritans, followed human migration routes across every continent. The insect that carried the Black Death across medieval Europe is now cosmopolitan, adapted to the full range of warm-blooded hosts available in human environments, and far better distributed than at any point in its evolutionary history. We have, inadvertently, given the flea the world. Chapter 7. The Whale. The oil that lit the Industrial Revolution. What we burned before coal. The common assumption is that the Industrial Revolution ran on coal. This is true of the factories. It is not true of the streets, the lighthouses, the homes, or the workshops where the revolution's first generation of workers lived and labored. Before kerosene was refined from petroleum in the 1850s, the light by which the industrializing world read, worked, and navigated at night came primarily from one source, the rendered fat of the sperm whale. Spermaceti, the waxy substance found in the enormous organ that fills the sperm whale's forehead, burns with an exceptionally bright, clean, nearly odorless flame. It was superior to every alternative available before petroleum. Tallow candles smelled and guttered, vegetable oils were expensive and uneven, coal gas was viable only in large cities with the infrastructure to distribute it. Spermaceti could be packed into barrels and shipped anywhere in the world. Sperm whale oil lubricated the machinery of the early Industrial Revolution. It kept the timepieces of the Royal Navy running. It lit the lighthouses that guided the ships that moved global trade. The sperm whale, in other words, was not merely a target of the whaling industry. It was a critical piece of industrial infrastructure, a mobile petroleum reserve, approximately 60 feet long, distributed across the world's deep oceans. The industry that chased them. New Bedford, Massachusetts, in the 1840s was one of the wealthiest cities per capita in the United States. Its wealth came entirely from whales. Whaling voyages lasted 3 to 5 years, ranging as far as the Pacific and the Arctic Ocean, pursuing sperm whales that had been the dominant target of the industry since the 1720s. Herman Melville sailed on a Nantucket whaler in 1841 and spent 18 months at sea before jumping ship in the Marquesas Islands. The novel he eventually wrote, Moby Dick, published in 1851, is, among many other things, the most detailed account of the economics, technology, and culture of an industry that was already beginning to decline. At its peak in the 1840s and 1850s, the American whaling fleet numbered over 700 ships. They killed an estimated 200,000 sperm whales over the industry's 2-century run. The whales did not collapse all at once, the populations were too widely distributed for that, but by the 1860s, voyages were lasting longer and returning with less oil, as hunters had to travel farther to find animals that were learning to avoid ships. The industry was already contracting before petroleum arrived to finish it. The sperm whale was not merely a target of an industry. It was industrial infrastructure, a mobile petroleum reserve, 60 feet long, distributed across the world's deep oceans. Eric J. Dolin, Leviathan, The History of Whaling in America, 2007. The oil that replaced them. Edwin Drake drilled the first successful commercial oil well in Titusville, Pennsylvania, in 1859. Kerosene, refined from crude oil, was immediately cheaper to produce than spermaceti, equally bright, and available in essentially unlimited quantities. Within a decade of Drake's well, the sperm whale oil market had collapsed. The whaling industry, which had sent hundreds of ships to the far corners of the earth in pursuit of a specific animal, found itself economically obsolete almost overnight. The irony of this displacement has not been lost on environmental historians. The discovery of petroleum, which we now understand as an environmental catastrophe in slow motion, saved the sperm whale from near-certain extinction. The species had been commercially hunted for 150 years by the time kerosene arrived. Another 50 years at the same rate would have been devastating. The whale survived the industrial era because an even more consequential fuel was found. What that fuel is doing to the whale's ocean is a separate problem. The whale's second story. Sperm whales are among the most cognitively complex animals ever studied. They live in matriarchal family groups with complex social structures. They communicate through patterns of cliques coders that appear to constitute dialects specific to particular social groups. Young sperm whales learn these dialects from their mothers and grandmothers and maintain them across lifetimes. Researchers studying sperm whale communication have identified what appear to be culturally transmitted behavioral traditions, specific hunting techniques, migratory routes, social norms that vary between populations and are passed on through learning rather than genetics. The animal that lit the Industrial Revolution was, all along, a cultural being with something like language, memory, and tradition. We did not know this when we were boiling it into lamp oil. We know it now, which creates an obligation that the 19th century did not feel. The sperm whale is not endangered. It is still present in every major ocean. What remains uncertain is whether the ocean it swims in will remain suitable for it, whether the warming and acidification driven by the very petroleum that replaced whale oil will undo what the harpoon could not. The discovery that sperm whales have cultural dialects, communication patterns specific to social groups, transmitted through learning rather than genetics, arrived at roughly the same time that the global ocean they inhabit began showing measurable signs of warming and acidification. The two facts sit side by side in the scientific literature without obvious resolution. We have learned enough about the sperm whale to understand that it is a cultural animal with something like language and memory. We have not learned it in time to prevent the ocean chemistry changes that may undermine the deep-diving, long-migrating life history that its culture depends on. Chapter 8. The Oyster. The filter feeder that built New York. 900 billion oysters. Before the Dutch arrived in 1609, New York Harbor contained an estimated 900 billion oysters. The beds covered approximately 350 square miles of the harbor floor, forming reefs in some places that were a hazard to navigation. Each oyster filtered up to 50 gallons of water per day. The harbor was, by any measure, one of the most productive marine ecosystems on the east coast of North America, clear, cold, extraordinarily rich in the finfish, crustaceans, and waterfowl that depended on the filtration the oysters provided. Today, New York Harbor's oyster population is functionally zero. The beds were systematically destroyed over 2 centuries of overharvesting, pollution, and harbor development. The last commercial oyster harvest from New York Harbor took place in 1927. The harbor, without its filter feeders, became one of the most polluted bodies of water in the world, a condition that persisted until the Clean Water Act of 1972 and decades of remediation work began to reverse it. What the oysters had done for free, for millennia, the city of New York now spends hundreds of millions of dollars attempting to replicate with infrastructure. The food of the poor. The oyster's career in New York is a story of inversion. In the 17th and 18th centuries, oysters were so abundant in New York Harbor that they were the food of the poor, sold from street carts, eaten raw by dock workers, piled in shells on the corners of Lower Manhattan. Oyster middens from the pre-colonial period, accumulated by indigenous communities over centuries, formed significant portions of the landscape. The shells were used as building material, as road fill, as the source of lime for cement. As the population of the city grew and the oyster beds began to decline, the price rose. By the late 19th century, the dynamic had fully inverted. Oysters had become luxury food, served at expensive restaurants, consumed by the wealthy. The poor who had once eaten them from street carts could no longer afford them. The pattern, abundant natural resource consumed until scarce, then revalued as luxury, is one that repeats throughout the history of Atlantic seafood, and oysters were among the first to complete the cycle. New York Harbor's oyster beds filtered the entire harbor every few days, for free, powered by sun and tide, for 7,000 years. We harvested them to extinction, then spent billions trying to replicate what they did. Mark Kurlansky, The Big Oyster, History on the Half Shell, 2006. What an oyster is. An oyster is a pump. It has no brain, no central nervous system capable of anything we would recognize as experience, no ability to move once it has settled. What it has is an extraordinary capacity to filter seawater through its gills, extract phytoplankton, and in doing so clarify the water around it. A single adult oyster filters 50 gallons of water per day. A reef of oysters filters the equivalent of an entire harbor in days. Nitrogen, phosphorus, sediment, and pathogens are captured, concentrated, and deposited as shell or feces on the harbor floor, where they are buried and removed from circulation. This filtration service is now recognized as one of the most economically valuable ecological services provided by any organism in coastal ecosystems. Economists attempting to calculate the dollar value of what New York Harbor's oyster beds would be worth in terms of water treatment alone have produced figures in the hundreds of millions of dollars annually. The oyster provided this service for nothing, powered by the sun and the tide, for approximately 7,000 years before European settlement. The decision to harvest it to extinction was, in economic terms, one of the most expensive choices the city ever made. The oyster's filtration service has a specific implication for how we think about the value of nature. The service was never priced, never invoiced, never accounted for in any budget. It simply happened, continuously, for 7,000 years, until it stopped. Only when it stopped, when the harbor turned murky, the finfish populations crashed, and the city began spending money on water treatment infrastructure, did anyone attempt to calculate what had been lost. The pattern is not unique to oysters. It is the standard pattern for every ecosystem service provided by every natural system that has been destroyed by human activity. We discover the value at the moment of elimination. The return. Since 2014, the Billion Oyster Project has been working to restore 1 billion live oysters to New York Harbor by 2035. The project uses shells collected from New York City restaurants, 1.4 million pounds of shell per year, as substrate for young oysters cultured in floating nurseries. The juvenile oysters are then deployed onto artificial reefs in the harbor. Early results are promising. Water clarity is improving in areas where the reefs have been established, and fish populations are recovering. The project will not recreate what existed before European settlement. The harbor is too altered, the water chemistry too different, the surrounding land too developed for that. What it may achieve is a partial restoration of the filtration capacity that once made the harbor one of the richest estuaries in the world. The oyster is being asked to fix what human beings broke. The animal that built New York's ecology, fed its poor, and was then consumed into near extinction is slowly being invited back. Whether the harbor still has room for it remains to be seen. Chapter 9. The Camel. The ship of the desert that carried Islam. The problem of distance. The Arabian Peninsula is not, at first glance, a place from which world historical religions and empires tend to emerge. It is hot, largely waterless, and surrounded by civilizations Egypt, Persia, Byzantium that are older, wealthier, and more densely organized. What the Arabian Peninsula had, in the 7th century CE, that none of its neighbors fully possessed was a logistical advantage that would take another millennium for its competitors to fully appreciate: the dromedary camel. The camel had been domesticated in the Arabian Peninsula around 3000 BCE. By the 7th century, Arabian traders had spent thousands of years developing the knowledge, infrastructure, and breeding programs to use the animal at the limits of its capacity. A properly loaded camel could carry 600 pounds across desert terrain that would kill a horse in a day. It could go without water for 2 weeks in cool weather. It could eat vegetation that other animals could not digest. It converted the Arabian desert from a barrier into a highway, and the people who controlled that highway controlled the most important trade route between the Mediterranean world and the Indian Ocean. The Prophet's economy. Muhammad ibn Abdullah was a caravan merchant before he was a prophet. He knew the camel routes between Mecca and Syria better than he knew almost anything else. The early Islamic community he built in Medina after 622 CE was, in economic terms, a caravan enterprise, mobile, networked, skilled at long-distance logistics, and comfortable with the vast distances of Arabian geography in ways that settled agricultural civilizations were not. The extraordinary speed of early Islamic expansion, from the Arabian Peninsula to Persia and Egypt within a decade, to North Africa and Spain within a century, is partly explained by military and religious factors. It is also explained by camels. Islamic armies could sustain supply lines across terrain that Byzantine and Sassanid forces could not cross efficiently. The camel gave Islamic forces a logistical reach that their opponents, organized around horse cavalry and river-based supply, could not match. When the armies of early Islam appeared, they appeared suddenly, from directions that were not supposed to be militarily accessible. The camel converted the Arabian desert from a barrier into a highway. The people who controlled that highway controlled the most important trade route between the Mediterranean and the Indian Ocean. Richard Bulliet, The Camel and the Wheel, 1975. The Bactrian and the Silk Road. The two-humped Bactrian camel, domesticated in Central Asia around the same period as the dromedary, served a different but equally consequential function. The Silk Road's overland routes across Central Asia, the Taklamakan Desert, the Pampas, the high grasslands of the steppe, were viable as commercial arteries only because of Bactrian camels. Their ability to carry heavy loads at altitude, in cold as well as heat, across terrain without water sources, made them the essential technology of the most important trade network in the pre-modern world. The caravans that moved silk, spices, glassware, paper, and ideas between China and the Mediterranean were not romantic adventures. They were industrial enterprises, organized with military precision, employing specialists in animal husbandry, navigation, finance, and diplomacy. At the center of every caravan was the camel, eating almost nothing, carrying everything, covering ground at a pace that made transcontinental trade economically feasible. The camel in America. In 1855, the United States Army imported 75 camels from Egypt and Turkey to support supply operations in the American Southwest. The experiment was championed by Jefferson Davis, then Secretary of War, who had calculated correctly that camels would outperform horses and mules in the desert terrain between Texas and California. The camels performed exactly as promised: superior load-bearing, dramatically lower water requirements, faster travel across desert terrain. The soldiers hated them. The camels were bad-tempered, unfamiliar, and frightened the horses. When the Civil War broke out and Davis resigned to lead the Confederacy, the program lost its sponsor. The camels were sold, abandoned, and released. Some survived in the Arizona desert for decades, occasionally alarming prospectors and ranchers. The last confirmed sighting of a feral American camel was in 1941. The experiment that almost gave the United States military a camel corps and might have changed the economics of westward expansion ended not because the technology failed but because the people using it refused to adapt to it. The camel, as it had been doing for 5,000 years, was simply waiting to be understood. The failed American camel experiment illuminates something consistent in the history of domesticated animals: the technology is never the constraint. Camels in the American Southwest worked exactly as their advocates promised. The constraint was always human: the resistance to unfamiliar animals, the disruption to existing systems, the absence of the accumulated cultural knowledge that makes working with an animal feel natural rather than alarming. Every successful domestication in history required generations of accumulated practice. The Americans tried to skip that accumulation and found that the animal alone was not enough. Chapter 10. The Horse. The engine that ran for 5,000 years. The domestication that changed war. The horse was domesticated on the steppes of what is now Kazakhstan approximately 5,500 years ago, initially for meat and milk. The moment someone sat on one was, in retrospect, among the most consequential events in military history. A mounted warrior moves 3 times faster than a running man, strikes from a height advantage that fundamentally alters the physics of combat, and can disengage from any fight he chooses to lose. Before the horse, armies were limited by how fast their soldiers could walk. After the horse, the strategic landscape of the ancient world was permanently altered. The stirrup, arriving in Europe from China via the steppe nomads around 700 CE, multiplied the horse's military value again. A rider without stirrups cannot deliver a couched lance strike without being thrown backward by the impact. With stirrups, a mounted warrior becomes, in effect, a human projectile backed by the horse's momentum. The feudal system of medieval Europe with its castle-holding knights, its hierarchies of mounted warriors, its culture organized entirely around the expensive maintenance of war horses, was made possible by a piece of metal looped around each foot. The collar that fed Europe. The horse's military role is well remembered. Its agricultural role is less often discussed, and arguably more important. For most of agricultural history, the heavy ploughing of European soils was done by oxen. Oxen are powerful but slow, covering perhaps 2 acres per day. A horse can cover 4 to 5. The problem was the harness. The throat and girth harness used on horses in antiquity tightened against the windpipe under load, partially strangling the animal and limiting the force it could exert. A heavily loaded horse in an ancient harness was operating at perhaps a quarter of its potential. The rigid horse collar, developed in China around 500 CE and reaching Europe through the same Central Asian conduits as the stirrup, transferred the load from the throat to the shoulders, where the animal's full muscular power could be applied. A collared horse pulling a wheeled plough could work land twice as fast as an ox. Medieval agricultural productivity, which historians have long noted increasing sharply in the 9th and 10th centuries, is substantially attributable to the horse collar. More food, on more land, produced the population growth that built the medieval cathedrals, the cities, and eventually the Renaissance. The horse collar transferred the load from throat to shoulder. A collared horse could work land twice as fast as an ox. Medieval Europe's population growth, the cathedrals, the cities, the Renaissance, was built on that shift. Lynn White Jr., Medieval Technology and Social Change, 1962. The Pony Express and the Telegraph. In April 1860, the Pony Express began carrying mail between St. Joseph, Missouri, and Sacramento, California, 1,900 miles in 10 days, using a relay of 400 horses and 80 riders. It was the fastest communication link between the eastern United States and California. It was also obsolete almost from the day it launched. The transcontinental telegraph, under construction the entire time the Pony Express operated, was completed in October 1861. The Pony Express immediately ceased operations, having run for 18 months at a substantial financial loss to its founders. The story is a capsule of the horse's entire technological history, unmatched for thousands of years, then replaced within a generation by something categorically different. The steam engine did to the horse what the telegraph did to the Pony Express, not immediately, not everywhere at once, but inexorably. By 1920, the working horse population of the United States was already in decline. By 1960, horses had been largely removed from agriculture and transportation. What the horse left behind. The horse did not disappear. It retreated from utility into culture. Equestrian sports, recreational riding, horse racing, a global industry generating tens of billions of dollars annually, are the residue of a 5,000-year working relationship. Cities designed around horses, wide boulevards for carriages, dispersed neighborhoods connected by horse-drawn transit still shape the urban geography of places that replaced horses with automobiles a century ago. The language is full of it. We measure engine power in horsepower. We describe determination as horsepower. The phrase holding the reins still means control. The horse gave human civilization its scale of effort, its measure of speed, its vocabulary of power, before it was replaced by machines that could do everything it did, faster. The machines inherited the metaphors. The horses kept the races. The horse's departure from economic utility did not happen uniformly. In the mechanized agriculture of North America and Europe, the tractor arrived quickly and decisively. In the mountainous terrain of Central Asia, the Andes, and parts of Eastern Europe, working horses persisted through the 20th century because the terrain did not suit mechanized alternatives. In Mongolia, the horse-based pastoral economy that has existed for 5,000 years is still operating, still organized around the management and riding of horses, still producing the fermented mare's milk that has been a dietary staple of the steppe for millennia. The replacement of the horse by the machine is a story about wealthy, flat, well-capitalized places. It is not a universal story. Chapter 11. The Fruit Fly. The insect that unlocked the genome. Room 613. In 1908, a young biologist named Thomas Hunt Morgan set up a laboratory at Columbia University that would become, within a decade, the most productive room in the history of genetics. Room 613, later known simply as the Fly Room, contained 8 desks, 4 benches, and tens of thousands of milk bottles filled with rotting bananas and the flies feeding on them. The smell was reportedly extraordinary. The science was unprecedented. Morgan chose Drosophila melanogaster, the common fruit fly, not because it was elegant or charismatic, but because it was cheap, fast, and cooperative. A fruit fly reaches sexual maturity in 2 weeks. A female lays 400 eggs per batch. In the time it took to run a single-generation experiment with mice, a fly experiment could produce 100 generations. Morgan and his students could test hypotheses in months that would have taken decades with other organisms. Within 3 years of setting up the Fly Room, Morgan had discovered sex-linked inheritance, confirmed the chromosomal theory of heredity, and begun mapping genes to specific locations on chromosomes, work that would eventually earn him the Nobel Prize in Physiology or Medicine in 1933. The basic architecture of modern genetics was built in a room that smelled of rotting fruit. The fly's gifts. Drosophila melanogaster has been the subject of more genetic research than almost any other organism on Earth. It has 4 pairs of chromosomes, a fully sequenced genome of approximately 14,000 genes, and genetic tools developed over a century of research that allow biologists to manipulate its biology with precision impossible in most other organisms. Roughly 75% of known human disease genes have a recognizable counterpart in the fruit fly genome. What a drug does to a fly's nervous system often predicts what it will do to a human's. The fly's contributions to medicine are difficult to overstate. Understanding of how genes control development, how a fertilized egg becomes an organism with specific body parts in specific locations, came primarily from Drosophila research. The Hox genes that control body plan in all animals, including humans, were first characterized in flies. Insights into how neurons work, how aging is regulated at the molecular level, how cancer develops from normal cell division all have deep roots in fly genetics. Roughly 75% of known human disease genes have a recognizable counterpart in the fruit fly genome. The room that smelled of rotting bananas turned out to be the foundation of modern medicine. Jonathan Weiner, Time, Love, Memory, 1999. The billion-dollar insect. The pharmaceutical industry has invested billions of dollars in fly research, not because drug companies are interested in flies, but because the fly is the fastest, cheapest way to test ideas before moving them into more expensive animal models. A fly experiment costs a fraction of what a mouse experiment costs, runs in weeks rather than months, and produces statistically robust results from population sizes that would be logistically impossible with any vertebrate. The fly is, in economic terms, the most efficient experimental organism in biology. This efficiency has compounded over time. The tools developed to study flies, genetic crosses, chromosomal mapping, transgenic manipulation, were adapted and extended to other organisms, including eventually humans. The Human Genome Project drew on techniques developed in the Drosophila Genome Project that preceded it. The CRISPR gene editing technology that has transformed medicine was tested and refined first in cells before moving to flies and mice. The fly did not create these tools alone, but it was the organism that made them economically viable to develop. Still in the bottles. More than a century after Morgan set up Room 613, fruit flies are still the workhorses of biology. Thousands of laboratories worldwide maintain fly stocks, specific genetic variants, preserved in bottles, kept at precisely controlled temperatures, representing the accumulated experimental capital of a century of research. The fly is now used to model Alzheimer's disease, Parkinson's disease, diabetes, obesity, addiction, and the basic mechanisms of aging. Every model contributes to understanding that eventually reaches human patients. The fruit fly does not know it has been the central actor in one of the most consequential scientific enterprises in human history. It knows only that the bottle contains food, that 2 weeks is a lifetime, and that the next generation is already hatching. This combination of ignorance and productivity is, in biology, almost perfect. The ethical calculus of using fruit flies in research is straightforward compared to the use of vertebrates. The fly has no capacity for suffering that we can detect or meaningfully compare to vertebrate pain. This simplicity is one reason the fly is preferred wherever it can substitute for a mouse or rat. The regulatory frameworks governing animal research impose far fewer restrictions on Drosophila experiments than on vertebrate ones, reducing cost, paperwork, and the ethical weight that researchers carry when working with animals whose suffering is more legible. The fly's cognitive simplicity, which limits what it can tell us about cognition, is simultaneously the source of its ethical convenience. Chapter 12. The pig. The animal that ate our garbage and fed our armies. The perfect soldier's companion. The pig has one overwhelming advantage over every other domestic food animal: it will eat anything. Grain, kitchen scraps, acorns, roots, dead fish, spoiled vegetables, human waste. The pig processes all of it into high-quality protein with an efficiency that no ruminant can match. This is not an accident of evolution. The pig is an omnivore designed by millions of years of natural selection to thrive in the margins of other animals' ecologies, consuming what others cannot or will not eat. For armies, this made the pig uniquely valuable. A herd of pigs could be driven on campaign and fed from whatever the landscape provided or whatever the army discarded. Roman legions traveled with pigs. Medieval armies drove them. The Spanish conquistadors, the same expeditions that introduced disease to the Americas, also introduced pigs, which multiplied on their own wherever they were left and provided food security for subsequent expeditions. Hernando de Soto brought 13 pigs to Florida in 1539. By the time his expedition ended 3 years later, the herd had grown to over 700. Salt pork and the Age of Exploration. The Age of Exploration ran on salted pork. Preserved in brine, packed into barrels, storable for months without refrigeration, salt pork was the primary protein source on long ocean voyages from the 15th century through the 19th. The caloric density and shelf stability of salted pig products, pork, bacon, lard, made distances possible that would have been logistically unachievable with any other protein source. The geography of European exploration was shaped by where you could resupply with pigs. Portuguese explorers established breeding colonies of pigs on uninhabited Atlantic islands, the Azores, Madeira, the Cape Verde Islands, specifically as way stations where ships could take on fresh or salted meat. The pattern was repeated across every ocean. When James Cook circumnavigated the globe, he left pigs on Pacific islands as a food source for future voyages. The pig preceded human settlement on many of the Pacific's inhabited islands. It arrived as logistics infrastructure and stayed as civilization. De Soto brought 13 pigs to Florida in 1539. By the time his expedition ended 3 years later, the herd had grown to over 700. The pig did not need supply lines. It was the supply line. Mark Essig, Lesser Beasts, A Snout-to-Tail History of the Humble Pig, 2015. The pig and the city. In the early 19th century, New York City's primary sanitation system was its pigs. An estimated 20,000 feral and semi-feral pigs roamed Manhattan, consuming the food waste, garbage, and organic debris that accumulated in streets without municipal collection. The pigs were tolerated and even depended upon because the alternative, allowing organic waste to accumulate without processors, was worse. The poor, particularly recent immigrants in Lower Manhattan, kept pigs as both sanitation workers and food security insurance. When the city attempted to remove the pigs in the 1840s as part of a broader sanitary reform movement, the response from the communities that depended on them was resistance amounting to riots. The Piggery War of 1859, a genuine conflict over the forced removal of pig farms from the Upper West Side, illustrates how central the animal was to the urban economy of the time. The city eventually prevailed. The pigs were gone from Manhattan streets by the Civil War. What replaced them was a municipal sanitation system that cost far more and worked, for most of the century, considerably worse. Inside the modern pig. The pig's anatomy is closer to human anatomy than that of almost any other animal. The pig's cardiovascular system, digestive system, and skin are similar enough to our own that pig heart valves have been used in human cardiac surgery since the 1960s. Porcine insulin was the primary treatment for diabetes before synthetic insulin became available. Current research involves growing human-compatible organs in genetically modified pigs, a technology that could, if successful, eliminate the shortage of transplant organs that kills tens of thousands of people annually. The animal that ate our garbage, marched with our armies, and cleaned our streets may yet save our lives. The pig's utility to human civilization has always outrun our understanding of it. That pattern appears to be continuing. The pig's proximity to humans over 10,000 years of shared settlement has also produced pharmacological consequences that run in the other direction. Pigs are used in the development and testing of drugs and surgical techniques specifically because their organ systems so closely mirror ours. Skin grafting techniques developed in pig models have been used to treat burn victims. Pig intestinal tissue is used to manufacture the heparin that prevents blood clotting during surgery. The relationship between the pig and human medicine is bidirectional. We give pigs our diseases, and pigs give us the tools to treat them. The research pipeline continues. Scientists are working to edit pig genomes to remove the retroviruses embedded in pig DNA, a necessary step before pig organs can be safely transplanted into humans at scale. The first pig-to-human kidney transplant in a living patient was performed in 2024. The animal that followed armies and cleaned cities is now being modified, at the genetic level, to provide human beings with replacement organs. Its usefulness to our species, 10,000 years in, is still expanding. Chapter 13. The bee. The invisible engine of agriculture. The third of everything. 1 in 3 bites of food consumed by humans depends on bee pollination. This is not a figure invented by environmental advocates. It is the result of decades of agricultural research that has systematically documented which crops require or benefit from animal pollination, and which pollinators do the work. The answer, for most flowering crops, is bees, wild bees, managed honeybees, and the hundreds of solitary bee species whose contributions are less well quantified but equally real. The honeybee Apis mellifera, native to Africa and the Middle East, now present on every inhabited continent, is the most commercially managed pollinator in the world. In the United States alone, approximately 2.7 million managed honeybee colonies are transported each year by truck to pollinate specific crops at specific times. The almond industry in California, producing 80% of the world's almonds, requires approximately 1.8 million colonies at bloom time, more bees than exist permanently in the state, which must be imported from as far as Florida and Maine. Without managed pollination, the almond crop does not exist. The colony's architecture. A honeybee colony is not a collection of individual animals. It is, in the terminology of biology, A superorganism, a collective entity in which the behaviors of individual bees are so tightly coordinated that the colony itself functions as a single metabolic unit. The queen does not command, she lays eggs. The workers, all female, all reproductively suppressed, make every operational decision through mechanisms that are still not fully understood. The waggle dance, decoded by Carl von Frisch in research that earned him the Nobel Prize in 1973, is the colony's communication system for food location. A returning forager dances a figure 8 on the vertical face of a comb, encoding in the angle and duration of the dance the direction and distance of a food source relative to the position of the sun. Other workers read the dance, adjust for the sun's movement since the dancer left the source, and fly directly to food they have never seen. The precision of this system, tested repeatedly in controlled experiments, is extraordinary. It is, arguably, the most sophisticated non-human communication system we have documented. 1 in 3 bites of food depends on bee pollination. The agricultural system that feeds 8 billion people was built around a service that bees provided for nothing. The cost of that service is now being calculated. The number is very large. Hannah Nordhaus, The Beekeeper's Lament, 2011. The collapse. In the winter of 2006 and 2007, American beekeepers began reporting losses of 30 to 90% of their colonies' hives that simply emptied, with no dead bees present, as if the workers had flown away and never returned. Colony collapse disorder, as it was named, had no obvious single cause. Subsequent research implicated a convergence of stressors, Varroa mites that had spread globally from Asian honeybees and attacked the immune systems of European lineage Apis mellifera, neonicotinoid pesticides that impaired navigation and memory in foragers, fungal pathogens, habitat loss that reduced floral diversity, and the cumulative stress of industrial beekeeping itself, which moved colonies thousands of miles per year and fed them on high-fructose corn syrup between pollination. Contracts. Colony collapse disorder has not ended. Managed honeybee colony losses in the United States have averaged between 30 and 40% per year since 2006, losses that beekeepers compensate for by splitting surviving colonies, a process that works but requires constant effort and expense. The agricultural system that depends on honeybee pollination has, in effect, been running on a treadmill, replacing what it loses at a rate that barely keeps pace with the losses. What happens without them? A world without managed pollinators would not be a world without food. Grain crops, wheat, corn, rice are wind-pollinated and would continue. What would disappear, or become far more expensive, is the nutritional diversity that bee-pollinated crops provide: fruits, vegetables, nuts, and the animal products derived from animals fed on pollinator-dependent forage crops. Nutritional scientists have estimated that a diet without bee-pollinated crops would be adequate in calories but severely deficient in the vitamins and micronutrients that come from produce. It would, in other words, be the diet of poverty everywhere. The bee did not ask to become essential. It became essential because humans built an agricultural system around the service it provided for free. The cost of that service, now that it is becoming scarce, is finally being calculated. The number is very large. The effort to replace pollinators mechanically has attracted significant investment. Researchers in Japan and the United States have developed robotic pollinators, small drones that carry pollen on bristled surfaces and transfer it between flowers. In controlled greenhouse conditions, these devices work. In open agricultural fields, at the scale required to service the almond groves of California or the apple orchards of Washington state, they do not yet work economically. A bee is the product of 50 million years of coevolution with flowering plants. The engineering required to replicate its efficiency, at cost, at the scale of global agriculture, is not a problem that current technology is close to solving. Chapter 14. The Rat. The stowaway that conquered the world. The ship's passenger. The black rat Rattus rattus did not choose to colonize the world. It was carried. It stowed away on the grain ships of Phoenician and Greek traders in the ancient Mediterranean, traveled with Roman legions, and spread with the expansion of European maritime trade to every port on every continent that could support a population. The black rat is now found on all 7 continents. It arrived on every one of them as a passenger, not a migrant. This distinction matters. The rat did not outcompete local species in any evolutionary sense. It succeeded because it lived inside human supply chains, in the granaries, the holds, the warehouses that concentrate food and create the ecological niche the rat was built to exploit. Where humans went, food storage followed. Where food storage went, rats followed. The map of the rat is, almost exactly, the map of human trade. The plague vector. The black rat's most consequential moment in human history was the Black Death, but as discussed in the chapter on the flea, the rat was not the vector. It was the reservoir. Yersinia pestis lived in rat bloodstreams without, typically, killing the rats. When rats died in large numbers, as they did at the start of each plague outbreak, their fleas abandoned them and transferred to available warm bodies, including humans. The rat was the tank that kept the bacterium alive, the flea was the weapon that deployed it. This relationship between rat and plague has a modern dimension. The brown rat Rattus norvegicus, which largely displaced the black rat in Europe and North America by the 18th century, is a more effective host for a wider range of pathogens. Brown rats carry leptospirosis, hantavirus, ratbite fever, and salmonella, among others. In cities where rat populations are poorly controlled, these diseases create significant public health burdens. New York City's rat population is estimated at approximately 2 million animals. A 2023 study found that a substantial proportion were carrying antibiotic-resistant strains of pathogens. The laboratory rat is saving our lives from disease. The urban rat is spreading disease through our cities. These are, biologically, the same animal. The difference is management. Robert Sullivan, Rats, Observations on the History and Habitat of the City's Most Unwanted Inhabitants, 2004. The laboratory rat. The story of the rat in human history is not only one of destruction. The same Rattus norvegicus that carries disease through city sores has been the primary subject of biomedical research for over a century. The laboratory rat bred from the brown rat into docile, genetically consistent strains beginning in the 1820s has been used to test virtually every drug now in human use. Its physiological similarity to humans, its rapid reproduction, its tolerance of laboratory conditions, and the accumulated knowledge base built up over decades of research make it irreplaceable in preclinical medicine. The polio vaccine, insulin therapy, chemotherapy, antihypertensive drugs, and antidepressants were all developed and tested in rats before they reached humans. The rat that spreads disease in our cities is, in the controlled conditions of a laboratory, saving our lives from disease. These are, biologically, the same animal. The difference is management. The laboratory rat is controlled, standardized, and cared for. The urban rat is free, variable, and competing with us for space and food. Our relationship with it is always one or the other. The rat that finds mines. In Tanzania and Mozambique, African giant pouched rats, Chrysetomys ansor, related to but distinct from the common rat, are trained by an organization called a popo to detect landmines by scent. Each rat can screen roughly 2,000 square feet in 30 minutes, a task that would take a human demoner with metal detecting equipment several days. The rats are too light to trigger the mines. They are trained on a click reward system and indicate a find by scratching the ground. They are then moved to another patch and the process continues. APOPO's rats have cleared millions of square meters of land in sub-Saharan Africa and Southeast Asia, returning territory to agricultural use and safe habitation. The same olfactory sensitivity that allows a rat to find food in a city's walls allows it, with training, to find explosives in a field. The stowaway that conquered the world is still surprising us. The Apopo program illustrates something that professional animal trainers have known for decades and that the general public consistently underestimates. The gap between what an animal can be trained to do and what we assume it is capable of is enormous. Rats were considered vermin. They were not considered diagnostic medical equipment. It required a specific combination of scientific curiosity and practical desperation, in this case, the need to clear millions of landmines from post-conflict countries with minimal resources, to ask whether a rat's nose could do what no machine could do cheaply. The question turned out to have a yes answer. The question was not asked for most of the rat's history alongside humans. Chapter 15. The Octopus. The alien intelligence in our oceans. The problem of the octopus. If you wanted to design an intelligent animal from scratch, you would not design an octopus. You would start with a central brain, protected in a skull, connected to a body through a spinal cord, the architecture that evolution has used repeatedly in vertebrates, from fish to mammals, because it works. The octopus has done something entirely different. It has distributed most of its neurons throughout its 8 arms, so that each arm has its own local processing center and can act, to a significant degree, independently of the central brain. 2/3 of the octopus's neurons are not in its brain. This architecture produces behaviors that have surprised and confused researchers for decades. An octopus can solve a puzzle, remember the solution, and apply it to novel versions of the same problem, evidence of general learning ability, not just conditioned response. It can recognize individual human faces and behave differently toward different humans, a cognitive capability that requires abstract representation of identity. It uses tools. Specific octopus populations have been documented carrying coconut shells across the ocean floor and assembling them into portable shelters. 9 brains and 3 hearts. The octopus has 9 brains, 1 central and 1 in each arm, 3 hearts, and blue blood containing hemocyanin, a copper-based oxygen carrier that works more efficiently than hemoglobin in cold, low-oxygen environments. Its skin contains chromatophores, iridophores, and papillae, 3 independent systems for controlling color, iridescence, and texture simultaneously. An octopus can change its appearance from smooth and pale to spiky and dark in a fraction of a second. What makes this remarkable is not just the capability but its independence from the central nervous system. The octopus's skin thinks. In a limited sense, it responds to local light stimuli through photoreceptors embedded in the chromatophores themselves, without waiting for instructions from the central brain. The octopus changes color while unconscious. Its skin is doing something the brain is not directing. The independence of the octopus's arms from its central brain has been tested in controlled experiments that produce unsettling results. An octopus arm, severed from the body, will continue to respond to stimuli for up to an hour, reaching toward food, recoiling from noxious stimuli, performing the coordinated movements that in an intact animal would require instruction from the central brain. The arm is not following orders. It is making local decisions with the neural tissue it contains. This distributed architecture means that the octopus, in a meaningful sense, is not one decision-making system. It is 9 partially autonomous systems that happen to be physically connected. The octopus evolved intelligence completely independently of vertebrates, starting from a common ancestor that had no brain 750 million years ago. Intelligence may be less a single improbable accident than a reliable outcome wherever the conditions favor it. Cy Montgomery, The Soul of an Octopus, 2015. Convergent intelligence. The last common ancestor of octopuses and vertebrates lived approximately 750 million years ago, a simple, flat worm with rudimentary sensory cells and no brain recognizable as such. Everything that an octopus and a human share in terms of cognitive architecture, the ability to learn, to remember, to recognize individuals, to use tools, to solve problems, evolved completely independently, in lineages that split before any of these capabilities existed. This is the concept of convergent evolution applied to intelligence, the same outcome reached by completely different paths. The implication is significant. If intelligence evolved twice, in lineages separated by 750 million years of independent evolution, it may be a more stable evolutionary outcome than we thought, something that emerges reliably when the ecological conditions favor it, rather than a single improbable accident that happened once in the vertebrate line. The practical consequence of convergent intelligence for biology is significant. If intelligence evolved twice in radically different lineages, the conditions that produce it may be more common than we assumed. Researchers studying animal cognition have, in the last 2 decades, found evidence of sophisticated problem-solving and social learning in crows, parrots, cleaner wrasfish, and bumblebees. Intelligence appears to be less a single evolutionary achievement than a family of adaptive solutions to the problem of living in complex environments. The octopus is the most extreme case, the furthest from vertebrate cognition while still being recognizably intelligent, and for that reason, the most useful to study. What happens when they die? The octopus lives fast and dies young. Most species live 1 to 2 years. After mating, females guard their eggs continuously, fanning them with water to oxygenate them, refusing to eat, deteriorating rapidly. By the time the eggs hatch, the mother is typically dead. Males often die within weeks of mating. There is no parental care, no transmission of learned behavior across generations. Whatever an octopus learns in its short life ends with it. This fact makes the octopus's demonstrated intelligence even more extraordinary. It cannot inherit knowledge from its parents. It cannot teach its offspring. Every octopus must reinvent its understanding of the world from scratch. That an animal operating under these constraints can solve mazes, use tools, and recognize human faces is a reminder that intelligence does not require accumulation. It requires only time, curiosity, and a world complex enough to reward investigation. Chapter 16. The cow. The animal whose milk rewired human genetics. A mutation that spread across a continent. Approximately 7,500 years ago, somewhere in the region of what is now Hungary or the Northern Balkans, a human being was born with a genetic mutation that allowed them to digest milk as an adult. In all mammals, the ability to digest lactose, the sugar in milk, diminishes sharply after weaning, when the gene for lactase enzyme production is switched off. In this individual, a single letter change in the DNA near the lactase gene kept it switched on for life. This mutation, lactase persistence, is now present in approximately 35% of the global human population. In populations of Northern European descent, the frequency is over 90%. Its spread across Europe over the following millennia was among the fastest genetic sweeps ever documented in human evolution. The selective pressure that drove it was the cow. The ecological bargain. The domestication of the aurochs, the wild ancestor of domestic cattle, began approximately 10,000 years ago in the Near East and separately in South Asia. By 7,000 years ago, cattle herding was established across much of Europe. What milk consumption offered in this environment was caloric insurance, a renewable resource, produced daily by a living animal, with roughly the same caloric density as meat but available without killing the animal. In environments where agriculture was unreliable, Northern Europe, with its unpredictable growing seasons, the steppes, where grain cultivation was marginal, the ability to extract calories from milk rather than only from slaughter gave herding populations a survival advantage that was real, measurable, and heritable. The people who could drink milk survived hard winters that killed those who could not. Their children were more likely to carry the mutation. Over 7,500 years, a mutation that was initially rare became almost universal in certain populations. Lactase persistence spread across Europe faster than almost any other genetic mutation ever documented. The cow did not just feed civilization. It rewrote the genome of the civilization that kept it. Mark Thomas, University College London, Genetic Study, 2007. The animal that built economies. The cow's contributions to civilization extend far beyond milk. Cattle provided traction for ploughing, the muscle that broke the heavy clay soils of Northern Europe and made large-scale agriculture possible there. Cattle hides became leather, the medieval world's most versatile industrial material, used for shoes, armor, book bindings, harnesses, and containers of every description. Cattle bones were rendered into glue, fertilizer, and buttons. In pre-industrial economies, A cow was a walking factory whose outputs ranged from food and fiber to fuel and raw materials. Cattle manure, returned to the soil, was the primary source of agricultural fertility in most of the world before synthetic fertilizers. The nitrogen cycle that sustained crop yields for millennia ran through the cow's digestive system. The Green Revolution of the 20th century replaced this system with synthetic nitrogen produced from natural gas, but the revolution itself depended on decades of plant breeding carried out on the agricultural foundation that cattle had built. The sacred status of cattle in Hindu tradition is sometimes treated as puzzling from a Western economic perspective. Why protect an animal so useful as food? The answer, seen from subsistence agricultural economics, is clear. A cow that is alive and working provides traction, manure, milk, and calves continuously for 15 years. Slaughtered, it provides one meal. In a farming economy where mechanized alternatives do not exist, the prohibition on cow slaughter is not sentiment. It is rational resource management. The animal's living value far exceeds its food value, and religious sanction provides the enforcement mechanism that market incentives, in conditions of scarcity, might not reliably sustain. The methane problem. The cow's digestive system is, by the standards of modern atmospheric chemistry, a serious problem. Cattle are ruminants. Their four-chambered stomachs contain microbes that ferment cellulose into usable nutrients, producing methane as a byproduct. Each cow produces approximately 200 to 500 liters of methane per day through belching and flatulence. With approximately 940 million cattle on Earth, the cumulative methane output is roughly 14.5% of global greenhouse gas emissions, more than the entire transportation sector. The animal that rewrote human genetics, built agricultural economies, and fed civilizations is now, at current scale, a significant driver of the climate change threatening those civilizations. This is not an argument against cattle. It is an argument about the difference between a domesticated animal managed at ecological scale and a domesticated animal managed as industrial machinery. The cow did not create this problem. 8 billion humans creating demand for cheap beef did. The geography of cattle-related emissions follows the geography of beef consumption, which follows the geography of income. The average American consumes roughly 80 pounds of beef per year. The average Indian consumes approximately 7 pounds. The methane produced by cattle is concentrated in North America, Brazil, and Australia, the wealthiest beef-consuming economies. The climate consequences are distributed globally, with the heaviest impacts falling on tropical and low-income regions that consume the least beef. The political economics of changing cattle production are correspondingly difficult. The costs of change fall on wealthy consumers who can absorb them, but the incentive to change requires those consumers to care about consequences experienced by others. Chapter 17. The Wolf. The Predator that Became a Partner. The First Domestication. The dog is a wolf. This is not a metaphor or a loose analogy. Every domestic dog, from the Chihuahua to the Great Dane, from the racing greyhound to the truffle-hunting Lagotto Romagnolo, is a descendant of the grey wolf, Canis lupus, with whom it shares 99.9% of its DNA. The domestication of the wolf was the first domestication of any animal, preceding cattle, sheep, pigs, and horses by thousands of years, and it produced an animal so transformed by its relationship with humans that distinguishing the original species from its domestic derivative now requires genetic analysis. When, exactly, wolves became dogs is disputed. The best current estimate, based on ancient DNA analysis, is somewhere between 15,000 and 40,000 years ago, before agriculture, before permanent settlements, before any of the other domestications that define civilization. The wolf was domesticated by hunter-gatherers, for purposes that were not about herding, ploughing, or meat production, but about something that hunter-gatherers needed, a partner in the hunt. The initial relationship between wolves and humans was probably opportunistic rather than intentional. Wolves that were less fearful of humans would have followed hunting groups at a distance, scavenging the carcasses left behind. Humans who tolerated these wolves gained early warning of approaching predators and prey. The relationship was mutualistic before it was deliberate, each species getting something from the other's presence without consciously choosing partnership. The domestication that produced the dog was not an invention. It was a formal recognition of something that had been developing, generation by generation, for perhaps thousands of years before anyone thought to name it. What the wolf did for us. A wolf's nose is, by most estimates, approximately 100,000 times more sensitive than a human nose. Its hearing range extends well beyond the human range in both directions. It can run at 35 miles per hour for extended periods and sprint to 45. In a world where humans hunted large prey on foot, with hand-thrown weapons, the wolf's sensory and physical capabilities filled a gap in the human toolkit that no human technology of the era could replicate. The partnership that developed wolves following human camps for scraps, humans tolerating wolves that were useful rather than dangerous, was not a conscious design decision. It was an ecological relationship that developed over generations into something more structured. The wolves that were least aggressive toward humans survived in human proximity. The humans who worked with rather than against the wolves that were near them were more successful hunters. Both species, over thousands of years, became increasingly dependent on the partnership. The reintroduction of wolves to Yellowstone changed elk behavior, revegetated riverbanks, narrowed rivers, and altered the park's physical geography. A predator's return remade a landscape. The wolf did not touch the rivers. It changed the fear. William Ripple and Robert Bechter, Yellowstone Trophic Cascade Research, 2012. The wolves that stayed outside. Not all wolves became dogs. The wolf populations that did not associate with humans remained wolves, hunted, feared, mythologized, and eventually nearly exterminated across most of Europe and North America. The gray wolf was effectively eliminated from the continental United States by the 1970s, a result of deliberate predator control programs that treated wolves as threats to livestock rather than as the keystone predators that structured the ecosystems they inhabited. The reintroduction of wolves to Yellowstone National Park in 1995 produced results that ecologists still use as the canonical example of trophic cascade. Within years of the wolves' return, elk behavior changed. Instead of grazing freely in valleys and riverbanks, elk avoided open areas where wolves could see them. The riverbanks, no longer overgrazed, revegetated. The roots held the soil. The rivers narrowed and deepened. Beaver populations increased. Songbird populations increased. The physical geography of the park began to change because a predator had returned. Two wolves. The wolf and the dog are the same species in two entirely different relationships with humanity. The dog is beloved, studied, bred for specific emotional and physical traits, housed, and mourned when it dies. The wolf is hunted, poisoned, and politically contested in every country where it still exists. The difference between them is not biology. It is the accident of which wolves, thousands of years ago, were willing to approach human camps and which were not. We have spent 10,000 years learning to love one and fear the other. The one we love has been shaped by that love into something that reflects human emotional needs back at us with extraordinary fidelity. The one we fear has been shaped by that fear into an animal that defines, for better or worse, our relationship with wildness itself. The co-evolutionary dimension of dog domestication is often overlooked. We shaped the wolf into the dog through selective breeding. But the wolf also shaped us. The humans who formed successful bonds with protodogs were likely better hunters, better warned against predators, and better fed than those who did not. They were more likely to survive and pass on their genes, including whatever genetic predispositions made cross-species bonding possible. The capacity for deep emotional connection with an animal of another species, which strikes many observers as a distinctly human quality, may itself be partly a product of 10,000 years of selection pressure from the animal we made. Chapter 18. The chicken. The most numerous bird in Earth's history. Not domesticated for food. There are approximately 33 billion chickens on Earth at any given moment, roughly 4 for every human being. They are by far the most numerous bird species in the history of the planet, and they got there through a domestication that had nothing to do with eating them. The red jungle fowl of Southeast Asia, Gallus gallus, ancestor of all domestic chickens, was first domesticated approximately 8,000 years ago in what is now Thailand and Vietnam. The primary purpose was cockfighting. This is not a footnote. Archaeological evidence from the earliest chicken-keeping sites in Southeast Asia and China shows no significant consumption of chicken eggs or meat. What the evidence shows is roosters selected for fighting traits, large spurs, aggressive temperament, distinctive appearance. The chicken entered human civilization as a gambling instrument and a ritual object, not as a food source. It was thousands of years before the bird's extraordinary productivity as an egg and meat producer was systematically exploited. The cockfighting origin of chicken domestication has a specific implication for how the bird spread across the ancient world. Fighting birds had cultural and religious value that food animals did not. They were exchanged as diplomatic gifts, used in divination rituals, and maintained in temple precincts across South and Southeast Asia. The rooster's crow at dawn acquired spiritual meaning in cultures from China to Greece, the signal of day's return, associated in many traditions with vigilance and courage. The chicken entered the symbolic vocabulary of civilization thousands of years before it became a protein source. It arrived as a status object and a religious instrument. It stayed for the eggs. The egg that traveled the world. The chicken's spread from Southeast Asia followed two routes. The overland route moved westward through South Asia, the Middle East, and into Europe, carried by the same networks that moved silk, spices, and bronze. The maritime route moved eastward across the Pacific to the Americas. DNA evidence from chicken bones found at archaeological sites in Chile, dating to approximately 1300 CE, establishes that Polynesian navigators brought chickens to South America before European contact. The chicken crossed the Pacific on an outrigger canoe. By the time the Spanish arrived in the Americas, chickens were already there. By the time Europeans settled in Africa, chickens were already there. The bird that is now the world's most consumed meat was a global traveler before the age of global travel, spread by the same human mobility that has always carried domestic animals and cultivated plants across the world's barriers. Future geologists examining the sedimentary record will find a distinct layer dominated by chicken bones more than any other vertebrate in the history of the planet. The Anthropocene may be marked by a bird domesticated for cockfighting. Caris Bennett et al., The Broiler Chicken as a Signal of a Human Reconfigured Biosphere, Royal Society Open Science, 2018. The Broiler Revolution. The chicken of 1950 and the chicken of 2024 are nominally the same species but practically different animals. The modern broiler chicken, bred specifically for meat production, reaches market weight in approximately 47 days on roughly 4 pounds of feed, compared to the 15 weeks and 10 pounds of feed required by the chickens of the mid-20th century. Its breast muscles are so large relative to its skeleton that it cannot fly and, in some breeds, cannot stand comfortably. It has been redesigned, through selective breeding, as a protein conversion machine. The consequences of this redesign are both economic and ethical. Economically, it has made chicken the cheapest animal protein available to most of the world, genuinely improving nutrition for low-income populations globally. Ethically, it has created an animal whose body cannot support the life it is built to lead, a bird that experiences chronic pain, respiratory difficulty, and cardiovascular stress as a consequence of the traits selected for its productivity. The chicken that fed the world was built to suffer for it. The geography of chicken consumption tracks the industrialization of its production. Americans ate roughly 10 pounds of chicken per person per year in 1950 and approximately 100 pounds today. The inflation-adjusted price of chicken fell roughly 80% over the same period, as efficiency improvements in broiler production outpaced every other sector of agriculture. The democratization of animal protein that resulted has genuine nutritional significance for lower-income populations worldwide. The conditions under which that protein is produced, confinement facilities housing tens of thousands of birds, antibiotic use that contributes to resistance, breeding programs that produce animals in chronic discomfort represent a cost that is distributed differently than the benefit. The chicken in the rock record. Future geologists examining the sedimentary record of the present era will find a distinct layer dominated by chicken bones, in more places, than any other vertebrate animal in the history of the planet. Researchers have proposed the modern broiler chicken as a potential marker species for the Anthropocene, the geological epoch defined by human influence on the Earth systems. If any single organism signals the scale of human dominion over the biological world, it may be this bird, domesticated for gambling, bred for efficiency, and now present in its billions in every corner of the Earth. The red junglefowl still exists in the forests of Southeast Asia, living roughly as it did 10,000 years ago, secretive, fast, magnificently plumed, and almost entirely unaware of what its domesticated descendants have become. Chapter 19. The Leech. The doctor's most trusted instrument. 2,000 years of medicine. For most of recorded medical history, the leech was a physician's primary tool. Hirudo medicinalis, the European medicinal leech, was applied to patients suffering from fever, infection, inflammation, headache, mental illness, and virtually every other condition that medicine recognized. The theoretical basis was humoral theory. Disease was caused by imbalance of the four humors, and bloodletting, removing excess blood from the body, was the primary treatment. The leech was the cleanest, most controllable method of bloodletting available. At the peak of leech medicine in the early 19th century, France alone was importing approximately 42 million leeches per year. Leech dealers were a recognized medical supply profession. Leech ponds were managed as agricultural resources. When Napoleon's Surgeon General François Broussais concluded that virtually all disease was caused by inflammation and could be treated by bloodletting, French leech imports rose to 57 million in 1833. The European leech population was being hunted toward extinction in service of a medical theory that was, as we now understand, largely incorrect. The scale of leech use at its peak staggers the modern imagination. In Parisian hospitals during the 1820s, patients might receive anywhere from 6 to 50 leeches per treatment session. The demand was so insatiable that professional leech collectors waded into ponds and marshes, allowing leeches to attach to their bare legs, then pulled them off to sell, a practice that produced significant wounds and was eventually banned in several European countries. The medicinal leech, Hirudo medicinalis, was being collected faster than it could reproduce. By the 1840s, France was importing leeches from Hungary, Poland, and Russia to meet demand that domestic populations could no longer supply. The broader consequences of humoral medicine's scale of practice were significant. Patients weakened by disease were frequently further weakened by the bloodletting intended to cure them. George Washington's death in 1799 is a plausible case. He developed a throat infection, was treated with multiple rounds of bloodletting totaling approximately 40% of his blood volume over 12 hours, and died. Whether the infection alone would have killed him is unknowable. That the treatment contributed to his death is the assessment of most modern physicians who have reviewed the record. The chemistry of the bite. The leech's medical value was not zero, even under false premises. What a leech injects when it bites contains a pharmacological toolkit of surprising sophistication. Hirudin, isolated from leech saliva in 1884, is the most potent natural inhibitor of thrombin, the enzyme that triggers blood clotting, ever discovered. Histamine expands blood vessels and increases blood flow. Hyaluronidase breaks down the tissue matrix, allowing other compounds to penetrate more deeply. The leech has been delivering anti-clotting, anti-inflammatory medicine for 2,000 years. The physicians applying it thought they were removing bad blood. They were also providing genuine biochemical treatment. Leech saliva contains the most potent natural inhibitor of blood clotting ever discovered. Physicians who applied leeches for 2,000 years thought they were removing bad blood. They were also delivering genuine anticoagulant therapy. They were not entirely wrong. Kenneth Muir, Leeches in Microsurgery, British Journal of Plastic Surgery, 1990. The Return. Leech therapy did not survive the germ theory of disease. By the 1870s, as Pasteur and Lister established that disease was caused by microorganisms rather than humoral imbalance, bloodletting lost its theoretical foundation and rapidly fell out of use. The leech disappeared from mainstream medicine for almost exactly a century. In 1985, surgeons at Harvard Medical School were struggling with a recurring problem in microsurgery. Patients who had digits, ears, or flaps of tissue successfully reattached would sometimes suffer venous congestion, the arterial blood supply restored but the venous drainage insufficient, causing the reattached tissue to engorge with blood and die. They applied medicinal leeches to the congested tissue. The leeches drained the excess blood. The tissue survived. The technique became standard practice in reconstructive surgery worldwide. What the leech teaches. Medicinal leeches are today a regulated pharmaceutical product in the United States, Europe, and most developed medical systems. Biopharmaceutical companies culture them in sterile conditions, provide them to hospitals on prescription, and have developed synthetic versions of hirudin, lepirudin, bivaludin that are now standard anticoagulants used during cardiac surgery and in the treatment of certain clotting disorders. The leech's career in medicine is a compressed history of how medical knowledge actually progresses, through observation, through wrong theory, through correct observation of real effects that wrong theory cannot explain, and eventually through the chemistry that reveals why what was observed was real. Physicians who used leeches were not entirely wrong. They were wrong about why they worked, but 2,000 years of clinical observation had identified a real effect. The biochemistry came last. The history of medicine is full of treatments that worked for reasons their practitioners could not explain. Willow bark tea reduced fever because it contains salicylic acid, the basis of aspirin, centuries before anyone understood the chemistry. Specific mold applied to wounds suppressed infection because it contained penicillin precursors. Clinical observation preceded biochemical explanation in virtually every major therapeutic advance. The leech is the most compressed version of this pattern. 2,000 years of observation correctly identified a real effect, the theoretical framework explaining that effect was entirely wrong, and the correct framework arrived last. The physicians who used leeches were not entirely mistaken. They were mistaken about why they worked, which is a different kind of error and a more forgivable one. Chapter 20. The Pearl Oyster. The gem that changed how we think about value. The price of a pearl. Before Mosquito, before cultured pearls, the finest natural pearls were among the most valuable objects on Earth. Julius Caesar's invasion of Britain in 55 BCE was motivated in part by reports of British freshwater pearls, which he distributed as gifts to Roman women of status. A pair of pearl earrings owned by Cleopatra was valued by Pliny the Elder at 10 million sesterces, the equivalent of roughly 10 years of Roman legionary pay for thousands of soldiers. The pearl's value was not aesthetic illusion. Producing a fine pearl required a specific oyster, a specific irritant, a specific water temperature, and approximately 5 to 7 years of growth without human intervention. Natural pearls of significant size and luster were genuinely rare. The Persian Gulf and the diving industry. The Persian Gulf, the Bahrain archipelago in particular, was for most of recorded history the world's primary source of fine natural pearls. The diving season lasted 4 months each year. Divers descended without breathing apparatus, equipped only with nose clips and a bag attached to a rope, to depths of up to 40 meters, harvesting oysters by hand and surfacing to breathe before descending again. A skilled diver might make 60 dives per day. The pearl diving industry was organized along lines that closely resembled debt bondage. Divers were advanced money before the season to pay for their equipment and their family's food. The advance was taken from their share of the season's harvest. In poor seasons, the debt exceeded the earnings, and divers returned the following year in deeper debt. The industry employed tens of thousands of people across the Gulf's coastal populations, not because they chose it freely, but because it was the only economy available. In 1929, the same year as the Wall Street crash, the pearl diving industry collapsed. The cause was not the Depression. It was Mosquito. Mikimito's cultured pearl was chemically identical to the natural pearl. The market decided it did not care. An industry that had organized the labor of millions of people for 3,000 years became economically irrelevant in a single decade. Fred Ward, Pearls, 1995. The Man Who Killed the Natural Pearl. Kokichi Mikimoto was a noodle seller's son from Toba, Japan, who became obsessed with the possibility of producing pearls artificially. After 17 years of failed experiments, he succeeded in 1893 in producing the first cultured pearl, an oyster surgically implanted with a nucleus that would stimulate nacre production. By the 1920s, Mikimoto's farms were producing cultured pearls in quantities that overwhelmed the natural pearl market. The social consequences were not small. The pearl diving economies of the Persian Gulf, the pearling industries of the Torres Strait and the Ceylon coast, the freshwater pearl fisheries of Europe and North America all collapsed within a decade as cultured pearls, visually identical to natural pearls, entered the market at a fraction of the price. An industry that had organized the labor and economy of millions of people for thousands of years became economically irrelevant in a generation. The Persian Gulf states that had been built on pearl wealth pivoted, over the following decades, to the oil reserves beneath the same waters their divers had once harvested. What the pearl teaches. The story of the pearl is, at its core, a story about the nature of value. The natural pearl had value because it was rare, because it was produced by chance, because acquiring it required skill and risk. The cultured pearl is, chemically and visually, the same object. The pearl cannot tell the difference. The market, once informed, largely has decided it does not care. The cultured pearl commands a fraction of the natural pearl's price not because it is inferior but because scarcity has been removed. Mikimoto understood this, which is why he spent decades lobbying against the cultured pearl industry he himself had created, arguing that cultured pearls were fake, inauthentic, unworthy of comparison with natural ones. He failed. The market applied its own logic. A beautiful object at a price that millions of people can afford is worth more to more people than a beautiful object that only the wealthy can buy. The pearl oyster, by becoming manageable, became democratic. Whether that represents gain or loss depends on what you thought you were paying for. The pearl's story also illuminates the economics of authenticity. The luxury market that collapsed with Mikimoto's cultured pearl recovered by pivoting to what could not be replicated. The story of the natural pearl, the rarity, the provenance. A natural pearl sold today carries documentation of its origin, its approximate age, its specific oyster species. It sells not for what it is but for what it represents: scarcity, chance, the absence of human control over the outcome. The cultured pearl cannot buy this. No matter how perfect its nacre, it is a managed product. The market for managed perfection and the market for unmanaged rarity are different markets, and the cultured pearl, by demonstrating this, inadvertently created the conditions for natural pearl prices to recover. Chapter 21. The Elephant. The Engineer of Forests and Armies. Hannibal's Blunder. In 218 BCE, the Carthaginian general Hannibal Barca crossed the Alps with 37 war elephants, approximately 90,000 soldiers, and the most ambitious military plan of the ancient world, to invade Italy from the north and force Rome to its knees. The elephants were North African forest elephants, smaller than the African bush elephant, probably similar in size to the Asian elephant, and trained for decades to carry armored platforms from which soldiers could fight. Hannibal's elephants terrified Roman horses at the Battle of the Trebia in December 218 BCE. By the time he reached Italy in spring, most of them were dead, killed by the cold, the terrain, and disease rather than by any Roman weapon. The sole survivor, an elephant named Shuruz, carried Hannibal himself through the Italian campaign. The elephants that had been meant to be the decisive weapon of the war were gone before it properly began. The lesson that military commanders repeatedly failed to learn from Hannibal is that war elephants are more logistically demanding than almost any other military asset and more psychologically fragile. An elephant panicked by wounds or noise will flee, trampling its own forces. The Romans, who had never seen elephants before the First Punic War, quickly learned to respond to elephant charges with noise, fire, and targeted attacks on the animal's feet and trunks. Within a generation of first contact, Roman legions were routing elephant units reliably. The ancient world's most impressive weapon had a surprisingly simple counter: the forest engineers. The elephant's ecological importance is as significant as its historical drama, and far more durable. African bush elephants push over trees, create clearings, dig water holes, and disperse the seeds of hundreds of plant species, including many large-seeded tropical trees whose seeds cannot be dispersed by any smaller animal. Where elephant populations have been removed, the composition of the forest changes. Tree species that depend on elephants for seed dispersal decline. Vegetation structure shifts. Other species that depend on the clearings and water holes elephants create disappear. Ecologists describe this as the elephant's role as a keystone species and mega-gardener, the animal that maintains the structure and composition of the ecosystems it inhabits. In the Congo Basin and across East and Central Africa, the forest as we know it was shaped over millennia by elephant behavior. The trees are where they are, in part, because elephants decided to eat elsewhere. Where elephant populations have been removed, the forest changes. The trees are where they are, in part, because elephants decided to eat elsewhere. The elephant is not just in the forest. It built the forest. Roman Garrost, Elephant Seed Dispersal Studies, 2011. The ivory trade. The demand for ivory elephant tusk, prized for its workability, durability, and luster, has driven the elephant to functional extinction across most of its historical range. Elephants once ranged across North Africa and the Middle East. Both populations were hunted out for ivory and war elephants in antiquity. The 20th century's ivory trade, fed by demand for piano keys, billiard balls, and ornamental objects, killed perhaps half of Africa's elephant population between 1970 and 1990. The 1989 CITES ban on international ivory trade arrested the decline, but illegal poaching continues to reduce populations in Central and West Africa. The calculation that drives poaching is simple: an elephant is worth more dead than alive to the individual who kills it. The calculation that points in the opposite direction, that a living elephant generates more economic value through tourism, ecosystem services, and carbon sequestration than its tusks are worth, is true but requires a time horizon and institutional capacity that poachers and the criminal networks they supply do not have. The memory. Elephants live up to 70 years. Females remain with the group of their birth throughout their lives, accumulating knowledge of water sources, seasonal migration routes, and effective responses to threats. Old matriarchs who have survived drought, poaching pressure, and predators carry knowledge that younger animals lack. Studies have shown that groups led by older matriarchs are more likely to survive drought years and less likely to make dangerous decisions when threatened. When an elephant dies, its group mourns it. They return repeatedly to the bones. They touch them with their trunks. Whether this constitutes grief in any psychological sense we would recognize is contested. What is not contested is that elephants have memory, social bonds, and something that looks from the outside like awareness of death. We have been killing them for piano keys. The gap between what they are and how we have treated them is worth sitting with. The matriarch's role in elephant society has a measurable survival value. Studies conducted during the severe droughts of the 1990s in Amboseli National Park found that groups led by older matriarchs, those with more years of experience navigating drought conditions, showed significantly higher survival rates than those led by younger females. The older matriarchs knew where to find water that younger animals did not. This knowledge, accumulated over decades and transmitted through leadership rather than language, is a form of cultural capital with direct biological consequences. When poachers kill the largest, oldest females, as they preferentially do, because the oldest animals carry the largest tusks, they are not only killing individuals. They are destroying the libraries their groups depended on. Chapter 22. The salmon. The fish that fed the Pacific world. The river as a calendar. For the indigenous nations of the Pacific Northwest, the Chinook, the Nez Perce, the Yakama, the Coast Salish, and dozens of others, the Salmon Run was the calendar. Every significant cultural event, every spiritual practice, every economic activity was organized around the timing of the different salmon species' annual return from the ocean to spawn in the rivers where they were born. The rivers were not empty waterways interrupted by periodic fish, they were salmon ecosystems that were occasionally navigable by canoe. The abundance was difficult to overstate. Early European observers reported salmon runs so dense that a person could walk across a river on the backs of the fish. The Chinook salmon of the Columbia River system reached weights exceeding 100 pounds. The total mass of salmon returning to the Pacific Northwest's river systems each year has been estimated at hundreds of thousands of tons, a massive annual import of marine nutrients into terrestrial ecosystems, carried by fish that spawned and died in the rivers, feeding bears, eagles, wolves, and the streamside trees that absorbed the nitrogen from their decomposing bodies. What the salmon does for the forest. The Pacific salmon's life cycle is, from an ecological standpoint, one of the most important nutrient transfer mechanisms in the world. Salmon spend years in the ocean, accumulating biomass from marine food webs. They then swim hundreds of miles upstream, spawn, die, and decompose, depositing ocean-derived nitrogen and phosphorus in freshwater and riparian ecosystems that would otherwise be nutrient-poor. Studies of old-growth forests near Pacific salmon streams have found marine nitrogen isotopes, the chemical signature of ocean-derived nutrients, in tree rings up to 500 meters from the stream. The trees are growing on salmon. Bears and eagles carry carcasses into the forest, their scat, and the decomposing pieces of fish scattered from their feeding, distribute marine nutrients across entire watersheds. Remove the salmon, and the forest grows more slowly. The fish and the trees are one system. The trees near Pacific salmon streams contain marine nitrogen, the chemical signature of ocean-derived nutrients, carried by fish and distributed by bears. Remove the salmon, and the forest grows more slowly. The fish and the trees are one system. Thomas Reinchen, Salmon Forest Nutrient Studies, University of Victoria, 2001. The dams. The 20th century built approximately 75,000 dams on American rivers. In the Pacific Northwest, the Columbia River system, historically one of the most productive salmon rivers in the world, was dammed repeatedly, beginning with the Grand Gully Dam in 1942. Grand Gully blocked access to approximately 1,100 miles of spawning habitat that had produced millions of salmon annually. Downstream dams blocked additional runs. By the late 20th century, salmon runs in the Columbia system were at approximately 1 to 3% of their historical levels. The economic argument for the dams was straightforward: hydroelectric power, irrigation water, and flood control. The economic argument against them, the salmon fisheries, the indigenous economies, the tourism, the ecosystem services, was diffuse, harder to quantify, and represented interests that had less political power. The dams were built. The salmon declined. The communities whose cultures and economies had been organized around the fish for thousands of years experienced a collapse that is still ongoing. The removal. Since the 1990s, dam removal has become one of the most consequential environmental restoration strategies in the United States. The removal of the Elwha and Glines Canyon dams on Washington's Elwha River, completed in 2014, was the largest dam removal in American history. Within 3 years, salmon were observed spawning in reaches of the river that had been blocked for a century. The ecosystem recovery has been faster than almost anyone predicted. Dam removal cannot undo a century of blocked migration. The salmon populations returning to restored rivers are fragments of what existed before. But the speed of recovery demonstrates that the river system retains the memory of what it was, that the gravel beds, the water chemistry, the temperatures that salmon require are still there, waiting for the fish to find them. The salmon, against reasonable odds, keeps returning. It is not clear that we deserve the second chance it is offering. The salmon's return to restored rivers is not merely an ecological fact. It is a political one. Dam removal on the Klamath River, a larger and more contested project than the Elwha, involving 4 dams on the California-Oregon border, was completed in 2024 after decades of legal and political conflict pitting hydroelectric operators, irrigators, and tribal nations against each other. The tribal nations who had depended on Klamath salmon for thousands of years, and whose fisheries had collapsed after the dams were built, were the most consistent advocates for removal across the entire decades-long process. The salmon did not negotiate its return. The people who remembered what the river had been negotiated it. The fish came back because someone kept asking for it. Chapter 23. The lab mouse. The animal that saves 1 million lives a year. The inbred strain. In 1909, a Harvard biologist named Clarence Cook Little began a breeding experiment that would change medicine. He bred brother to sister, then their offspring to each other, 4 generation after generation, until the genetic variation within each breeding line was nearly eliminated. What he produced were inbred mouse strains, populations of mice so genetically similar to each other that the results of experiments on one mouse could be reliably replicated in another. This seems like a technical detail. It is actually the foundation of modern biomedical research. Before inbred strains, animal experiments produced variable results because different animals had different genetic backgrounds that interacted differently with the treatments being tested. With inbred strains, experimental variability dropped dramatically. The results became reproducible. The mouse became a model organism, an animal whose standardized biology served as a proxy for understanding human biology, in conditions controlled precisely enough to produce knowledge that could be built upon. Why the mouse? The mouse was not an inevitable choice. Early biomedical research used rabbits, guinea pigs, and dogs as readily as mice. The mouse prevailed because of a specific combination of properties. It is small enough to house in large numbers at reasonable cost, it breeds rapidly enough to produce statistically significant experimental populations in weeks. Its genome is 85% similar to the human genome at the sequence level, with 99% of mouse genes having a human counterpart, and a century of research has produced genetic tools, knockout mice, transgenic mice, humanized mice carrying human immune systems, that allow researchers to model human diseases with extraordinary precision. The Jackson Laboratory in Bar Harbor, Maine, maintains a collection of over 11,000 mouse strains, each one representing a specific genetic modification, a specific disease model, or a specific research need, and ships approximately 3 million mice per year to researchers worldwide. A single institution, organized around the standardization of one small rodent, is the backbone of a global biomedical research enterprise. The Jackson Laboratory ships 3 million mice a year to researchers worldwide. The drugs that emerge from that research, the chemotherapies, the immunotherapies, the vaccines, began as experiments in a standardized rodent that one institution has been breeding since 1929. Karen Rader, Making Mice, Standardizing Animals for American Biomedical Research, 2004. The Mouse's CV. The list of medical advances to which laboratory mice have contributed substantially reads like a summary of 20th century medicine. Penicillin's efficacy was demonstrated in mice before it was tried in humans. The mechanism of type 1 diabetes was worked out in nod mice, a strain that spontaneously develops the disease. HIV's behavior in the human immune system was studied in mice carrying transplanted human immune cells. The cancer immunotherapy drugs that have transformed oncology since 2010 were developed using mouse tumor models. The mRNA technology underlying the COVID-19 vaccines was tested in mice. It is not possible to calculate how many human deaths have been averted by research conducted in mice. The figure is certainly in the hundreds of millions, likely more. The animal that most people associate with domestic infestation and urban disease is, in a laboratory, among the most productive partners in the history of medicine. The limits. The mouse is not a small human. Approximately 90% of drugs that succeed in mouse models fail in human clinical trials. The reasons are multiple. Mice metabolize drugs differently than humans, their immune systems differ in important ways, and the standardized inbred mouse, precisely because of its uniformity, does not capture the genetic diversity that determines how real human populations respond to treatment. The biomedical research community has spent decades arguing about how to improve the predictive value of mouse research. The answers involve more genetically diverse mouse populations, better mouse models of specific human diseases, and earlier introduction of human-relevant biology into the development pipeline. None of these solutions eliminates the mouse. They all improve it. The animal that was standardized in 1909 to make experiments reproducible is now being diversified to make them more realistic. The mouse remains, after a century of alternatives and improvements, the best available tool for understanding what will kill us and what might save us. The search for alternatives to animal testing has, for decades, been driven by both ethical and practical concerns. Organoids, miniature organ-like structures grown from human stem cells, are now used to screen drug compounds in ways that were impossible 10 years ago. Computer modeling has improved to the point where some metabolic and toxicological predictions can be made without any animal testing. These alternatives have reduced, in certain research areas, the number of mice required. They have not replaced the mouse, because the integrated complexity of a living organism, the way a drug moves through a body, interacts with multiple organ systems, and produces effects that no single organ or computer model captures, is something that alternatives can approach but not yet replicate. The mouse remains essential precisely in the situations where everything else is insufficient. Chapter 24. The Donkey. The Forgotten Engine of Civilization. The animal history forgot. The horse gets the glory. The donkey did the work. This is not a recent injustice, it is a pattern as old as civilization itself. The horse was the prestige animal of kings, cavalry, and aristocrats. The donkey was the working animal of farmers, traders, miners, and pilgrims, the animal whose labor was so ordinary, so ubiquitous, and so essential that it became invisible. There are approximately 40 million donkeys in the world today, more than there are horses, nearly all of them working animals in developing economies. They are, by any measure of practical impact on human life, one of the most important domestic animals ever bred. Domesticated in northeast Africa from the Nubian wild as approximately 5,000 to 7,000 years ago, the donkey spread along the same routes as agriculture and trade. By 3000 BCE, donkeys were the primary long-distance transport animals of Egypt, Mesopotamia, and the Levant, carrying grain, copper, timber, and textiles across terrain and distances that human porters could not manage economically. The earliest written records of donkey caravans, from Mesopotamian merchant archives of around 2000 BCE, show a scale of organization: hundreds of animals, fixed routes, standardized loads, professional drivers, that resembles modern logistics more than it resembles pastoral animal husbandry. The economics of the donkey. The donkey's practical advantages over the horse are not obvious at first glance, because they are the advantages of the poor rather than the powerful. Donkeys eat approximately 1/3 as much as horses relative to their body weight. They can subsist on lower quality forage, straw, sparse pasture, scrubland vegetation that would leave a horse malnourished. They require less water. They are far more resistant to heat and disease than horses. They are virtually impossible to exhaust. A donkey, unlike a horse, will simply stop when it reaches its limit rather than working itself to death. For smallholder farmers in semi-arid regions, the majority of agricultural producers for most of human history, these advantages were decisive. A horse requires investment. A donkey pays for itself quickly and runs cheaply. The agricultural productivity of regions from sub-Saharan Africa to South Asia to rural Mexico depends, in millions of individual cases, on donkey power. Remove the donkeys, and the food security of a significant portion of the world's poor is immediately compromised. The Bronze Age economies that built Mesopotamian civilization ran on donkey caravans. The metal from which civilization's first tools were made moved on an animal that history has largely forgotten. Paulette Roulandocco, Donkey Archaeology Studies, 2013. The Silk Road's Real Workhorse. The Silk Road is associated with camels in the Central Asian stretches and horses in the minds of historians who focus on political and military events. The workhorses of the eastern Mediterranean end of the same trade network, the routes connecting Egypt, the Levant, Anatolia, and Greece, were donkeys. The ancient trading networks of the Bronze Age Near East ran on donkey caravans. The Assyrian merchant colony at Karnesh in Anatolia, whose archives survive from around 1900 BCE, organized the entire copper and tin trade of the ancient Near East through donkey caravans carrying standardized loads across fixed routes with professional animal handlers. This is not a minor commercial footnote. The Bronze Age economies that built Mesopotamian civilization, funded Egyptian monumental architecture, and connected the Mediterranean world were donkey economies. The metal from which bronze was made moved on donkeys. The grain that fed cities moved on donkeys. The administrative documents recording these transactions were carried by donkeys. The ancient world's most important industrial revolution, the transition from stone to metal tools, was logistically organized around an animal that history has largely forgotten. The animal at the edge. Today, donkeys occupy the edge of the modern economy, the last mile of supply chains in places where roads are bad, fuel is expensive, and mechanization has not reached. In the highlands of Ethiopia, the Atlas Mountains of Morocco, the mountains of Bolivia and Peru, and across rural South Asia and the Middle East, donkeys carry water, firewood, agricultural produce, and building materials to and from places that no vehicle can access economically. The welfare of these animals is, in many cases, poor. Working donkeys in developing countries frequently suffer from untreated wounds, overloading, inadequate water, and lack of veterinary care. Organizations like the Donkey Sanctuary work across 40 countries to improve conditions. Their argument is not sentimental. A healthy donkey works longer and more productively than a suffering one, and the families who depend on them need them to work for years, not months. The most practical argument for treating the donkey well is that civilization still needs it. The calculus of donkey welfare is also the calculus of development economics. In the smallholder farming systems of sub-Saharan Africa and South Asia, a healthy working donkey can increase a family's agricultural productivity by 30 to 50% relative to manual labor. The difference between a healthy and a suffering donkey in load capacity, working hours, and working years is the difference between a family that can produce a surplus and one that cannot. Veterinary interventions costing a few dollars per animal can extend working life by years. The return on that investment, in the terms most relevant to the families involved, is substantial. The donkey welfare question is inseparable from the rural poverty question. Chapter 25. The sheep. The animal that clothed the world. Before cotton, before synthetics. For most of human history, clothing was wool. Not exclusively linen, cotton, and silk all played roles, but wool was the fiber of everyday life for most people in most climates for most of recorded history. It is warm when wet. It resists fire. It wicks moisture away from the body. It can be felted into windproof fabric or spun into thread fine enough to be woven into cloth of surprising elegance. The domestication of wild sheep in the Zagros Mountains approximately 10,000 years ago, initially for meat and hides, eventually produced the woolly breeds whose fiber became the industrial basis of European civilization. The importance of wool to the medieval European economy was structural, not incidental. English wool exports to Flemish weavers were the primary source of royal revenue in medieval England. Edward I used wool taxes to finance wars. Florence's wool guild, the Arte della Lana, was the most powerful economic institution in 15th century Italy, funding the banking houses that financed Renaissance art and architecture. The Medici fortune that paid for Brunelleschi's dome and Michelangelo's sculptures was built, at its foundation, on sheep. The merino monopoly. The Spanish merino sheep, developed in the 12th century from North African breeds introduced to the Iberian Peninsula, produced wool of a fineness that no other breed could match. Spanish law made the export of merino sheep a capital offense. The same logic applied to silkworms in China and to any other technology so valuable that revealing it to competitors was tantamount to military surrender. For 2 centuries, Spain's merino monopoly was a significant source of economic and political power. The monopoly broke in 1765, when the King of Saxony received a gift of merino sheep from the Spanish crown and immediately began breeding them. By 1800, merino flocks were established in Saxony, France, and the Cape Colony in South Africa. In 1797, the first merino sheep reached Australia and found the dry, open grasslands of the continent so perfectly suited to their biology that the Australian wool industry grew within 50 years to dominate global wool supply. The continent that had no sheep before European contact became, within 2 generations, the world's primary source of fine wool. The Medici fortune that paid for Brunelleschi's dome and Michelangelo's sculptures was built, at its foundation, on sheep. The Wool Guild was the most powerful economic institution in 15th century Italy. Robert Lopez, The Wool Trade in Italy, Journal of Economic History, 1952. The Enclosure of England. The shift from arable farming to sheep grazing in 16th century England was one of the most disruptive social transformations of the pre-industrial era. Landlords, recognizing that wool profits exceeded grain profits per acre, converted common agricultural land into enclosed sheep pasture. The peasant families who had farmed these commons for generations were evicted, a process called enclosure, and driven off the land into towns, cities, and, eventually, the industrial workforce of the factories that the 18th century built. Thomas More, writing in 1516, described sheep as animals that eat up and swallow down the very men themselves. He was correct in the literal sense. The economic logic of wool was consuming the agricultural social order of England, replacing it with a system of enclosed private property that would eventually produce both industrial capitalism and the first global empire. The sheep that grazed the enclosed commons were not agents of this transformation. The market that made their wool more valuable than the food grown beneath their feet was the fiber at the end. Wool's share of the global textile market today is approximately 1%, a fraction of what it was before synthetic fibers and cheap cotton displaced it in the 20th century. But wool's properties have not changed. It is still the most effective natural insulator available, still fire-resistant, still moisture-managing in ways that synthetics cannot fully replicate. High-performance outdoor gear, military uniforms, and premium athletic wear all still use merino wool for applications where synthetics are inadequate. There are approximately 1 billion sheep on Earth. They are, by global count, the third most numerous large domestic animal after cattle and pigs. Most of them are kept for meat rather than wool now. The economics shifted as synthetic fibers arrived. But the animal that clothed civilization for 10,000 years has not gone anywhere. It is still on the hillside, still producing the fiber that built the Medici and the British Empire, still being shorn each spring in a ritual as old as agriculture itself. The wool industry's decline relative to synthetics masks a genuine functional superiority in specific applications. Merino wool regulates body temperature more effectively than any synthetic fiber yet produced, warming when cold, cooling when warm, by managing moisture vapor at the fiber level rather than trapping air as insulation does. Elite military units, mountaineers, and endurance athletes consistently return to merino wool for conditions where synthetic alternatives fail. The fiber that clothed civilization for 10,000 years is not obsolete. It has been displaced from mass-market applications by cheaper alternatives while remaining irreplaceable at the performance edge. The sheep, in this sense, is still working. Chapter 26. The Chimpanzee. The mirror that showed us ourselves. The uncomfortable resemblance. In 1960, a 26-year-old Englishwoman named Jane Goodall arrived at Gomstream on the eastern shore of Lake Tanganyika with almost no formal scientific training and a commission from Louis Leakey to observe chimpanzees in the wild for as long as it took. What she observed over the following decade overturned 2 assumptions that Western science had treated as foundational: that tool use was uniquely human, and that humans were uniquely capable of deliberate violence against members of their own species. Goodall documented chimpanzees stripping leaves from twigs and inserting them into termite mounds to extract termites, manufacturing a tool for a specific purpose. When she reported this finding, Leech sent back a telegram that became famous. Now we must redefine tool, redefine man, or accept chimpanzees as humans. Science chose to redefine tool. The category of tool-using animals has expanded dramatically in the decades since. The violence was harder to assimilate. In the 1970s, Goodall observed a 4-year war between two groups of chimpanzees at Gom, systematic raids, ambushes, and killings that eliminated one group entirely. The chimpanzee communities she had spent years studying as relatively peaceful family groups turned out to conduct warfare. The parallel with human behavior was too close for comfort, and remains contested in its interpretation to this day. What the genome says. The chimpanzee genome, sequenced in 2005, is approximately 98.7% identical to the human genome at the nucleotide level. This figure is cited so frequently that it has become almost meaningless from repetition, but the specific differences are worth examining. The genes that differ most between humans and chimpanzees are concentrated in a few functional categories: speech and language, brain development, immune function, and sperm competition. The gaps in the genome correspond, with some precision, to the gaps in behavior. The 1.3% difference that separates us from chimpanzees contains the genetic basis of human language, the enlarged prefrontal cortex that supports long-term planning and abstract reasoning, and the immune modifications that allowed humans to survive the new disease environments they encountered as they migrated out of Africa. Evolution did not produce humans by making many changes. It made a small number of changes in precisely the right places. When Goodall reported chimpanzees making and using tools, Leech telegraphed back, "Now we must redefine tool, redefine man, or accept chimpanzees as humans." Science chose to redefine tool. The category of tool-using animals has been expanding ever since. Jane Goodall, In the Shadow of Man, 1971. The laboratory. Chimpanzees were used extensively in biomedical research throughout the 20th century, specifically because their physiological and immunological similarity to humans made them the closest available substitute for human subjects. Chimpanzees were infected with human diseases, used to test vaccines and drugs, and maintained in research facilities for decades, sometimes for their entire lives. The NIH maintained a colony of chimpanzees designated for research until 2013, when it retired most of them to sanctuary following a National Academy of Sciences review that concluded chimpanzee research was no longer necessary for most biomedical purposes. The decision to retire the knee chimps was not purely scientific. It was a recognition that the cognitive and emotional complexity that makes chimpanzees useful research subjects, their similarity to humans, also gives them a claim to moral consideration that other research animals do not have in the same degree. The argument that ended most chimpanzee research was, essentially, that the animals are too much like us to treat as instruments. The genome had said as much in 2005. The policy took 8 more years to follow. The forest is going. Wild chimpanzee populations across Central and West Africa are declining rapidly, driven by habitat loss, hunting, and disease. The great apes range has contracted dramatically in the last century. Forest loss driven by agricultural expansion, logging, and mining has fragmented populations into increasingly small and isolated groups. Isolated groups cannot maintain genetic diversity and are vulnerable to local disease outbreaks and demographic accidents that larger connected populations can absorb. The chimpanzee is classified as endangered. Its closest living relative, the bonobo, is classified as endangered. The gorilla is classified as critically endangered. The entire group of great apes, the animals most similar to us in cognition, social structure, and genome, is in serious decline at the same moment that we have the scientific understanding to appreciate exactly how similar to us they are. The timing is, as these things often are, not a coincidence. We tend to understand what we are losing precisely as we are finishing the process of losing it. The legal status of great apes has been debated in courts in the United States, Argentina, and Spain, with advocates arguing that the cognitive and emotional complexity documented in chimpanzees warrants some form of legal personhood, not the full rights of a human being, but protections against arbitrary captivity and experimentation. These cases have not yet succeeded in establishing legal personhood, but they have forced courts and legislatures to articulate, explicitly, why cognitive complexity does or does not create moral standing. The chimpanzee has done more to clarify the philosophical foundations of animal rights law than any other species, simply by existing at the cognitive threshold where our categories begin to fail. Chapter 27. The Sea Otter. The keystone that held the ocean together. The fur that almost ended an ecosystem. The sea otter's fur is the densest of any mammal on Earth, approximately 1 million hairs per square inch, compared to roughly 100,000 hairs on the entire human head. This density is not incidental. Sea otters have no blubber. Their fur is their insulation, trapping air to maintain body temperature in cold Pacific waters. It is also, from the perspective of an 18th-century furrier, the finest pelt available anywhere in the world. When Russian pro-Mishleniki fur hunters discovered the sea otter populations of the Aleutian Islands in the 1740s, the response was immediate and devastating. Within 50 years of sustained hunting, otter populations along the North Pacific coast had collapsed from an estimated 300,000 animals to perhaps 2,000. The Russian-American company, established in 1799 to manage the fur trade, was hunting an ecosystem into collapse in real time, without the vocabulary to recognize what it was doing. Sea otter pelts were selling in Canton for the equivalent of 2 years of a laborious wages. The economics overwhelmed the ecology. What happens when otters disappear? The sea otter's role in the North Pacific kelp forest ecosystem was not understood until the animals were nearly gone, which is when their absence became impossible to ignore. Sea otters eat sea urchins. Sea urchins eat kelp. In the absence of otters, urchin populations explode. In the presence of exploding urchin populations, kelp forests disappear, grazed down to bare rock in a process ecologists call an urchin barren. The kelp forest, which provides habitat for hundreds of species of fish, invertebrates, and seabirds, simply ceases to exist. The concept of the keystone species, an animal whose presence or absence has effects on the ecosystem disproportionate to its biomass, was developed largely from observing sea otters. The ecologist Robert Payne, who coined the term in 1969, was working with sea stars in intertidal zones, but it was the otter story that made the concept legible to the broader scientific and public audience. Remove the right animal from a system and the whole system changes. Leave it in place and the system remains stable. The otter is the clearest example of this principle ever documented. Remove the sea otter and the kelp forest disappears, grazed to bare rock by unchecked urchins. The concept of the keystone species was built on watching what happened when otters were gone. James Estes and John Palmisano, Sea Otters, Their Role in Structuring Nearshore Communities, Science, 1974. The recovery. Following the International Fur Treaty of 1911, which banned commercial sea otter hunting, populations slowly began to recover. Reintroduction programs in the 1960s and 1970s moved otters from the remnant Aleutian population to coastal California, Washington, and British Columbia. Where otters were re-established, kelp forests returned. Where otters were absent, urchin barrens persisted. The cause-and-effect relationship was visible in real time, across adjacent stretches of coastline where otters were present on one side and absent on the other. The California sea otter population now stands at approximately 3,000 animals recovering, but not recovered. The otter's range has not returned to its pre-hunting extent. Conflicts with the shellfish fishing industry, which regards otters as competitors for the urchins and abalone that commercial divers harvest, have complicated efforts to expand the otter's range southward. The political economy of restoration is always more complex than the ecology, because it requires reconciling the interests of people who benefit from the restored system with the interests of people whose livelihoods the restoration disrupts. The conflict between sea otters and shellfish fisheries is a specific case of a general problem in restoration ecology. The people who benefit most from a restored ecosystem are often not the people who bear the costs of its disruption. Coastal communities that lose fishing income when otters expand into new territory experience real economic harm. The recreational divers, the kayakers, the tourists who value kelp forests, the broader public that benefits from carbon sequestration and coastal protection, their interests are diffuse, distributed, and less politically organized. Conservation economics exists, in part, to make this imbalance visible. Making it visible is not the same as resolving it. The carbon calculation. A 2012 study in Frontiers in Ecology estimated that sea otters, by maintaining kelp forests, indirectly sequester between 4.4 and 8.7 million tons of carbon annually, carbon that would otherwise be released as kelp is grazed by urchins and decomposes. This makes the sea otter a carbon sequestration tool of measurable value, and provides an economic argument for otter conservation that goes beyond ecology or aesthetics. The calculation is complicated by the fact that otters also eat other shellfish that shellfish fisheries depend on, creating a direct economic conflict. But the carbon sequestration value assigned a dollar figure using standard carbon pricing models substantially exceeds the estimated value of the shellfish the otters consume. The otter, in this accounting, is an asset. Whether the people most directly affected by its presence will accept that calculation is a different question, and one that the otter cannot answer for itself. The sea otter's story has become a standard reference point in the emerging field of biodiversity economics, the attempt to assign monetary value to the services that wild species provide to human welfare. The argument is not that nature has value only when it can be monetized. It is that the failure to assign value to natural services has consistently led to their underprotection, because they appear in no budget and no balance sheet until they are gone. The sea otter provides a clean case, a quantified service, a documented collapse, a measured recovery, and a calculated value. Whether this framing will protect species that provide services less easily calculated is the question the field has not yet answered. Chapter 28. The Turkey. The New World's Gift to the Old. The Wrong Bird. Christopher Columbus, upon his return from the Caribbean in 1493, brought back several animals and plants that would eventually reshape European diets. Among them was a bird that Europeans called the turkey, almost certainly confusing it with the guinea fowl imported through Turkey from Africa, a confusion that permanently embedded the wrong geography into the bird's English name. The turkey is not from Turkey. It is from Mexico, where it had been domesticated by the Aztec for at least 2,000 years before any European saw one. The Aztec called it Huexolotl. They kept large flocks, used the feathers for ceremonial garments and military decoration, ate the birds on significant occasions, and had bred multiple domestic varieties. When Hernán Cortés encountered Aztec turkey flocks during his 1519 campaign, he found an agricultural system of considerable sophistication organized around a bird that no European had ever seen. Within a generation, turkeys were breeding in Spanish farmyards. Within a century, they were common across Europe. The turkey's adoption into European agriculture was remarkably fast by the standards of agricultural history. By 1570, barely 50 years after Cortés's arrival in Mexico, turkeys were documented as common farm birds in England, France, Germany, and Italy. The bird had crossed the Atlantic, adapted to European climates and management practices, and inserted itself into the food economy of an entire continent in the span of a single human lifetime. The turkey's rapid adoption into European farmyards reflects a general pattern in the Columbian exchange. Plants and animals from the Americas that were productive and manageable were incorporated into Old World agriculture with remarkable speed, while the exchange in the other direction, European species moving to the Americas, was slower, more contested, and frequently catastrophic for the ecosystems receiving them. The turkey was an exception on both counts. It moved east voluntarily, in the sense that it was welcomed, and it did not devastate any ecosystem when it arrived. It simply became a farm bird, as it had been in Mexico, in a new setting. The Thanksgiving invention. The association between turkeys and American Thanksgiving is largely a 19th century construction. The actual harvest celebrations of early New England settlers, including the 1621 Plymouth feast that is retrospectively called the first Thanksgiving, more likely featured venison, seafood, and waterfowl than turkeys. Turkey became the standard Thanksgiving dish through a combination of practical and literary factors. The birds were large enough to feed extended families, they were conveniently ready for slaughter in late autumn, and Sarah Joseph R. Hale, the editor who spent 40 years lobbying for Thanksgiving to become a national holiday, featured turkey prominently in her 1827 novel and subsequent advocacy. When Abraham Lincoln proclaimed Thanksgiving a national holiday in 1863, partly as a gesture of national unity during the Civil War, turkey was already strongly associated with the occasion. The industrial poultry industry that developed in the 20th century standardized the turkey into the narrow-breasted, white-feathered broad-breasted white that now accounts for nearly all commercial turkey production, an animal so modified by selective breeding that it cannot reproduce naturally and must be artificially inseminated to maintain the breed. The modern commercial turkey, bred for maximum breast meat, unable to reproduce naturally, raised in confinement facilities with tens of thousands of birds per building, is the industrialization of an animal that the Aztec maintained in elaborate managed flocks and Europeans adopted as a farmyard bird of considerable character. The broad-breasted white turkey that fills American grocery stores each November is a different creature in almost every practical sense from either of its ancestors. It has been optimized for one moment, Thanksgiving dinner, and the rest of its biology has been treated as irrelevant to that purpose. The turkey crossed the Atlantic and became a staple of European farmyards within 50 years of Europeans first encountering it. No other New World domesticate was adopted so rapidly or so completely by the Old World. Andrew Smith, The Turkey, An American Story, 2006. The Wild Turkey's Return. The wild turkey, Meleagris gallopavo, ancestor of all domestic turkeys, was nearly extinct in the United States by the early 20th century. Unregulated hunting and habitat loss had reduced a population that once numbered in the tens of millions to an estimated 30,000 birds by 1900. Conservation programs beginning in the 1940s, combined with the reforestation of eastern North America as marginal farmland reverted to forest, produced one of the most successful wildlife recoveries in American history. Wild turkey populations now exceed 7 million birds across the continent. Benjamin Franklin's supposed advocacy for the turkey as the national bird rather than the bald eagle is almost certainly apocryphal. His actual letter compared the eagle unfavorably to the turkey, but in the context of heraldry rather than national symbolism. The story persists because it captures something real. The turkey is, by the standards of practical usefulness to the people who domesticated it, a more impressive animal than the eagle. It fed a civilization. The eagle only symbolized one. The wild turkey's recovery is often cited alongside the bald eagle, the gray wolf, and the American alligator as evidence that conservation intervention can work, that species reduced to small remnant populations by hunting and habitat loss can recover when given legal protection and habitat management. The common element in these recoveries is not any single intervention but the combination of legal protection, habitat availability, and a species resilient enough to expand once the killing stops. The wild turkey was almost gone. It came back because it turned out to be very good at being a turkey when humans stopped shooting all of them. Chapter 29. The Bat. The pilot that invented sonar. The problem of flying in the dark. Bats have been flying at night for approximately 52 million years. They evolved the capacity for powered flight at roughly the same time as echolocation, the ability to emit ultrasonic pulses and interpret the returning echoes to construct a three-dimensional map of the surrounding environment in real time. The two capabilities together solved a problem that no other flying vertebrate had solved: how to hunt, navigate, and avoid obstacles in complete darkness at high speed. The echolocation system of a hunting bat processes information at a rate that modern engineers describe as remarkable. A little brown bat emitting 10 pulses per second in cruise flight increases its call rate to 200 pulses per second during the final approach to prey, a process called a feeding buzz, compressing the acoustic updates to millisecond intervals as the target closes. The bat's auditory cortex processes these returns, tracks the moving target, predicts its trajectory, and coordinates the wing and tail movements required to intercept it. All of this happens faster than the bat's brain can consciously direct it, which means it does not consciously direct it. The hunt is automatic. What bats eat? A single little brown bat can consume 1,000 mosquitoes per hour. A colony of 150 big brown bats, a medium-sized colony by North American standards, eats an estimated 600,000 insects per summer, many of them agricultural pests. The economic value of bat predation on crop insects has been estimated at between $3.7 billion and $53 billion per year in the United States alone, depending on the methodology. The range is wide because the calculation is difficult, but even the lower bound is a substantial number for an animal that most people would prefer not to encounter. Bats also pollinate plants and disperse seeds. In tropical ecosystems, bat-pollinated plants include the agave, the source of tequila and mezcal, along with many fruit trees and the balsa wood trees whose wood is lighter than any other. In the Sonoran Desert, the lesser long-nosed bat is the primary pollinator of the giant saguaro cactus, the organ pipe cactus, and the agave species from which tequila is produced. Every bottle of tequila is, in a real sense, a bat product. A single little brown bat consumes 1,000 mosquitoes per hour. The economic value of bat insect control across North America has been estimated at up to $53 billion per year for an animal most people would prefer not to encounter. Justin Boyles et al., Economic Importance of Bats in Agriculture, Science, 2011. White nose syndrome. In 2006, a cave in upstate New York was found to contain hundreds of dead bats with a white powdery growth on their muzzles and wings. White nose syndrome, caused by the fungus Pseudogymnoas destructans, had arrived from Europe, apparently introduced on the equipment of a spelunker, and was spreading through North American bat hibernation caves with catastrophic speed. The fungus disrupts hibernation, causing bats to rouse and burn their fat reserves in winter when no insects are available. They starve. By 2019, white nose syndrome had killed an estimated 6 million bats in North America and was still spreading westward. The little brown bat, once one of the most abundant mammals on the continent, has declined by more than 90% in affected regions. The economic consequences of this decline, in terms of the agricultural pest control service the bats provided, have been estimated in the hundreds of millions of dollars annually. Farmers in affected regions are applying more pesticide to compensate for the insect control they are losing. The bats that kept those insects in check for free are being replaced by chemicals that cost money and have their own ecological consequences. The virus question. Bats are the natural reservoir for a remarkable number of viruses that are dangerous to humans: rabies, Nipah, Hendra, Marburg, and the subject of sustained scientific debate, the SARS-CoV-2 coronavirus that caused the COVID-19 pandemic. Bats' immune systems appear to have co-evolved with these viruses over millions of years, tolerating infections that would kill other mammals. Their high body temperatures during flight, equivalent to a sustained fever, may accelerate viral replication and drive the evolution of strains that are increasingly temperature-tolerant and therefore capable of infecting other warm-blooded animals. The bat is not responsible for the viruses it carries, any more than the flea was responsible for Yersinia pestis. The conditions that transmit bat viruses to humans, wildlife markets, habitat destruction that forces bats into closer contact with human settlements, the hunting and consumption of bats as bushmeat are human conditions. The bat has been managing its viral passengers for 50 million years without incident. The incidents occur when humans disturb the arrangement. The precautionary lesson of bat-borne viruses is not that bats should be feared or culled, policies that have been tried and found ineffective at reducing disease risk. It is that the conditions enabling spillover are human conditions. Reducing wildlife habitat, expanding into previously wild areas, hunting, and consuming wild animals. These are the proximate causes of most zoonotic disease emergence. The bat carries its viruses quietly for millions of years until a human being creates the conditions for transfer. The epidemic begins not in the bat colony but in the market, the farm, the deforested landscape where wild and domestic animals and humans meet in new combinations. Chapter 30. The Ox. The engine that broke the ground. Before the tractor. The ox, a castrated male bovine, trained to draft work, is among the most underappreciated agricultural technologies in human history. For approximately 10,000 years, from the earliest farming settlements of the Near East through the mid-20th century, the ox was the primary source of mechanical power in agriculture worldwide. It plowed the fields that fed cities. It hauled the timber that built cathedrals. It pulled the carts that moved grain, stone, and armies across the landscape of civilization. Every major agricultural civilization before industrialization, Mesopotamian, Egyptian, Chinese, Indian, Greek, Roman, medieval European, organized its agricultural power around the ox. The choice of the ox over the bull or the horse was economically rational. A castrated male bovine is calmer, more controllable, and more willing to work steadily for extended periods than either a bull or a stallion. It is slower than a horse but eats less, is more tolerant of poor forage, and is more powerful at low speeds, the regime relevant to plowing and hauling. A horse outperforms an ox at speed. An ox outperforms a horse at raw draft force on heavy ground. For most of agricultural history, heavy ground was the problem. The plow and the landscape. The heavy moldboard plow, the implement that could turn the thick, wet, clay-rich soils of northern Europe, required draft power that only multiple oxen could provide. A team of 8 oxen was needed to pull a heavy plow through English clay. The organization of labor required to maintain and deploy 8 ox teams shaped the entire social structure of medieval English agriculture. The open field system, the strips, the cooperative organization of village farming, the rights and obligations of manor and village, all followed from the logistical requirements of the plow team. Marc Bloch, the great French medieval historian, argued that the heavy plow was responsible for the shift in European demographic gravity from the light soils of the Mediterranean easily worked with a light plow to the rich clay soils of northern France, the Low Countries, and England. The most productive agricultural land in Europe was not the Mediterranean basin. It was the north, once the heavy plow and the ox team made its soils workable. The economic and political center of gravity followed. The ox, by enabling the plow, shaped the map of European civilization. The word capital derives from caput, head, as in head of cattle. The ox that broke the ground to grow the grain was also the unit in which ancient wealth was measured. Finance still speaks in cattle. Marc Bloch, French Rural History, 1931. The symbolic ox. The ox's cultural significance runs as deep as its agricultural importance. In ancient Mesopotamia, the bull, divine ancestor of the ox, was a symbol of royal and divine power. In Egypt, the Apis bull was a living god, housed in a temple, tended by priests, and mourned with elaborate ceremony when it died. In Hindu tradition, the bull Nandi is the vehicle of Shiva and the protector of Dharma. The domesticated ox was not only an economic resource, it was a theological object, a symbol of the power that civilization depended on. The word pecuniary, meaning relating to money, derives from the Latin pecus, meaning cattle. The word capital derives from caput, meaning head, as in head of cattle. Cattle were the first currency in many cultures, and the vocabulary of finance still bears their trace. The ox that broke the ground to grow the grain that fed the city was also, in the counting houses of the ancient world, the unit in which wealth was measured and debts were denominated. The retirement. The ox began its long retirement with the arrival of the horse collar in medieval Europe, which made the horse competitive for agricultural draft work. It retreated further with the steam traction engine in the 19th century and was largely replaced by the gasoline tractor in the 20th. In the industrialized world, Working oxen are now primarily found at historical farm demonstrations and in specific niche applications where their docility and sure-footedness are preferred. In sub-Saharan Africa, South Asia, and parts of Latin America, ox-drawn plows are still in daily use on smallholder farms where tractors are too expensive to buy and maintain. The global working bovine population is estimated at several hundred million animals, most of them in developing countries, most of them doing the same work their ancestors have done for 10,000 years. The industrial world has moved on. The rest of the world is still, in many places, in the age of the ox. The persistence of the working ox in developing economies is not nostalgia or technological backwardness. It is economics. A tractor requires capital to purchase, diesel to run, mechanics to maintain, and spare parts that may not be locally available. An ox requires grass, water, and the knowledge that has been transmitted across generations of farmers without institutional support. In the smallholder farming systems that produce a significant share of the world's food, the ox's cost structure, low acquisition cost, local fuel, local maintenance remains competitive in ways that the energy costs and capital requirements of mechanization cannot overcome without subsidy. The animal is still working because the economics still work. Chapter 31. The Tuna. The fish worth more than gold. The New Year's auction. On January 5, 2019, a 612-pound bluefin tuna sold at the Toyosu Fish Market in Tokyo for 333.6 million yen, approximately $3.1 million, or just over $5,000 per pound. The buyer was Kiyoshi Kimura, president of the Sushizanmai restaurant chain, who had been winning the annual New Year's auction for several consecutive years, partly as a marketing exercise and partly as a genuine expression of the premium market that has grown up around bluefin tuna. The fish that once sold for pennies per pound in the United States, so undesirable that it was used as cat food until the 1970s, had become the most expensive food animal in the world. The transformation happened quickly and for reasons that are simultaneously cultural, economic, and ecological. Sushi's global expansion from the 1980s onward created demand for bluefin that had not previously existed outside Japan. Japanese traders and restaurants developed relationships with Atlantic bluefin fishermen in Nova Scotia and New England, paying prices that bore no relationship to the prices those fishermen had previously received. The fishermen, naturally, increased their catch. The bluefin population, which had been stable or recovering, began to decline. The biology of the bluefin. The Atlantic bluefin tuna is among the most physiologically impressive fish in the ocean. It is warm-blooded, one of the very few fish capable of maintaining a body temperature significantly above the surrounding water, which allows it to operate in cold North Atlantic waters where other large tuna cannot go. It can reach speeds of 45 miles per hour in short bursts. It migrates annually between feeding grounds in the North Atlantic and spawning grounds in the Mediterranean or the Gulf of Mexico, a round trip of thousands of miles navigated with precision that researchers still do not fully understand. The bluefin's size and fat content, the qualities that make it desirable for high-grade sushi, are the products of a life history organized around long migrations and extended cold-water foraging. A large bluefin is, in a literal sense, years of accumulated ocean. It takes approximately 8 years for a bluefin to reach sexual maturity, and the largest individuals are 20 to 30 years old. This life history makes the population highly vulnerable to overfishing. Remove the large, old, mature fish that are most desirable and most valuable, and you remove precisely the individuals whose reproduction sustains the population. As the bluefin became scarcer, its scarcity increased its prestige, which increased its price, which increased the incentive to catch the remaining fish. The high price of a bluefin tuna is not protecting the species. It is incentivizing its elimination. Paul Greenberg, 4 Fish, The Future of the Last Wild Food, 2010. The Collapse and the Market. Atlantic bluefin tuna populations declined by approximately 85% between the 1960s and the 1990s. Management quotas established by the International Commission for the Conservation of Atlantic Tunas, known, with some bitterness, in the fishing industry as the international conspiracy to catch all the tuna were consistently set above sustainable levels and consistently exceeded in practice. The political economy of fisheries management, in which the fishing industry has a concentrated, immediate interest in higher quotas and the public has a diffuse, long-term interest in lower ones, produced predictable results. The market response to declining bluefin populations has been perverse by the standards of conservation economics. As the fish became scarcer, its scarcity increased its prestige value, which increased its price, which increased the financial return to catching the remaining animals. The high price of bluefin tuna is not, in this case, creating an incentive to protect the stock. It is creating an incentive to catch what remains before someone else does. Farming the bluefin. Bluefin tuna aquaculture, farming the fish from egg to market weight, is among the most technically difficult aquaculture challenges ever attempted. The fish are sensitive, fast-moving, and require conditions that are extraordinarily difficult to maintain in captivity. Japan's Kinki University began its bluefin aquaculture program in 1970 and produced the first full-cycle farmed bluefin in 2002, 32 years of research to produce a fish that nature had been producing for millions of years. The farmed fish are now commercially available, marketed under the brand name Kindai Tuna, and fetch premium prices. Whether farmed bluefin can meaningfully reduce pressure on wild populations depends on the economics of each. If farmed bluefin becomes cheaper than wild-caught, demand may shift. If farmed fish remain a niche premium product, the wild fishery continues under the same pressures. The fish that was once cat food, that became the most expensive food animal in the world, is now also a farmed product. What it is not, in the Atlantic, is safe. The tuna's journey from cat food to the most expensive food animal in the world happened in less than 50 years, faster than almost any other commodity revaluation in food history. The mechanism was cultural rather than intrinsic, the globalization of sushi taste, the association of bluefin with premium Japanese cuisine, and the scarcity premium that followed. The fish did not change. The market's perception of it changed completely. This trajectory, abundance to scarcity to luxury, is the standard arc of any natural resource whose extraction is not managed below the level at which price signals are reliable guides. By the time price signals indicate scarcity, the resource is already in serious trouble. Chapter 32. The cat. The predator that chose civilization. The uninvited guest. The domestication of the cat is unique in the history of animal domestication because it was, in all probability, not intentional. Every other domestic animal was deliberately captured, selectively bred, and consciously shaped into its domestic form over generations. The cat appears to have domesticated itself. The agricultural revolution created grain stores. Grain stores attracted rodents. Rodents attracted wild cats, specifically the Near Eastern wildcat, Felis sylvestris libica, which discovered that the margins of human settlements offered a concentrated prey supply unavailable in the surrounding landscape. The cats that were least fearful of humans could exploit this resource. Their offspring inherited both the tolerance of humans and the advantage it conferred. The earliest evidence of cats living with humans dates to approximately 9,500 years ago on Cyprus, an island that, in the Neolithic period, had no native wildcats, meaning the animals must have been transported deliberately by settlers who had already begun maintaining them. By 4,000 years ago in Egypt, cats were not merely tolerated, they were venerated. The goddess Bastet, depicted as a cat or a woman with a cat's head, was one of the most popular deities in the Egyptian pantheon. Harming a cat was a capital offense. When a household cat died, the family mourned it as they would a human family member. The ship's cat. The cat's most historically significant role outside Egypt was on ships. A ship carrying grain is a floating ecosystem for rats and mice. Cats controlled these populations and protected cargo that was vulnerable to rodent damage on voyages that might last months. Maritime cultures from ancient Phoenicia through the Age of Sail maintained cats as standard ship's equipment, and the global distribution of the domestic cat today closely tracks the roots of maritime trade and colonization. The domestic cat reached Britain with the Romans, the Americas with European colonizers, Australia with the first fleet, and the Pacific Islands with Polynesian and European sailors. In every new environment, cats encountered prey species that had evolved without them: birds, reptiles, small mammals that had no behavioral adaptations for avoiding a stealthy, fast predator of the cat's capabilities. The results, on islands in particular, have been catastrophic. Cats are estimated to kill between 1.3 and 4 billion birds annually in the United States alone and have been implicated in the extinction of at least 63 species worldwide. The cat domesticated itself. It came to the margins of human settlements because grain stores attracted rodents and rodents attracted cats. It stayed because the arrangement suited it. We did not choose the cat. The cat chose us. Claudio Ottoni et al., The Paleogenetics of Cat Dispersal, Nature Ecology and Evolution, 2017. The Indifferent Companion. The cat's relationship with humans has never been fully domesticated in the behavioral sense. A dog deprived of human company shows distress. A cat, for the most part, does not. Behavioral studies comparing dog and cat responses to separation indicate that cats show little cortisol elevation, the hormonal marker of stress, when their owners leave, and variable but often minimal greeting behavior when they return. This is not evidence that cats are incapable of attachment. Studies do document individual cats forming strong preferences for specific humans. It is evidence that the cat's attachment system is qualitatively different from the dog's, less dependent, less anxious, and apparently chosen rather than assumed. From an evolutionary standpoint, this makes sense. The dog was shaped by thousands of years of selection for dependence on human social cues, a partner in the hunt, the herd, and the home. The cat was shaped by selection for solitary hunting efficiency, into which it allowed humans at the margins without ever fully reorganizing its social architecture. It came to us for the rats. It stayed for reasons that remain, characteristically, its own. The cat's particular form of companionship, available but not dependent, affectionate but not anxious, has proven remarkably well suited to specific cultural moments. The rise of single-person households in industrialized countries, the extension of working hours that makes dog ownership logistically difficult, the growth of urban apartment living where outdoor access is limited, all of these trends have favored cats over dogs as companions. The cat's self-sufficiency is not a bug. It is, in the specific ecological niche of the contemporary urban apartment, a feature. The animal that chose civilization on its own terms has found, in the contemporary city, a new version of the arrangement it first proposed 10,000 years ago. The population problem. There are estimated to be between 600 million and 1 billion domestic cats worldwide, of which approximately 480 million are unowned or feral, living in and around human environments without human care. The feral cat population is one of the most significant wildlife management problems in many countries, both because of the predation pressure on native wildlife and because of the zoonotic diseases, toxoplasmosis, rabies, cat scratch disease, that feral populations harbor. Trap-neuter-return programs, which capture feral cats, sterilize them, and return them to their territory, are widely promoted as a humane management strategy. Their effectiveness at reducing feral cat populations at landscape scale is contested by wildlife biologists, who point out that sterilized cats still hunt and that reduced reproduction in one colony is quickly offset by immigration from adjacent areas. The cat that chose civilization has, in its feral form, become one of civilization's most challenging ecological consequences. Chapter 33. The Reindeer. The animal that made the Arctic livable. The North without the reindeer. The Arctic and subarctic landscapes of northern Eurasia, the tundra, the taiga, the coastal grasslands of Siberia and Scandinavia are among the most inhospitable environments in which humans have maintained continuous habitation. The peoples who have lived there for thousands of years, the Sami of Scandinavia, the Nenets and Evenki of Siberia, the Chuki of the far northeast, managed this inhospitality through a single technological solution, the domestication and management of reindeer. Reindeer provide everything a human being needs to survive in the far north. Their meat is dense with fat and protein suitable for cold climates. Their hides, tanned with the animal's own brain matter in traditional practice, produce the warmest and most wind-resistant clothing available before synthetic materials. Their tendons serve as thread. Their bones and antlers as tools. Their sinew as bowstring. Their milk as food for children and nursing mothers. Their dung as fuel when wood is unavailable. In the most demanding environment on Earth, the reindeer is not one resource among many. It is the entire resource base. The migration. Reindeer are migratory. Wild reindeer herds move hundreds of miles between summer and winter ranges, following the availability of the lichens and sedges they depend on. The peoples who domesticated them, the process appears to have begun in southern Siberia approximately 5,000 years ago, adapted their own lives to the reindeer's movement, following the herds across the same seasonal routes that the wild animals had traveled for millennia. This nomadic herding system, still practiced across northern Scandinavia and Siberia, is not primitive by any reasonable standard. It is a sophisticated logistical operation that manages thousands of animals across landscapes too large and cold for any fixed agricultural system. The Nenets of northwestern Siberia manage herds of up to 10,000 reindeer, following them on routes spanning 700 miles each year. The knowledge required of landscape, weather, ice conditions, grazing quality, and animal health is accumulated over lifetimes and transmitted across generations. It is, in every meaningful sense, a science. In the far north, the reindeer is not one resource among many. It is the entire resource base: food, clothing, tools, fuel, transportation. The peoples of the Arctic did not domesticate the reindeer. They built their civilization on it. Tim Ingold, Hunters, Pastoralists and Ranchers, 1980. The caribou of North America. In North America, the reindeer's wild cousin, the caribou, was never domesticated, but it was no less central to the cultures that depended on it. The Dene, Cree, Inuit, and other indigenous peoples of subarctic and Arctic North America organized their entire economies around caribou migration. The timing of caribou movements determined where communities lived and when they moved. The success or failure of caribou intercepts during migration determined whether families survived the winter. The porcupine caribou herd, approximately 218,000 animals that migrate between calving grounds in the Arctic National Wildlife Refuge in Alaska and winter ranges in the Yukon, is the subject of a decades-long political conflict between conservation, indigenous rights, and oil development interests. The Gwich'in people, whose communities are located along the caribou migration route and who have depended on the herd for thousands of years, have been among the most consistent opponents of oil development in the calving grounds. Their argument is not sentimental. It is existential. The caribou is the foundation of a way of life that oil development would eliminate. Climate change at the top of the world. The Arctic is warming approximately 4 times faster than the global average. For reindeer and caribou, this has specific and documented consequences. Warmer temperatures produce rain-on-snow events, ice crusts that seal the lichens beneath them and can starve entire herds. Reduced snowpack changes the timing and passability of seasonal migrations. Expanding shrub vegetation, driven by warming temperatures, alters the composition of grazing habitat. Insect populations, botflies and warble flies that parasitize reindeer, expand with warming temperatures and increase the stress on animals. Wild caribou populations in North America have declined by more than 50% since the 1990s. Reindeer herding in Siberia is being disrupted by permafrost thaw that changes the landscape, and by rain-on-snow events that have killed thousands of animals in single episodes. The people who organized their lives around these animals for millennia are finding that the animals' predictability, the foundation of a herding system, is diminishing. The Arctic that the reindeer made livable is becoming, for both the animals and the people who followed them, increasingly difficult to inhabit. The warming of the Arctic is also changing the relationship between reindeer herders and the state systems that govern their territories. Fences, administrative boundaries, and land use regulations designed around a static landscape are increasingly mismatched to a migratory system that is itself changing, shifting routes, altered timing, new obstacles from thawing permafrost and changed vegetation. In Norway, Sweden, and Russia, indigenous herding communities are navigating not only ecological disruption but the bureaucratic frameworks that were not designed for the dynamics they now face. The reindeer's adaptability may be less limiting than the human institutional response to the landscape it is trying to adapt to. Chapter 34. The Rabbit. The Invader That Remade Continents. 24 Rabbits. In October 1859, a pastoralist named Thomas Austin released 24 wild European rabbits onto his property in Victoria, Australia. He had brought them from England for hunting. Within 10 years, the rabbit population of southeastern Australia had grown to millions. Within 30 years, it had spread across the continent. The European rabbit Oryctolagus cuniculus, encountering a landscape without any evolved predators and with virtually unlimited forage, reproduced at the maximum rate its biology allowed and kept reproducing. By the early 20th century, Australia's rabbit population was estimated at 10 billion animals. The ecological and economic consequences were severe. Rabbits competed directly with sheep for pasture, contributing to a pastoral industry crisis in the 1890s that ruined thousands of farmers. They stripped vegetation from entire hillsides, accelerating erosion on a continental scale. They browsed tree seedlings and shrubs, preventing forest regeneration and converting woodland to grassland. Native plants that had evolved without browsers capable of rabbit-like population densities were eaten to local extinction in many areas. The rabbit did not intend any of this. It was simply very good at being a rabbit in a place where nothing had evolved to stop it. The fence and the virus. Australia's response to the rabbit invasion began with fencing and ended with biology. The No. 1 rabbit-proof fence, completed in 1907, stretching 1,833 kilometers from the north to the south coast of Western Australia, was the longest continuous fence in the world, built to prevent rabbits from spreading westward into the agricultural districts of Western Australia. It failed. Rabbits were already past the fence line before construction was completed, and the fence itself required constant maintenance against breaches. The biological solution arrived in 1950, when the myxoma virus, discovered in Brazilian wild rabbits, which had evolved resistance to it, was deliberately released into the Australian rabbit population. Within 2 years, it had killed an estimated 500 million rabbits. Australian farmers watching the epidemic spread across the landscape described it as the most dramatic agricultural event they had ever witnessed. The virus was not a permanent solution. Surviving rabbits were genetically resistant, and rabbit populations began recovering within a decade, but it provided temporary relief and established the principle that biological control could work at continental scale. Thomas Austin released 24 rabbits in 1859 for hunting. By the early 20th century, Australia's rabbit population was estimated at 10 billion. He thought a few rabbits could do little harm. Eric Rolls, They All Ran Wild, The Story of Pests on the Land in Australia, 1969. The same animal in Europe. The rabbit's ecological history in Europe is precisely the reverse of its history in Australia. In its native Iberian Peninsula and southern France, the European rabbit is a keystone species whose burrows provide habitat for dozens of other species, whose grazing maintains the open grassland habitats that many Mediterranean plant communities require, and whose population supports the entire predator community of the Iberian scrubland, including the critically endangered Iberian lynx and Spanish imperial eagle, both of which depend almost entirely on rabbits for food. Rabbit populations in Spain and Portugal have collapsed since the 1950s, driven by myxomatosis, the same virus deliberately introduced in Australia, a second disease called rabbit hemorrhagic disease, and habitat loss. The Iberian lynx, reduced to fewer than 100 individuals by 2002, faced extinction partly because its prey base had disappeared. Recovery programs for both the lynx and the Spanish imperial eagle now include active rabbit population management, breeding and releasing rabbits to support the predators that depend on them. The same animal that is considered a plague in Australia is being raised in captivity and released to prevent ecological collapse in Spain. What the rabbit teaches. The rabbit's story is a lesson in ecological context. An animal is not inherently a pest or a keystone species. It is one or the other depending on the ecosystem it inhabits, whether the ecosystem has evolved with it or not, whether its population is regulated by predators and disease or is free of both. The rabbit in Australia occupied a niche with no constraints. The rabbit in Spain occupied a niche as a structural element. The animal is the same. The context is everything. Thomas Austin, who released the 24 Rabbits in 1859, reportedly said that he thought the introduction of a few rabbits could do little harm and might provide a touch of home. The most consequential ecological disasters in history have tended to begin with similar calculations, confident, small-scale, and entirely wrong about what a few of something can become when the conditions are right. The biological control failure in Hawaii, introducing a predatory snail to control the giant African land snail and watching it eat everything except the target, is now taught in ecology courses as a canonical example of how not to do biological control. The lesson is that introduced species interact with ecosystems in ways that are impossible to fully predict from laboratory testing or short-term trials. The conditions of the wild, the behavioral flexibility of the introduced organism, the absence of its co-evolved context, these produce outcomes that controlled studies cannot anticipate. The rabbit taught this lesson on a continental scale. The wolf snail taught it on an archipelago. Neither lesson was cheap. Chapter 35. The Locust. The hunger that made empires fall. The swarm. A desert locust swarm can contain up to 80 billion insects, cover an area of 460 square miles, and consume in a single day the same amount of food that 35,000 people eat in a year. The swarm moves with the wind, consuming everything in its path: crops, pasture, bark, thatch, and leaving behind a landscape that looks as though it has been burned. The individual desert locust, Schista circa gregaria, is a small grasshopper in its solitary phase, spending most of its life inconspicuously on dryland vegetation. When population density crosses a threshold, the insects change physically and behaviorally into the gregarious phase, more active, more mobile, drawn together into the immense coordinated masses that have been described in human records for 5,000 years. The transformation is triggered by serotonin. Crowding causes locusts to rub against each other's hind legs, which elevates serotonin in the nervous system, which triggers the behavioral and physiological shift to the gregarious phase. The same neurotransmitter that humans associate with well-being and social connection is, in the locust, the signal that initiates a collective behavior capable of destroying the food supply of entire regions. The biochemical link between human and locust is close enough to be instructive and disturbing in equal measure. Famine and the fall of empires. Locust swarms appear throughout the historical record as precursors to famine, political instability, and the collapse of agricultural states. The biblical plagues of Egypt almost certainly included a genuine locust event. The natural history of desert locusts in the Nile Valley is consistent with the conditions described. The fall of the Aksumite Empire in the 6th century CE has been linked to repeated locust invasions that destabilized its agricultural base. The famines that contributed to the French Revolution were preceded by several seasons of poor harvests, some of which were aggravated by locust damage to grain crops in North Africa and southern Europe. The relationship between locust outbreaks and political instability runs in both directions. Locusts are more likely to swarm when wet conditions in normally dry breeding areas allow populations to build up to threshold densities, conditions that correlate with the disruption of traditional land management practices during wars or political crises. Unstable politics can create locust conditions. Locust swarms can create political instability. The historical record contains many cases that are difficult to untangle. A desert locust swarm of 80 billion insects can consume in one day what 35,000 people eat in a year. The transformation from solitary grasshopper to swarming plague is triggered by serotonin, the same neurotransmitter humans associate with well-being. Stephen Simpson and Gregory Sword, Locusts, Current Biology, 2008. The 2020 Outbreak. The largest desert locust outbreak in 70 years began in 2019, driven by unusual rainfall in the Arabian Peninsula and eastern Africa associated with intensified Indian Ocean weather patterns. By early 2020, swarms had invaded 20 countries across East Africa, the Middle East, and South Asia. A single swarm in Kenya was estimated to cover 2,400 square kilometers. The outbreak threatened the food security of approximately 42 million people across the region and required emergency international response involving aerial pesticide spraying across millions of hectares. Climate scientists noted that the weather conditions driving the outbreak, the warm Indian Ocean temperatures and associated rainfall anomalies, were consistent with climate change projections. The locust may be a preview, an insect whose outbreaks are driven by climatic conditions that are becoming more frequent, affecting food production in regions already under stress from population growth and economic vulnerability. The swarm that has ended harvests and destabilized governments since the Bronze Age appears to be preparing for a larger role. Eating the locust. In every culture that has experienced locust swarms, people have also eaten locusts. They are, nutritionally, excellent, high in protein, fat, and micronutrients, available in enormous quantities at precisely the moments when other food sources are being destroyed. The Book of Leviticus permits eating locusts, katydids, crickets, and grasshoppers, a dietary rule that made practical sense in an environment where swarms regularly destroyed crops and provided an alternative caloric source simultaneously. In East Africa today, roasted locusts are sold as street food during outbreak seasons, providing income to families whose crops the same swarms have just destroyed. The global interest in insect protein as a sustainable food source has given the locust new relevance. Raising insects requires a fraction of the land, water, and feed that livestock production requires, and produces comparable protein per kilogram. Whether Western consumers will accept insect protein at scale remains to be seen. The rest of the world, which has been eating insects for thousands of years, is waiting patiently for the question to be answered. The locust's agricultural devastation and its nutritional value are not in contradiction. They are expressions of the same biological fact. The locust is an extremely efficient converter of plant matter into animal protein, which is why it can strip a landscape and why it is also worth eating. The irony is that the same insects destroying crops in East Africa are, in principle, a harvestable food source of considerable nutritional density. The practical obstacles, harvest logistics, processing infrastructure, consumer acceptance, and the timing overlap between peak swarm activity and the capacity of affected communities are real. But the basic arithmetic is there. The swarm that destroys the harvest is also the harvest. Chapter 36. The Eel. The creature that defied everything we knew. The mystery of reproduction. No one has ever seen a European eel reproduce. Despite centuries of observation, despite the eel's presence in virtually every river, lake, and coastal waterway in Europe and North Africa, and despite the commercial fishing of eels that has sustained industries across the continent for thousands of years, the eel's reproductive act has never been witnessed by a human being. We know it happens. We know approximately where, the Sargasso Sea, in the western Atlantic, where larval eels have been collected. We do not know exactly how, or precisely when, or exactly what triggers the journey. The European eel Anguilla anguilla hatches in the Sargasso Sea and drifts on ocean currents for up to 3 years as a transparent, leaf-shaped larva before reaching European coasts. It then transforms into a glass eel, still transparent, but recognizably eel-shaped, and migrates inland up river systems, where it lives for anywhere from 5 to 20 years as a yellow eel, growing to maturity. Then, responding to cues that are still not fully understood, it transforms again, eyes enlarge, skin darkens, digestive system shrinks, and begins a one-way journey back to the Sargasso Sea to spawn and die. No adult eel that has begun this journey has ever been captured in the Sargasso. The spawning grounds have never been found. The eel's most fundamental biological act remains, for all practical purposes, a mystery. The eel in culture. The eel's reproductive mystery has made it the subject of speculation for as long as humans have had writing. Aristotle concluded that eels spontaneously generated from mud. Pliny the Elder proposed that they reproduced by rubbing against rocks and that the shed fragments came to life. Isaac Walton, in The Complete Angler in 1653, reviewed the existing theories and found them all unsatisfactory, which was the correct assessment. Sigmund Freud, as a young medical student in Vienna, spent 4 weeks at a marine research station in Trieste dissecting 400 male eels in an attempt to find the testicles. He failed. In his first published scientific paper, he reported that he had been unable to find them, a paper that suggests, in retrospect, that the young Freud's interest in what was hidden was already fully formed. Aristotle thought eels spontaneously generated from mud. Freud dissected 400 of them looking for testicles and failed. We still cannot complete the European eel's life cycle in captivity. It is critically endangered. It will probably take its secret with it. Tom Fort, The Book of Eels, 2002. The Economics of the Eel. The European eel has been a significant food fish in Europe since the Neolithic period. Eel traps are among the oldest continuous pieces of fishing infrastructure in the world. Some sites in Belgium and the Netherlands have documentation of eel fishing in the same locations for over 1,000 years. In medieval England, eels were so economically important that rents and taxes were sometimes paid in them. The Domesday Book of 1086 records over 68,000 eels as tax payments in a single year. Today, the European eel is critically endangered. Its population has declined by more than 90% since the 1980s, driven by a combination of overfishing, habitat loss through river damming and drainage, parasitic infestation by a swim bladder nematode introduced from Asia, and, perhaps most significantly, changes to ocean circulation patterns that appear to be affecting the survival of larvae crossing from the Sargasso Sea to European coasts. The critically endangered animal that no one has seen reproduce is disappearing for reasons that are only partially understood, into a mystery that has never been solved. The eel as argument. The eel is a useful argument against the assumption that we understand the natural world. We have been fishing it commercially for thousands of years. We have subjected it to more scientific scrutiny than almost any other freshwater fish. We still cannot complete its life cycle in captivity. We cannot farm it from egg to adult. We can only collect wild glass eels and raise them in aquaculture systems that depend entirely on wild recruitment. We are, in practical terms, mining a wild population that we cannot replenish, of an animal we cannot breed, whose most basic biology we cannot observe. If we lose the European eel, which the current population trajectory suggests is a real possibility, we will lose it before we understand it. This is not unusual in the history of extinction. What is unusual about the eel is that the mystery is so fundamental, we do not know where it goes or what it does when it gets there. The eel will take its secret with it. Whether that is loss or simply the natural order of things depends on how you think about the relationship between knowledge and obligation. The European eel is a warning about the limits of management without understanding. We cannot set a sustainable harvest level for an animal whose population dynamics we cannot model because we cannot observe its reproduction. We cannot breed it in captivity to supplement wild populations. We can only reduce harvest and hope that the ocean conditions affecting larval survival improve. This is not wildlife management. It is wildlife prayer. The eel is the clearest example of a species that we have been extracting commercially for 1,000 years while remaining fundamentally ignorant of how it works. The ignorance did not matter when the population was large enough to absorb the extraction. It matters now. Chapter 37. The shark. The predator that has outlived 5 extinctions. 450 million years. The shark is older than the trees. Forests first appeared on Earth approximately 385 million years ago. Sharks have been swimming in the world's oceans for approximately 450 million years, longer than any other major group of jawed vertebrates still alive today. They survived the late Devonian extinction event. They survived the Permian extinction, which killed approximately 96% of all marine species. They survived the Triassic-Jurassic extinction. They survived the Cretaceous extinction that eliminated the dinosaurs. They survived each of these catastrophes essentially unchanged, same body plan, same predatory ecology, same sensory systems, because the ecological niche of an apex predator in open water is stable enough that a design perfected hundreds of millions of years ago requires no significant revision. The shark's longevity is not luck. It is the result of a suite of adaptations that have proven robust across more geological time than almost any other vertebrate body plan. The dermal denticles that cover the shark's skin and reduce drag at speed. The lateral line that detects pressure changes in water from hundreds of meters away. The ampullae of Lorenzini that detect the electromagnetic fields produced by the muscle contractions of nearby animals. The liver, which in some species constitutes up to 30% of body weight and provides buoyancy without the swim bladder that other fish require. These are not primitive features waiting to be replaced by something better. They are optimized solutions that have not needed replacement. The apex predator's function. Removing apex predators from marine ecosystems does not simply create an ecological vacancy. It triggers a cascade of effects that restructures the entire food web, a process that ecologists, borrowing from physics, call a trophic cascade. When large shark populations in the northwestern Atlantic were reduced by overfishing in the late 20th century, their prey rays and smaller sharks increased dramatically. The rays, newly abundant, devastated shellfish populations along the eastern seaboard. Scallop fisheries that had sustained coastal communities for generations collapsed within years of the shark population decline. The mechanism is not obvious and the timescale is long enough that connecting cause and effect requires careful research rather than casual observation. This is why apex predator regulation of ecosystems was underappreciated for so long. The shark does not directly manage the scallop population. It manages the ray population that manages the scallop population. Remove the shark and you do not immediately see scallop loss. You see ray increase. The scallop collapse follows years later, and by then the connection to the missing shark is not visible to anyone who has not been watching the whole chain. The shark is older than trees. It has survived 5 mass extinctions, essentially unchanged, because the design worked. Whether it outlasts us, with our fin trade and our fear, remains, for the first time in 450 million years, genuinely uncertain. David Schiffman, Why Sharks Matter, 2022. The fear industry. Approximately 70 to 100 people are bitten by sharks annually worldwide, of whom fewer than 10 die. Sharks kill fewer people per year than cows, horses, dogs, hippos, or bees. They kill dramatically fewer people than cars, swimming pools, or lightning. The statistical insignificance of shark attacks on human safety does not prevent them from generating disproportionate media coverage, public fear, and political pressure for shark culling programs. Peter Benchley, whose 1974 novel Jaws and its subsequent film adaptation fundamentally shaped public perception of sharks, spent the last decades of his life as a shark conservation advocate, arguing that the fear his fiction had generated was driving policy that made no rational sense. The shark cull programs introduced in Western Australia and elsewhere following fatal attacks have been opposed by marine biologists on the grounds that they kill the wrong species, in the wrong places, and are ineffective at reducing attack risk while producing significant collateral damage to marine ecosystems. The shark is being killed, in part, because of a novel. The finning crisis. Between 63 and 273 million sharks are killed annually, the vast majority for the fin trade. Shark fin soup, a Chinese delicacy associated with wealth and status, drives a market that targets sharks specifically for their fins, which are sliced off while the animal is still alive, after which the body is thrown back into the ocean to drown. The practice is banned in many countries but remains common in international waters and in jurisdictions where enforcement is weak. Shark populations globally have declined by 70 to 71% since 1970. Several open-ocean shark species have declined by more than 90%. An animal that survived 5 mass extinctions is being eliminated, in decades, by a market for a single luxury ingredient. The geological record shows that sharks have outlasted everything the Earth has thrown at them. Whether they outlast us remains, for the first time in 450 million years, genuinely uncertain. Chapter 38. The Peacock. The bird that explained evolution. Darwin's headache. In 1860, Charles Darwin wrote to the botanist Asa Gray that the sight of a peacock's feather made him physically ill. The reason was theoretical rather than aesthetic. The peacock's tail, enormous, unwieldy, metabolically expensive, and apparently useless for anything except display, seemed to contradict natural selection. If survival of the fittest was the mechanism of evolution, how had an adaptation that made its bearer slower, more visible to predators, and more vulnerable to starvation evolved at all? The peacock's tail was beautiful precisely because it was extravagant. Evolution was supposed to be about efficiency. The peacock was the argument against efficiency. Darwin's resolution was sexual selection, a mechanism distinct from natural selection, in which traits evolve not because they help an organism survive but because they help it reproduce. A peacock with a larger, more elaborate tail was chosen more frequently as a mate by peahens. His genes, including the genes producing the elaborate tail, were passed on more frequently. Over generations, the tail became more elaborate, not despite its cost but because of it. The cost was the signal. Only a genuinely healthy, well-nourished, parasite-free male could afford the metabolic investment. The tail was honest advertising. The honest signal. The peacock's tail, under Darwin's sexual selection framework, is a handicap. This sounds paradoxical, but it is the foundation of a branch of evolutionary biology that has produced some of the most counterintuitive and robust predictions in the field. The biologist Amos Zahavi formalized the idea in 1975 as the handicap principle. A costly signal is honest precisely because it is costly. A fake could not afford it. A healthy, fit individual can. The signal's reliability is guaranteed by its expense. The peacock's tail is now understood as one example of a general evolutionary phenomenon. The elaborate calls of frogs and birds in breeding season, the bright colors of many poisonous animals, the complex nuptial gifts of certain insects, the antlers of male deer, all of these are honest signals of quality, maintained at genuine metabolic cost, that cannot be easily faked. The theory that Darwin found so troubling turned out to be not an exception to natural selection but an extension of it. Survival is not the only currency. Reproduction is the currency, and the peacock's tail is a check that only the healthy can cash. Darwin found the peacock's tail physically disturbing. It contradicted survival of the fittest. His resolution, sexual selection, turned out to be as radical as natural selection itself. The peacock resolved the contradiction by being beautiful at a cost that only the fit could pay. Charles Darwin, The Descent of Man and Selection in Relation to Sex, 1871. The peahen's choice. What the peahen is selecting for when she chooses a male with a better tail remains an active research question. Early work by the biologist Marion Petrie found that pea chicks fathered by males with more elaborate tails had better survival rates in the wild, suggesting that the tail was indeed tracking some heritable quality. Later work has found more mixed results, and the question of exactly what the tail advertises, parasite resistance, immune function, developmental stability, genetic diversity, is not definitively settled. What is settled is that the peahen chooses. She examines multiple males, often over several days. She appears to evaluate the number of eye spots in the tail fan, the symmetry of the display, and possibly the quality of the male's calls and behavior. The decision is hers. The peacock performs, the peahen selects. In this arrangement, which appears across hundreds of species with similar sexual dimorphism, the supposedly passive female is actually the agent driving evolutionary change. Darwin understood this, and it was as radical an insight as natural selection, and considerably less well remembered. The peacock in civilization. The peacock has been a symbol of royalty, divinity, and immortality in cultures from ancient Persia through Christian Europe. Alexander the Great imposed the death penalty on anyone who killed a peacock in conquered territories. Roman senators kept peacocks as status symbols. Peacock brains and tongues appeared on the menus of the most extravagant banquets. In Christian iconography, the peacock's ability to molt and regrow its tail each year made it a symbol of resurrection. In Islamic art, peacocks flanking a chalice or fountain appear as symbols of paradise. The bird that gave Darwin a headache and resolved it has been a human obsession for at least 3,000 years. We have always understood, without the vocabulary of evolutionary biology, that the peacock's tail means something. Darwin gave us the vocabulary. The bird had been making its argument since long before he was born to hear it. The peacock's appearance in human symbolic systems across cultures that had no contact with each other is an example of convergent symbolism. Independent cultures, encountering the same animal, arriving at similar interpretations of its meaning. The elaborateness of the tail reads as abundance and vitality to human perceptual systems that evolved to associate visual complexity with health and fertility. Darwin's sexual selection theory explains why the tail means what it means to peahens. The history of human symbolism suggests that it means approximately the same thing to us, that the response to elaborate display is deep enough in primate perceptual systems to have been culturally reinvented, independently, dozens of times across human history. Chapter 39. The Snail. The slow creature that fed empires. Roman snail farms. The Romans ate snails obsessively. Marcus Terentius Varro, writing in the 1st century BCE, described elaborate snail enclosures, carcliaria, that maintained different species in separated sections, fed on specific diets to improve flavor, and supplied the finest Roman tables with a product that Varro described as a luxury of considerable value. The land snail species most prized by Roman epicures, Helix pomatia, the Roman snail, still found across Europe, was consumed in such quantities that archaeologists have found its shells in large concentrations at Roman sites from Britain to North Africa. The Romans were not merely consuming snails as a convenient wild food. They were farming them systematically, selecting for size and flavor, and supplying a market that apparently paid premium prices for the best specimens. The carcliarium was a recognized agricultural enterprise, described in agricultural manuals alongside fish ponds, apiaries, and poultry yards as a profitable investment for an estate owner with the appropriate land. The escargot that appears on contemporary French menus as a luxury appetizer is the direct descendant of a Roman farming system 2,000 years old. The purple that ruled the world. The most economically significant snail in history was not eaten. It was squeezed. The sea snail Murex brandaris and related species of the genus Hexaplex produces a mucus that, when exposed to sunlight and air, turns a distinctive purple. Tyrian purple, produced from these snails along the Phoenician coast, was the most expensive dye in the ancient world. Producing a single gram of dye required approximately 9,000 snails. A pound of wool dyed Tyrian purple cost the equivalent of several months of wages. Roman emperors reserved the color exclusively for their own use. Wearing purple without imperial authorization was, in some periods, a capital offense. The snail-based purple industry dominated the economy of Phoenicia, the coastal cities of what is now Lebanon, for over 1,000 years. Sidon and Tyre were wealthy cities whose wealth came entirely from snails. The archaeological evidence is olfactorily suggestive. Processing snails in the quantities required to produce commercial amounts of dye generates an extraordinarily powerful smell, and the midden heaps of crushed murex shells outside Phoenician cities were large enough to change the local topography. The color that signified imperial power had its origin in an industrial process that smelled catastrophic. Producing a single gram of Tyrian purple required approximately 9,000 snails. The color that Roman emperors reserved for themselves under penalty of death had its origin in an industrial process that smelled catastrophic. Pliny the Elder, Natural History, 77 CE. The snail that ate the world's islands. In 1955, the giant African land snail Achatina fulica, native to East Africa, was introduced to Hawaii as a potential food source. It escaped. By the 1970s, it had spread to most of the Pacific Islands, parts of the Caribbean, and significant areas of Southeast Asia, consuming agricultural crops and native vegetation wherever it established itself. Attempts to control it by introducing the carnivorous rosy wolf snail Euglandina rosea produced a cascade. The wolf snail largely ignored the giant African land snail and instead ate through the native snail fauna of Hawaii and the Pacific Islands, driving dozens of species to extinction. It is regarded as one of the most catastrophic biological control failures in recorded history. The giant African land snail also carries a parasitic nematode, Angiostrongylus cantonensis, that causes rat lungworm disease in humans, a parasitic meningitis that can cause paralysis and death. The snail introduced as food became a vector for a serious human pathogen, an agricultural pest, and an ecological disaster simultaneously. The history of species introductions contains many cautionary tales. The giant African land snail is among the most comprehensive. What snails do. The ecological role of snails in native ecosystems is substantial and poorly appreciated. Land snails are primary decomposers, breaking down leaf litter and dead wood and recycling nutrients into the soil. They are calcium sources for birds and small mammals. They are seed dispersers for certain plant species. In freshwater ecosystems, aquatic snails graze algae from rocks and aquatic plants, maintaining the water clarity that other species depend on. The snail moves through the world at a pace that makes it easy to overlook. It does not command attention. It does not appear in military histories or economic treatises except in the specific cases where it produced dye or fed armies. Its contributions to soil health, nutrient cycling, and the functioning of the ecosystems that agriculture depends on are real but invisible. This is true of many of the animals that matter most. The slow ones, the small ones, the ones that do their work without drama, they are doing the work that the visible world depends on. The snail's obscurity in discussions of ecological importance reflects a broader pattern in how we think about wildlife. Large, charismatic, visibly active animals command conservation attention. Snails, along with the insects, nematodes, fungi, and other invertebrates that perform most of the soil's biological work, remain largely invisible to the public and significantly underrepresented in conservation funding. Invertebrate species account for approximately 97% of all animal species, perform a disproportionate share of the ecosystem services that agriculture and human welfare depend on, and receive a small fraction of the conservation attention and resources devoted to vertebrates. The snail is a symbol of this imbalance, slow, uncharismatic, genuinely important, and almost entirely overlooked. Chapter 40. The Lion. The symbol that outlasted the empires it represented. The king of beasts in reality. The lion is not the most dangerous predator in Africa. That distinction belongs to the hippopotamus or the Nile crocodile, depending on how you measure it. The lion is not the fastest, the cheetah is faster. It is not the most numerous large predator, spotted hyenas are, in most African ecosystems, more abundant. What the lion has, beyond genuine physical power, is a combination of visual presence and social behavior that makes it uniquely compelling to human observation. The manner, which amplifies apparent size. The roar, audible at 5 miles, which announces presence before the animal is seen. And the pride structure, which allows coordinated hunting of prey much larger than any individual lion could take. Lions are the only truly social cat. They live in groups of up to 30 animals, with a core of related females doing most of the hunting and males defending the territory and the cubs. The social structure is not the romantic monarchy that human mythology has imposed on it. The king of beasts is, in practice, a coalition of males who hold a territory for approximately 2 to 3 years before being displaced by younger males, and who spend most of their time sleeping. The females do the work. The males provide the defense and the genetic diversity. The symbolism and the reality have never been the same animal. The symbol. The lion appears in human symbolic art earlier than almost any other animal. Lion figurines from Swabian Jura in Germany, carved from mammoth ivory, date to approximately 40,000 years ago. The Lion Gate at Mycenae, dated to approximately 1250 BCE, is among the oldest monumental sculptural programs in Europe. Richard I of England was called Richard the Lionheart in the 12th century. The British royal coat of arms has featured lions since the 12th century. England, Scotland, Flanders, Denmark, Sweden, Norway, Ethiopia, Sri Lanka, and Morocco have all featured lions on their national symbols. The lion's meaning has been consistent across cultures that had no contact with each other: power, courage, royalty, divine authority. The paradox is that most of these symbolic traditions developed in cultures where lions were absent. Medieval English kings adopted the lion as a symbol of royal power, even as English lions, the cave lions that had lived in Britain until approximately 13,000 years ago, were long extinct. The Romans imported lions for the arena and knew the animal well. Their successors knew it primarily through the symbol that Rome had propagated. The lion became more culturally powerful as it became more physically distant, present in the imagination precisely because it was absent from the landscape. The lion is absent from British landscapes and has been for 13,000 years. It appears on the royal coat of arms, the national flag, and the currency. The symbol outlasted the animal by 10 millennia and shows no sign of fading. Cynthia Moss, Lion Ecology Research, Amboseli, Kenya. The range that shrank. Lions once ranged across Africa, the Middle East, southern Europe, and into India. The population that survived into the modern era in India was reduced to a single remnant population in the Gir forest of Gujarat, fewer than 50 animals at the beginning of the 20th century, protected by the local Maharaja who valued them for hunting. Conservation efforts have brought this population to approximately 600 animals, still confined to a single protected area, still representing the entire Indian population. African lion populations have declined from an estimated 200,000 in the 1970s to approximately 20,000 to 25,000 today. The decline is driven by habitat loss, human-wildlife conflict as expanding agricultural settlements push into lion territory, and the bushmeat trade that reduces the prey base. The conflict between lions and the livestock owners who share their landscape is essentially intractable without economic solutions. Lions kill livestock, farmers kill lions, and no conservation policy survives contact with a family that has lost its livelihood to a predator and received nothing in return. The canned lion. South Africa's captive lion breeding industry, often called canned hunting, maintains approximately 12,000 lions in private facilities, where they are bred for petting by tourists, harvested for the Asian bone trade as substitutes for tiger bone, and released into enclosed areas to be shot by paying hunters. The industry is legal, generates significant income, and is vigorously opposed by conservation biologists who argue that it provides no conservation benefit to wild populations and creates demand for lion products that can be supplied by poaching wild animals when captive animals are unavailable. The lion that has meant royalty, divinity, and power to more cultures than any other animal is, in 2024, being bred in cages for pet tourism and bones. The symbol outlasted the empires that adopted it. Whether the animal outlasts the symbol is the question that the 21st century is answering. The gap between the lion's cultural meaning and its commercial treatment is one of the starker contradictions in contemporary wildlife economics. The animal that has signified royal power and divine authority across 3,000 years of human culture is being bred in cages for petting and bones. The symbol survives on national flags and currency while the animal that inspired it is confined in facilities optimized for commercial extraction. This is not unique to the lion, the same pattern applies to many species whose cultural prestige has not protected them from economic exploitation. What is unusual about the lion is the scale of the gap between what the symbol means and what is being done to the animal. Chapter 41. The Tiger. The Ghost that Guards the Forest. 9 subspecies, 3 remaining. The tiger is 9 subspecies of which 6 are critically endangered, 1 is extinct in the wild, and 2, the Siberian and the South China, number in the dozens of wild individuals. The Bengal tiger, the most numerous, has a wild population of approximately 3,000. The total wild tiger population across all remaining subspecies is approximately 5,574 animals, according to the most recent comprehensive count. A century ago, tigers were distributed from Turkey to the Russian Far East and throughout Southeast Asia. Their current range is fragments, scattered protected areas separated by agricultural and urban development that tigers cannot cross without being killed. The tiger's decline is one of the most documented wildlife collapses in history, which makes it all the more striking that it has continued. The Bengal tiger was predicted to be extinct in the wild by 1990, then by 2000, then by 2010. Repeated predictions of imminent extinction have not been fulfilled, partly because of genuine conservation effort and partly because tigers are more persistent than their circumstances warrant. This resilience is worth noting. The tiger is not a fragile specialist. It is a generalist apex predator capable of surviving on a wide range of prey in a wide range of habitats. What it cannot survive is a human population of 8 billion people competing for the same land. What the tiger does. In the ecosystems where tigers are present, their effect on prey populations, primarily deer, wild pigs, and cow, regulates overgrazing and maintains forest structure in ways that downstream species depend on. The Sundarbans mangrove forest, shared between Bangladesh and India, supports the world's only tiger population adapted to saltwater environments. The tiger's presence in the Sundarbans has been credited with regulating deer populations in ways that maintain the mangrove structural integrity, the dense root systems that protect coastal Bangladesh from cyclone surge and rising sea levels. This is not a theoretical relationship. Bangladesh is one of the most flood-vulnerable countries in the world. The mangrove forests that provide its primary coastal protection are maintained, in part, by a population of approximately 100 tigers. The economic value of that coastal protection, measured in terms of the damage that cyclones would do to an unprotected coast, is enormous. The tiger is, in this calculation, a piece of national infrastructure. Whether this framing changes the political calculus of tiger conservation in a country where tigers do occasionally kill people remains to be seen. Bangladesh's coastal protection from cyclones depends, in part, on mangrove forests maintained by approximately 100 tigers. The tiger is not just a symbol. In the Sundarbans, it is a piece of national infrastructure. Atul Kaushik and Jared Diamond, Tiger Ecology Literature Synthesis. The bone trade. Traditional Chinese medicine has used tiger bone as a treatment for joint pain and arthritis for at least 2,000 years. The demand for tiger bone, and for other tiger parts, skin, teeth, claws, fat, has driven poaching throughout the range countries despite international trade bans under CITES since 1975. The trade did not stop. It went underground, became more profitable as tigers became scarcer, and expanded to include tiger farms in China and Southeast Asia that raise captive tigers for the legal domestic market while creating cover for wild-caught animals to be laundered through the same supply chains. The bone trade's persistence illustrates the limitation of conservation strategies that treat demand as fixed rather than subject to change. Supply-side measures, protected areas, anti-poaching patrols, CITES enforcement are necessary but insufficient when the underlying demand continues. Demand reduction campaigns in China and Vietnam, targeting the consumers of tiger products rather than the poachers who supply them, have shown more promising results in recent years. Whether they can reduce demand faster than the last tigers can be killed is the race that tiger conservation is running. Project Tiger. India's Project Tiger, launched in 1973 by Prime Minister Indira Gandhi, was among the first national programs to designate specific protected areas for a single species. The program established tiger reserves across India with restricted human habitation and intensive management. India's tiger population, which had fallen to approximately 1,800 animals by 1972, has recovered to approximately 3,167 according to the 2022 census, the largest wild tiger population in the world and the only significant recovery story in the species' recent history. Project Tiger's success is partial and contested. The reserves it created displaced hundreds of thousands of Adivasi indigenous forest-dwelling communities from their traditional territories, often without adequate compensation or resettlement support. The conservation gain was produced at a social cost that is still being reckoned with. The tiger, in India as elsewhere, exists at the intersection of ecology, politics, tradition, and poverty, and no conservation strategy that ignores this intersection has ever worked. The social cost of Project Tiger, the displacement of Adivasi communities from tiger reserves, is a version of a conflict that plays out wherever large-scale conservation competes with the land rights of people who have lived in those landscapes for generations. The framework that pits wildlife against people is consistently counterproductive. Reserves without community support are more vulnerable to poaching, not less, because the communities living around them have no stake in their success. The most successful long-term conservation programs globally are those that have found ways to make local communities economic beneficiaries of the wildlife they are asked to coexist with. Tiger conservation that displaces its human neighbors is buying short-term population numbers at the cost of long-term sustainability. Chapter 42. The coral. The animal that holds the ocean together. Not a plant. Coral reefs are the largest biological structures on Earth, visible from space, home to approximately 25% of all marine species, and built entirely by animals. The coral polyp, a small, soft-bodied animal related to the jellyfish and sea anemone, constructs a calcium carbonate skeleton around its base and lives within it. When the polyp dies, its skeleton remains. New polyps grow on top of old skeletons. Over thousands of years, these accumulated structures form the reefs that host ecosystems of complexity and productivity exceeding most terrestrial environments. The confusion between coral and plant is understandable. Coral doesn't move, it photosynthesizes, or rather, it hosts photosynthesizing organisms. The coral polyp's tissues contain symbiotic algae called zooxanthellae, which perform photosynthesis and pass the products to their coral host. The zooxanthellae provide approximately 90% of the coral's energy requirements. This arrangement is the foundation of reef productivity. The algae convert sunlight into the chemical energy that feeds the entire reef ecosystem, starting with the coral itself. Bleaching. When seawater temperatures rise above the threshold that zooxanthellae can tolerate, typically about 1 degree Celsius above the maximum summer temperature for a sustained period, the algae produce toxins and the coral expels them. Without its algae, the coral loses its color and its primary energy source simultaneously. The white skeleton beneath the transparent tissue is what becomes visible. Bleaching. A bleached coral is not dead. If temperatures return to normal quickly enough, zooxanthellae can recolonize and the coral can recover. If the elevated temperature persists, the coral starves and dies. The 2016 bleaching event on the Great Barrier Reef was the most severe in recorded history. Approximately 50% of the shallow water corals in the northern section died. The 2017 event added further mortality in the central section. The 2020, 2021, and 2022 events extended damage further. The Great Barrier Reef has now experienced 6 mass bleaching events in 25 years. The first occurred in 1998. The frequency is accelerating because ocean temperatures are rising, and the recovery time between events is shrinking below the period required for coral to regrow. Coral reefs cover 0.1% of the ocean floor and support 25% of marine species. At 2 degrees Celsius of global warming, more than 99% will be severely degraded. The ocean's most productive ecosystem is being turned off by a dial we are still choosing not to turn. IPCC Special Report on the Ocean and Cryosphere, 2019. What reefs provide? Coral reefs cover approximately 0.1% of the ocean floor but provide food and income to approximately 1 billion people. They protect coastlines from wave energy. A reef can dissipate more than 97% of wave energy, protecting the coastal communities behind it from storm surge, erosion, and flooding. The economic value of this coastal protection service has been estimated at $400 billion per year globally. The fisheries that coral reefs support, including reef-associated species harvested across the Indo-Pacific and Caribbean, feed hundreds of millions of people. The medical value is less quantified but real. Coral reef organisms have produced compounds used in treatments for cancer, HIV, cardiovascular disease, and bacterial infections. The unusual chemistry of organisms adapted to the specific conditions of the reef environment, intense UV exposure, precise salinity ranges, the chemical signaling systems of dense ecological communities has proven to be a productive source of pharmaceutical leads. The reef's biological diversity is, among other things, a pharmaceutical library that we have barely opened. The prognosis. The Intergovernmental Panel on Climate Change estimates that at 1.5 degrees Celsius of global warming above pre-industrial levels, 70 to 90% of the world's coral reefs will be severely degraded. At 2 degrees Celsius of warming, more than 99% will be severely degraded or gone. Current emissions trajectories place the world on a path toward 2.5 to 3 degrees Celsius of warming by the end of the century. Coral reefs have survived previous periods of environmental stress, but those events unfolded over thousands to millions of years, allowing ecological adaptation. The current warming is occurring over decades, too fast for evolutionary adaptation, and faster than the management interventions currently available can offset. Coral restoration, growing coral fragments in nurseries and transplanting them to damaged reefs exists and works at small scales. Selective breeding programs are producing more heat-tolerant coral strains. Experimental shading of reefs to reduce temperature stress is under investigation. All of these interventions are real and worth pursuing. None of them can substitute for reducing the emissions that are heating the ocean. The coral cannot negotiate the terms of its survival. We can. Whether we will is the question that every bleaching event is asking us to answer. The phrase coral reef under climate change tends to produce a specific emotional response in people who have been paying attention, a mixture of grief and helplessness that is difficult to act on. The scale of the threat is global. The intervention required rapid decarbonization of the world economy is the most politically difficult problem our civilization has ever faced. The reef cannot wait for the politics to resolve. It is bleaching now, at a rate that accelerates with each degree of warming. What can be done at the local level, reducing pollution, protecting reef fish populations, establishing marine protected areas, buys time. It does not change the trajectory. The coral is teaching us, in real time, what the limits of local action look like when the threat is planetary. Chapter 43. The Passenger Pigeon. The Extinction That Woke the World. 3 billion birds. In 1813, the ornithologist Alexander Wilson watched a flock of passenger pigeons fly over Kentucky for hours. He estimated the flock to be 1 mile wide and 240 miles long, containing approximately 2.2 billion birds. John James Audubon described a similar flock that darkened the sky for 3 days. The passenger pigeon, Ectopistes migratorius, was not merely abundant. It was, by most estimates, the most numerous bird species that has ever existed. At its peak, it may have constituted between 25 and 40% of the total bird population of North America. The pigeon's abundance was a function of its ecology. It traveled in massive flocks that overwhelmed the carrying capacity of any local predator population, so that the losses to predation in any given flock were individually small even if absolutely large. It bred in enormous communal colonies, sometimes hundreds of square miles of nesting activity, where individual vigilance against predators was supplemented by the collective safety of sheer numbers. The strategy worked perfectly for millions of years against every predator the North American ecosystem had produced. The hunting. The strategy failed against market hunters with railroads. The passenger pigeon was edible, abundant, and cheap to kill in enormous numbers. Railroad access to breeding colonies in the 1860s and 1870s allowed hunters to ship barrels of pigeons to eastern cities faster than the birds could reproduce. Breeding colonies were disrupted when hunters arrived in force, pigeons abandoned nests, chicks died, reproductive success collapsed precisely in the locations where it was most concentrated. The scale of the slaughter was industrial. A single hunter could kill hundreds of birds per day using nets, traps, and later shotguns. Professional hunting operations killed millions per season. The species that had darkened the sky for days was reduced to scattered remnant flocks within 2 decades of the railroad reaching its range. The last significant flock was reported in 1896. The last wild individual was shot in 1900. The last passenger pigeon on Earth, a captive female named Martha, held at the Cincinnati Zoo, died on September 1, 1914. The passenger pigeon went from 3 billion individuals to 0 in 50 years. Martha, the last one, died at the Cincinnati Zoo on September 1, 1914. Her death was news because it demonstrated that billions could become nothing within a lifetime. Joel Greenberg, A Feathered River Across the Sky, 2014. What changed? Martha's death was news. It was treated as news not primarily because of conservation sentiment. The conservation movement in 1914 was nascent, focused mainly on game species and national parks, but because the passenger pigeon's extinction demonstrated something that most people had considered impossible, that an animal present in billions could be eliminated entirely within a single human lifetime. The extinction of the passenger pigeon accelerated the development of the conservation movement in the United States and internationally. The Migratory Bird Treaty Act of 1918, one of the first federal wildlife protection laws in American history, was passed in part as a direct response to the pigeon's extinction. Aldo Leopold, who as a young man had seen the last Wisconsin flocks, later made the passenger pigeon a central example in a Sand County almanac of what the industrial age had cost the natural world. The pigeon did not die to teach us a lesson. But the lesson was learned. De-extinction. The passenger pigeon is now a target of de-extinction research. The Revive and Restore organization is working to reconstruct the passenger pigeon's genome using genetic material from museum specimens and the closely related band-tailed pigeon. The project aims to edit band-tailed pigeon cells to carry the key genetic variants that distinguish the passenger pigeon, develop the engineered cells into viable birds, and eventually release them into North American forests. The scientific challenges are significant. The passenger pigeon's sociality, its dependence on enormous flock dynamics for breeding success, may not be reproduced by a small founder population. The forests it lived in have changed substantially since 1914. Whether a reconstructed passenger pigeon would be ecologically functional or merely a spectacle is genuinely unknown. What is certain is that the attempt reflects something new in human consciousness about extinction, a recognition that what we destroyed, we might have an obligation to attempt to restore. Whether we can is a scientific question. Whether we should is a philosophical one that the passenger pigeon made it necessary to ask. The broader question that de-extinction raises, whether we have obligations to species we have driven to extinction, has no consensus answer. The passenger pigeon did not choose to go extinct. Its extinction was not a natural event. It was a consequence of specific human decisions made for economic reasons, in the knowledge that the birds were declining and without meaningful effort to stop the decline until it was complete. Whether this history creates an obligation to attempt restoration is a question about the relationship between historical harm and present responsibility that conservation ethics has not fully worked out. The Pigeon De-Extinction Project has at least made the question unavoidable. Chapter 44. The Dodo. The bird that taught us what we were losing. The island without predators. The dodo, Rhaphis cucullatus, evolved on the island of Mauritius in the Indian Ocean over approximately 25 million years of island isolation. In the absence of mammalian predators, it lost the capacity for flight, which requires an enormous metabolic investment that is only worth maintaining if you need to escape something or travel distances that walking cannot cover. The dodo walked. It ate fallen fruit, nuts, seeds, and roots. It nested on the ground. It had no behavioral repertoire for avoiding the kind of predator that Dutch sailors, their rats, and their pigs represented when they arrived on Mauritius in 1638. The dodo was not stupid, though the word has become synonymous with failure. It was optimized for an environment that had not contained terrestrial predators. It approached Dutch sailors with curiosity rather than flight because nothing in its evolutionary history had taught it that large, upright animals were dangerous. This was not stupidity. It was a rational response to the world as it had existed for millions of years. The world changed in 1638, and the dodo had no time to adapt. The extinction nobody noticed. The dodo was extinct by approximately 1680, within 40 years of European contact. The hunters were not only Dutch sailors, introduced rats, pigs, and monkeys ate eggs and chicks from the ground nesting colonies, removing the next generation even when adults escaped hunting. The species that had been stable for millions of years was gone within 2 human generations. What is remarkable about the dodo's extinction is how little attention it received at the time. There was no mourning, no record of the last individual, no sense that something irreversible had happened. The dodo appeared in a handful of Dutch illustrations, was brought to Europe as a curiosity on at least one occasion, and then ceased to exist. The concept of extinction, the permanent elimination of a species, was not yet part of scientific or cultural vocabulary. The 18th century naturalist who would have been most interested, Linnaeus, was born 30 years after the dodo disappeared. He never knew it had existed. The dodo was extinct within 40 years of first European contact. Nobody noticed. The concept of extinction did not yet exist. The bird that taught us what extinction meant was gone before we had the word for it. Errol Fuller, Dodo, A Brief History, 2002. How the dodo became a symbol. The dodo's second life as a cultural symbol began in the 19th century, when its bones were excavated from Mauritian swamps and reconstructed for European natural history museums. Lewis Carroll put a dodo in Alice's Adventures in Wonderland in 1865. Carroll, whose real name was Dodgson, may have identified with the bird, or may simply have known the Oxford Natural History Museum's dodo specimen well. The phrase "dead as a dodo" entered common usage, and the bird became the universal symbol of extinction through stupidity, an ironic fate for an animal whose stupidity was simply insufficient wariness of a predator it had never encountered. The dodo's cultural afterlife has been more useful than its actual life. As the first extinction that Europeans could clearly attribute to human action, even if the attribution was not made immediately, it established the template for how we think about species loss. Every subsequent extinction has been measured against the dodo: how recent, how preventable, how stupid. The bird has been more useful dead, as a cautionary symbol, than it ever was alive on Mauritius, where it was simply another animal going about its business. What the dodo is now. The dodo's bones, preserved in museums across Europe, have become increasingly valuable as DNA sequencing technology improves. Recent work on ancient dodo DNA has confirmed its relationship to Nicobar pigeons and established its evolutionary history with more precision than earlier morphological studies allowed. The dodo is now among the extinct species being considered for de-extinction programs, though its island isolation and specialized ecology create challenges that the passenger pigeon program does not face. Mauritius itself has become a test case for island restoration ecology. The removal of introduced mammals from small islands and reserves, the restoration of native vegetation, and the reintroduction of surviving relatives of extinct species as ecological substitutes. The Aldabra giant tortoise has been introduced to Mauritius as a substitute for the extinct giant tortoises that the dodo's ecosystem once included. The dodo's island is being rebuilt, without the dodo, as a demonstration that what was broken can be partially repaired. It cannot be fully repaired. But partial is better than nothing. The dodo's extinction and its subsequent elevation to universal symbol of human-caused extinction loss are separated by almost exactly 2 centuries. For the first 100 years after its disappearance, the dodo was largely forgotten, a curiosity that had briefly appeared in Dutch natural history records and then vanished without cultural consequence. The Victorian era's excavation of its bones and its placement in natural history museums transformed it from a forgotten bird into an icon. The dodo became famous, paradoxically, because of its extinction, because the reconstructed skeleton in the museum case made visible what an animal's complete disappearance looked like. Every subsequent extinction has stood in the dodo's shadow. Chapter 45. The Vulture. The Undertaker at the Edge of Civilization. What vultures do. A white-backed vulture can locate a large carcass from the air at distances of up to 30 miles. A group of vultures can strip a 90-pound impala to bones in under 30 minutes. The speed and thoroughness of this processing is not simply efficient. It is epidemiologically critical. Carcasses that are consumed quickly by vultures are carcasses that do not become incubators for anthrax, botulism, or rabies, or water source contaminants, or breeding grounds for the blowflies that spread disease to livestock and wild animals across a landscape. The vulture's digestive system is uniquely adapted to this function. Stomach acids with a pH of approximately 1 more acidic than battery acid kill pathogens including anthrax spores and Clostridium botulinum that would kill virtually any other scavenger. The vulture eats disease and destroys it. In doing so, it provides a sanitation service to the ecosystems it inhabits that has no equivalent among any other group of animals. Researchers studying ecosystems where vulture populations have collapsed have found increased rates of disease in livestock and wild animals, increased time for carcass decomposition, and increased populations of scavenging mammals, feral dogs, rats, that are less efficient pathogen destroyers and are themselves significant disease vectors. The diclofenac catastrophe. In the 1990s, the use of the veterinary anti-inflammatory drug diclofenac expanded rapidly across South Asia as a cheap and effective treatment for livestock pain and fever. Diclofenac remains in the tissues of treated animals after death. Vultures that feed on treated carcasses develop acute kidney failure and die within days. The drug is lethal to vultures at concentrations far below those that cause any apparent harm in the livestock for which it was intended. Between 1992 and 2007, 3 vulture species that had been among the most abundant large raptors in the world, the oriental white-backed vulture, the long-billed vulture, and the slender-billed vulture, declined by between 97 and 99.9% across South Asia. The declines were among the fastest of any bird species ever recorded. At the low point, the oriental white-backed vulture had fallen from an estimated 40 million individuals to fewer than 11,000. The drug that caused this was not a toxin designed to kill birds. It was a pain reliever for cattle, with a side effect that turned a continental vulture population to near nothing in 15 years. The diclofenac catastrophe killed 99% of South Asia's vultures in 15 years. The estimated downstream cost in rabies deaths, disease, and livestock losses was $34 billion. A bird provided its sanitation service for free. We found out what it was worth when we accidentally eliminated it. Rees Green et al., Diclofenac poisoning as a cause of vulture population declines, Proceedings of the Royal Society B., 2004. The consequence. The collapse of vulture populations in South Asia produced measurable downstream effects. Feral dog populations in India expanded dramatically in the 1990s and 2000s, feeding on the carcasses that vultures no longer processed. The expansion of feral dog populations increased human exposure to rabies. India already had the world's highest rate of human rabies deaths, and by some estimates contributed to an additional 48,000 human deaths per year from rabies during the period of the vulture decline. The economic cost of the vulture collapse has been estimated at approximately $34 billion in increased veterinary costs, livestock losses to disease, and public health costs. A bird that provided its sanitation service for free, powered by its own biology, turned out to be worth more in straightforward economic terms than the entire veterinary pharmaceutical industry in the region could easily calculate. The recovery. Diclofenac was banned for veterinary use in India, Pakistan, Bangladesh, and Nepal in 2006, following advocacy by conservation organizations that had identified it as the cause of the collapse. Vulture populations have stabilized in some areas since the ban, and captive breeding programs have produced birds for eventual reintroduction. Recovery is slow, Vultures reproduce at very low rates, typically 1 egg per year, and populations that have declined by 99% take decades to recover even under the best conditions. The vulture story is one of the most complete demonstrations of how ecosystem services are valued only when they disappear. No one counted the economic contribution of vultures in South Asia when they were present. The contribution was simply taken for granted, as clean water and breathable air are taken for granted, until the system that produced it failed. The lesson is the same as the oyster, the bee, the mangrove. The services that natural systems provide for free are the most expensive things we can lose. The time required for vulture populations to recover from the diclofenac catastrophe illustrates a general principle in conservation biology. The more slowly a species reproduces, the longer the recovery from any significant population decline, and the more permanent the damage from any event that removes adults faster than they can be replaced. A species that lays 1 egg per year and takes 5 years to reach reproductive maturity cannot absorb mortality at rates that a rabbit could recover from in a season. The conservation triage implicit in wildlife management, which species to prioritize for intervention, which populations to protect at what cost, is partly a calculation about life history. The vulture is expensive to lose and expensive to recover. The drug that caused the collapse cost less than $1 per dose. Chapter 46. The Dog. The animal that made us human. Before the dog, the wolf. The dog was the first. Before the cow, the sheep, the pig, the horse, the chicken, before agriculture itself, before the permanent settlements that agriculture made possible, the dog was already domesticated and already living with humans. Genetic evidence places the divergence of the domestic dog from its wolf ancestors somewhere between 15,000 and 40,000 years ago. The oldest undisputed dog burial, a dog interred with a human at a site in Germany, dates to 14,000 years ago. By the time the first city was built, the dog had been a human companion for millennia. This priority is significant. The dog was not domesticated as a food animal, a fiber producer, a draft animal, or a controlled source of any commodity. It was domesticated as a partner, specifically, as a partner in the hunt. The dog's nose, ears, and speed combined with the human's intelligence, projectile weapons, and group coordination to make the partnership more effective at hunting than either species alone. The human-dog team could track, corner, and bring down prey that neither could have managed independently. For hunter-gatherers living in environments where food was the primary challenge, this was not a luxury. It was a strategic advantage. The invisible selection. The traits that distinguish dogs from wolves were not deliberately selected by early humans. They emerged from the selection pressure of living in human proximity. Wolves that were less fearful, less aggressive, more responsive to human social cues, and more oriented toward humans in general survived and reproduced in the human camp environment better than wolves that were not. Over thousands of generations, these tendencies became more pronounced. The dog is not a tamed wolf. It is a wolf shaped by 10,000 years of selection in an environment where attentiveness to humans was the most important survival trait. The consequence is a suite of behavioral capabilities that wolves do not possess. Dogs follow human pointing gestures, the act of extending an arm and finger to indicate direction, and use them to find hidden food. Wolves trained in identical conditions do not do this. Dogs spontaneously look to human faces for guidance when solving problems they cannot solve alone. Wolves do not do this. Dogs form attachment bonds with humans that show the same biochemistry, oxytocin elevation in both the human and the dog during eye contact, as mother-infant bonds in primates. The dog has been shaped to understand us in ways that no other animal has been. Dogs follow human pointing gestures and use them to find hidden food. Wolves trained in identical conditions do not. The dog has been shaped, over 15,000 years of living in human camps, to understand us in ways that no other animal has been. Brian Hare and Vanessa Woods, The Genius of Dogs, 2013. The jobs. The functional diversity of the domestic dog, the range of work it has been bred to perform, exceeds that of any other domestic animal. Herding dogs, hunting dogs, sled dogs, guard dogs, guide dogs for the blind, search and rescue dogs, detection dogs for drugs and explosives, therapy dogs, military service dogs, medical alert dogs that can detect seizures, hypoglycemic events, or certain cancers before symptoms are apparent to their owners. The list represents thousands of years of deliberate breeding applied to a species whose basic behavioral architecture made all of these specializations possible. Guide dogs for the blind were first formally trained in Germany after World War I to help soldiers blinded in combat. The program was introduced to the United States in 1929, producing a partnership between animal and human that has enabled independent mobility for hundreds of thousands of people over the century since. The explosive detection dogs deployed in military and security operations save lives in a manner that no mechanical system has replicated at comparable cost and accuracy. The cancer detection research, still in early stages, has identified dogs that can detect lung cancer from breath samples at accuracy rates exceeding standard clinical tests. What we owe. There are approximately 900 million dogs in the world, of which an estimated 700 million are unowned or semi-owned, living in and around human settlements without the care and feeding that owned dogs receive. The conditions in which many of the world's owned dogs are kept, confined, understimulated, isolated from other dogs and from the outdoor environments their physiology was built for, are a source of ongoing ethical debate among veterinarians and animal behaviorists. The animal that we shaped to understand us better than any other animal on Earth, that we selected for dependence on human social contact, that we bred into an emotional partner, this animal deserves consideration that is proportionate to the relationship we built. The dog did not choose to need us. We made it need us, over 15,000 years of selection for exactly that quality. The obligation runs in one direction only. Chapter 47. The Horseshoe Crab. The living fossil that saves your life. 450 million years old. The horseshoe crab is not a crab. It is more closely related to spiders and scorpions than to any crustacean. Its body plan, domed carapace, compound eyes, 10 legs, long tail spine, has remained essentially unchanged for approximately 450 million years. It survived the 5 major mass extinctions that redrew the map of life on Earth. It was present in the oceans before the first amphibian crawled onto land, before trees evolved, before the first dinosaur existed. The horseshoe crab is, in paleontological terms, a success so complete that it required no revision. It is also, at this moment, saving your life. Every injectable drug, every vaccine, every intravenous fluid approved for human use in the United States is tested with a reagent derived from the blood of the Atlantic horseshoe crab, Limulus polyphemus. The test detects endotoxins, the cell wall fragments of gram-negative bacteria that cause fever, septic shock, and death when they contaminate drugs intended to be sterile. It is called the Limulus amebocyte lysate test, or LAL. It is the most sensitive and reliable method of endotoxin detection available, and it has been a regulatory requirement for drug safety testing since 1977. Blue blood. Horseshoe crab blood is blue, the result of hemocyanin, the copper-based oxygen carrier that performs the function hemoglobin performs in vertebrates. It clots almost instantaneously around bacterial endotoxins, a response that the animal appears to have evolved as a defense against bacterial infection in the sediment environments it inhabits. This clotting reaction, extraordinarily sensitive and specific to bacterial contamination, is what makes the blood valuable for pharmaceutical testing. The horseshoe crab blood industry harvests approximately 600,000 animals per year in the United States. Animals are collected from beaches during their spring spawning aggregation, transported to facilities where approximately 30% of their blood volume is drawn, and returned to the ocean. Mortality from the bleeding process is estimated at between 15 and 30%, meaning that between 90,000 and 180,000 animals die annually from the harvest. The blood that saves millions of human lives from drug contamination is extracted from an ancient animal at a cost that the animal is still paying. Every vaccine, every injectable drug approved for human use is tested with a reagent derived from horseshoe crab blood. An animal 450 million years old, unchanged through 5 mass extinctions, is a mandatory component of modern pharmaceutical safety. Carl Zimmer, The Crabs That Bleed for Modern Medicine, The Atlantic, 2019. The Shorebird Connection. The Atlantic horseshoe crab has a second role that has nothing to do with pharmaceuticals. Each spring, horseshoe crabs come ashore on Delaware Bay beaches in one of the largest mass spawning events in the world. Their eggs, laid in sand just above the waterline, billions per season, provide the critical food source for approximately 1 million migratory shorebirds that stop at Delaware Bay during their northward migration. The red knot, in particular, has timed its 10,000-mile migration from Tierra del Fuego to its Arctic breeding grounds to coincide precisely with the horseshoe crab spawning season. The red knot needs to double its body weight in a 2-week stop at Delaware Bay to have the energy reserves to complete its migration and breed successfully. It does this by eating horseshoe crab eggs exclusively. When horseshoe crab populations declined sharply in the 1990s due to overharvesting for bait, egg availability on Delaware Bay beaches dropped. Red knot populations crashed. The bird, which had evolved over millions of years to depend on the predictable abundance of an animal 450 million years old, was caught in a collapse it had no way to prepare for. The synthetic alternative. A synthetic alternative to the LAL test, recombinant factor C, or RFC, has been developed and validated. It does not require horseshoe crab blood. It is manufactured by biotechnology rather than harvest. It is as sensitive as LAL and less variable between batches. The European Pharmacopoeia approved it as an alternative to LAL in 2020. The US FDA has been slower to allow its use in final product testing, due to regulatory processes that are calibrated to assess risk in the context of existing requirements rather than the risks of continuing current practice. The horseshoe crab survived 450 million years of geological change, mass extinctions, and the full history of multicellular life on Earth. It is now facing pressure from pharmaceutical demand and overharvesting that it did not face in any previous era. The synthetic test exists. The transition is slow because regulatory systems change slowly. The horseshoe crab is waiting on the pace of paperwork. The horseshoe crab situation is a case study in regulatory path dependence. The LAL test became the regulatory standard because it was the best available option when the standard was established. Replacing it now requires demonstrating equivalence against a benchmark that has been validated over decades of use, at a regulatory threshold that was not designed with the cost of continued horseshoe crab harvest in mind. The synthetic alternative is arguably better, more consistent, free from the batch-to-batch variability inherent in biological products, not dependent on the availability of a wild animal that is also a shorebird food source. The regulatory process is not wrong to require careful validation. It is simply slower than the problem it is being asked to solve. Chapter 48. The Bison. The animal that was America. 60 million. Before the first Europeans set foot on the Great Plains, North America contained an estimated 30 to 60 million American bison, the largest aggregation of large mammals in the world at the time. The bison shaped the ecology of the plains in ways so fundamental that the grassland ecosystem essentially was the bison, or rather, the bison and the grass were a single system. The bison grazed selectively, creating the mosaic of short and tall grass prairie that hosted hundreds of plant species. They wallowed in depressions that filled with water and became wetlands. Their movement patterns distributed grazing pressure across millions of acres, preventing the overgrazing that stationary livestock produce. The cultures of the Great Plains, the Lakota, Comanche, Cheyenne, Arapaho, Blackfoot, and dozens of others organized their entire existence around the bison. The animal provided food, shelter, tools, clothing, and spiritual meaning. Its bones became needles, knives, and sleds. Its sinew became bowstrings and thread. Its dung fueled fires on the treeless plains. Its hide, stretched over wood frames, became the teepee, a portable dwelling system that allowed communities to follow the herds across hundreds of miles of open landscape each year. The bison was not a resource that these cultures used. It was the foundation on which their civilizations were built. The slaughter. Between 1870 and 1883, the American bison population was reduced from approximately 30 million animals to fewer than 1,000. The slaughter was industrial. Commercial hunters operating with high-powered rifles could kill hundreds of bison per day, and railroad access to the plains allowed the hides to be shipped east to leather markets. The army encouraged the hunting as deliberate policy, recognizing that eliminating the bison would eliminate the economic foundation of the Plains Indian cultures it was simultaneously at war with. General Philip Sheridan reportedly told the Texas legislature in 1875 that the hide hunters were doing more to pacify the Indians than the army, and that they deserved a medal for destroying the commissary. The calculation was correct in its own terms. The destruction of the bison was a deliberate act of ecological warfare. When the bison went, the civilizations that depended on them could not maintain themselves. The Plains tribes were confined to reservations on a timeline that closely tracked the bison's decline. The animal was the target, the cultures that depended on it were the intended casualty. General Sheridan reportedly told the Texas legislature that the hide hunters deserved a medal for destroying the bison, because eliminating the bison eliminated the commissary of the Plains tribes. The slaughter was ecological warfare. The bison was the target, the cultures that depended on it were the intended casualty. Andrew Eisenberg, The Destruction of the Bison, 2000. The Remnant and the Recovery. The 1,000 bison that survived the slaughter, protected in Yellowstone National Park and on private ranches, are the ancestors of all bison alive today. The recovery from this bottleneck is one of the more improbable events in American wildlife history. The current bison population is approximately 500,000 animals, of which roughly 30,000 are in conservation herds managed for genetic diversity. The Yellowstone herd, the only continuously wild population that was never reduced to captivity, numbers approximately 5,000 animals. Indigenous-led bison restoration has been among the most significant developments in the recent history of the species. The Intertribal Buffalo Council, founded in 1992, has worked with 30 tribes across 11 states to re-establish bison herds on tribal lands, both as ecological restoration and as a direct reconnect to the economic and spiritual traditions that the slaughter interrupted. Bison grazing is being studied as a tool for restoring the shortgrass prairie ecosystems of the plains, systems that have been degraded by a century of cattle ranching and wheat farming that replaced the ecological function the bison had performed. The unfinished reckoning. The bison's story is incomplete in a way that the passenger pigeon's is not. The pigeon is gone. The bison is here, in reduced numbers, on a fraction of its former range, subject to debates about management, brucellosis, grazing rights, and the political economy of wildlife conservation in states where cattle ranching is economically and culturally dominant. The bison stands at the intersection of every difficult conversation in American environmental history: the dispossession of indigenous peoples, the replacement of native ecosystems with agricultural ones, the relationship between wildlife restoration and economic development, and the possibility of returning something to a landscape that was deliberately taken from it. The bison does not know any of this. It is simply trying to find grass. The question of whether there is enough grass left, and who it belongs to, is one that only humans can answer and have not yet answered satisfactorily. The bison's recovery is happening simultaneously with an ongoing legal and political reckoning over the treaty rights of the indigenous nations whose territories it historically occupied. Several tribes have asserted treaty rights to bison on public lands that predate the federal statutes governing wildlife management. These claims are being litigated and negotiated in a legal framework that was not designed for the complexity of treaty rights, wildlife management, and ecological restoration intersecting simultaneously. The bison that is being restored to the plains is not being restored to a blank landscape. It is being restored to a landscape with competing claims, contested histories, and living communities whose relationship to the animal was interrupted rather than ended. The restoration is incomplete without the reckoning. Chapter 49. The Nematode. The ruler of the soil. The invisible majority. Take a handful of healthy soil from a garden. In that handful, you are holding approximately 10 billion individual organisms. The majority of them, by number and by metabolic activity, are bacteria. But the most numerous multicellular animals in that handful and on the planet are nematodes, microscopic roundworms, typically less than 1 millimeter long, invisible to the naked eye, present in densities of up to 4.4 million per square meter of topsoil. Nematodes are the most abundant multicellular animals on Earth. They inhabit every ecosystem where water is available: deep sea sediments, polar ice, desert soils, freshwater sediments, and the bodies of virtually every multicellular organism that has ever lived. A single decomposing apple may harbor 90,000 nematodes. The human body typically harbors several species of nematode as routine, mostly harmless, co-inhabitants. Biologist Nathan Cobb, who pioneered nematode research in the early 20th century, wrote that if all other matter in the universe were removed and only nematodes remained, a ghostly outline of the world would still be visible in the form of nematode distribution. This was hyperbole, but calibrated hyperbole. What nematodes do in soil. Soil nematodes perform several of the most important functions in the terrestrial nutrient cycle. Bacterial-feeding nematodes graze on soil bacteria, releasing nitrogen from bacterial cells in a form that plant roots can absorb, a process that provides a significant proportion of the nitrogen available to crops in organic farming systems. Fungal-feeding nematodes regulate fungal populations, preventing any single fungal species from dominating the soil community. Predatory nematodes eat other nematodes, bacteria, and protists, distributing nutrients through the food web and maintaining the diversity of soil microbial communities. The relationship between soil nematode diversity and soil health is measurable and significant. Soils with diverse and abundant nematode communities support more productive plant growth, resist compaction better, cycle nutrients more efficiently, and recover from disturbance faster than soils with impoverished nematode communities. Industrial agriculture, with its tillage, synthetic fertilizers, and pesticides, tends to reduce nematode diversity sharply. The productivity gains of industrial methods are partially offset by the loss of biological services that a functioning nematode community provided for free. Biologist Nathan Cobb wrote that if all other matter were removed and only nematodes remained, a ghostly outline of the world would still be visible. They are the most abundant multicellular animals on Earth. Almost no one knows they exist. Nathan Cobb, Nemas, The New Kingdom of the Animal World, 1914. The Parasitic Minority. Approximately 16,000 nematode species are parasitic, and within this group are some of the most significant human pathogens in the world. Roundworm Ascaris lumbricoides infects approximately 800 million people globally. Hookworm and whipworm infect hundreds of millions more. Filaria nematodes cause lymphatic filariasis elephantiasis, affecting approximately 120 million people. Onchocerca volvulus, transmitted by blackflies, causes river blindness in sub-Saharan Africa and Yemen, with approximately 20 million people currently infected. The burden of nematode disease falls almost entirely on the world's poor. The soil-transmitted helminth infections, roundworm, hookworm, whipworm, are concentrated in tropical and subtropical regions without adequate sanitation. They impair growth, cognitive development, and school performance in children in ways that compound over a lifetime. Albendazole and mebendazole, the drugs used to treat them, are inexpensive and effective. The gap between available treatment and its distribution is a logistics and funding problem, not a scientific one. The nematode that feeds science. Caenorhabditis elegans, a transparent, soil-dwelling nematode 1 mm long, has been the subject of more scientific research per unit body length than almost any other organism on Earth. It was the first multicellular animal to have its genome fully sequenced. It was the organism in which programmed cell death was first characterized, work that led to the 2002 Nobel Prize in Physiology or Medicine. It was used to demonstrate that genes could silence other genes, the discovery of RNA interference, which led to the 2006 Nobel Prize. C. elegans is also the only organism whose complete neural wiring diagram has been mapped every neuron, every synapse, in every individual. The animal has exactly 302 neurons and approximately 7,000 synapses. The wiring diagram is being used as a model for understanding how simple neural circuits produce coordinated behavior, with implications for both neuroscience and robotics. The most studied small animal in the world, invisible to the naked eye, living in the soil beneath your feet, has contributed to 2 Nobel Prizes and is being used to build the foundations of artificial neural networks. Most people do not know it exists. The complete neural wiring diagram of C. elegans, 302 neurons, every connection mapped, has been used as the basis for one of the most ambitious projects in robotics, the Openworm project, which is attempting to simulate the complete nervous system of the nematode in software and use it to control a small robot. Preliminary results have produced robots that exhibit behaviors recognizable from the actual worm's repertoire, avoiding obstacles, seeking food-associated stimuli, displaying the characteristic movement patterns of a worm navigating its environment. Whether this constitutes uploading the nematode's nervous system in any meaningful sense, or simply building a machine that behaves similarly, is a question that the project has made newly urgent. The simplest animal nervous system fully mapped turns out to raise some of the hardest questions in neuroscience. Chapter 50. The Earthworm. Darwin's Last Obsession. The final book. Charles Darwin spent the last 4 decades of his life, intermittently, on earthworms. Between the publication of On the Origin of Species in 1859 and his death in 1882, he conducted experiments on earthworms in his garden at Down House, measuring the rate at which they buried objects, analyzing the composition of their castings, calculating the depth of soil they moved in a year. The Formation of Vegetable Mold Through the Action of Worms, published 6 months before his death in 1881, sold more copies in its first year than any of his previous books except The Origin itself. Darwin's conclusion, laboriously documented over years of observation, was that earthworms had been the primary agent reshaping the surface of the English landscape for millennia, that the level fields of England, the burial of Roman ruins beneath pasture, the slow sinking of ancient monuments into the earth were all the work of earthworms, moving soil particle by particle from depth to surface through their digestion and depositing it as castings above. He calculated that earthworms in English pasture could move approximately 10 tons of soil per acre per year. At this rate, they could bury the surface of a field by an inch in 10 years. The English countryside, Darwin argued, was earthworm-made. The chemistry of the casting. An earthworm's gut is a soil processing factory. Organic matter, dead leaves, fungi, bacteria, plant fragments is ingested along with mineral soil particles, physically broken down by muscular gizzard action, chemically transformed by microbial activity in the gut, and excreted as castings that are chemically distinct from the surrounding soil. Earthworm castings are richer in available nitrogen, phosphorus, and potassium than unprocessed soil. They have a more stable aggregate structure, clumping together in ways that resist erosion and retain water better than loose soil particles. They contain more beneficial microbes and more microbial diversity than the soil that went in. In agricultural soils with healthy earthworm populations, the contribution to soil fertility is measurable and significant. Studies comparing earthworm-rich and earthworm-poor plots of otherwise identical soil have found yield differences of 25 to 50% in favor of earthworm-present plots without any other inputs. The worm is a fertility engine, running on dead organic matter, producing plant-available nutrients as a byproduct, and doing the work that synthetic fertilizers were invented to partially replicate. Darwin spent 40 years on earthworms and concluded they had been the primary agents reshaping the English landscape for millennia. His final book argued that the most profound changes are produced not by dramatic events, but by the patient, continuous work of the ordinary. Charles Darwin, The Formation of Vegetable Mold Through the Action of Worms, 1881. The threats. Earthworm populations in agricultural soils have declined substantially under intensive farming systems. Deep tillage disrupts burrows and kills animals directly. Pesticide application, particularly neonicotinoids and some fungicides, has been found to reduce earthworm survival and reproduction at concentrations approved for agricultural use. Compaction from heavy machinery removes the air spaces that earthworms require. The agricultural system that depends on earthworm-created soil fertility is, in many regions, simultaneously destroying the earthworm populations that created it. The invasion of North American hardwood forests by European earthworms, brought in soil ballast of colonial-era ships, is producing a different kind of damage in the opposite direction. Eastern North American forests evolved without earthworms and developed a distinct ecology based on a deep layer of slowly decomposing leaf litter. European earthworms consume this litter rapidly, eliminating the forest floor habitat that many plant species, salamanders, and songbirds depend on. An animal celebrated as a soil benefit in agricultural contexts is, in a different ecological context, an invasive species causing significant damage. What Darwin knew. Darwin's last book was not a valediction or a summary. It was an argument, characteristically patient, characteristically concerned with accumulation over time, characteristically focused on the unremarkable. The earthworm was, for Darwin, the demonstration of a principle he had spent his life elaborating, that the most profound changes in the world are produced not by dramatic events but by the continuous, patient work of the ordinary. The animals that have shaped civilization are not, for the most part, the glamorous ones. The mosquito that decided the outcome of wars. The flea that ended the Middle Ages. The silkworm whose eggs were smuggled in a cane. The cod that funded a revolution. The leech that turned out to be delivering real medicine all along. The earthworm, moving 10 tons of soil per acre per year, burying the ruins of empires, building the fields that grew the grain that fed the cities, doing it all from beneath, invisible, unthanked, and, as Darwin understood, as important as any animal that has ever lived. Darwin's attention to the earthworm was not accidental. It fit his larger project, demonstrating that the history of the natural world was written not in catastrophes but in accumulations. The uniformitarian geology he had absorbed from Charles Lyell, the idea that the present landscape was the product of the same slow processes observable today, operating over vast time, found its biological counterpart in the earthworm. The worm did not transform the landscape in a day. It moved 10 tons of soil per acre per year. Multiplied by the millions of years of earthworm activity, this added up to everything visible from Darwin's garden window. The most powerful forces in nature are the ones that never stop. The complete book is available in our store, link in the description below. Subscribe for more history, and we'll see you in the next one.